It'll warm up. It'll warm up. Okay. Where snow severe weather. I started in 70. No, 81. 81 something. I've probably been old. Or an annual fishing trip. I've never compiled the thing silver lining. No. Yeah. I'm usually on the Monday evenings. Zoom meetings. So I harass these guys. Okay.
Well, good morning, everybody. Welcome to the Dayton Hamvention. It's so nice to be back again for another year. And it's so nice to see everyone out here. So my name is Nathaniel Frizzell. My call sign is W2NAF. And I am an associate professor of physics and engineering at the University of Scranton in Pennsylvania. And it's always a lot of fun to be here. And I got started, the reason I'm a professor and I have got my PhD in ionospheric physics was because I got started in ham radio when I was 15 years old. And and even before that, I went to a Boy Scout Jamboree on the air, and that's when I first learned about ham radio. And I just thought this was really cool, so I just stuck with it, and I eventually ended up with a PhD in ionospheric physics, working at a university. And while I was in grad school, I was able to start the HamSci community, or the Ham Radio Science Citizen Investigation. And this was actually started formally back in 2015, so the whole effort is now over 10 years old. And our first real HamSci project was the 2017 solar eclipse. And it's really cool that since then, we have been able to have additional solar eclipses, and we're going to hear some of those results today. And we've also added quite a few other projects along the way, which we'll talk to you about. They include the Personal Space Weather Station, the Meteor Scatter QSO Party, and we're even starting new additional initiatives. So what exactly is HamSci? HamSci is a collective or a community that allows university researchers to collaborate with the amateur radio community in scientific investigations. And it's really neat because many of there are people in the university who study the ionosphere and radio propagation professionally, but don't necessarily have the practical experience that amateur radio operators have. And amateur radio operators have lots of interesting technical, or I'd say very practical experience with radio propagation and radio, but they don't always know the formal methods of science the way that you would if you went through the formal training to become a scientist. And then there are some people that are really members of both communities, are both really hams and both professionals. And what we try to do here at HamSci is get everyone to work together for a mutual benefit. So HamSci has 3 objectives. We advance scientific research and understanding through amateur radio activities. We encourage the development of new technologies to support this research, and we provide educational opportunities for the amateur radio community and the general public. And we're very collaborative, so I lead the project from the University of Scranton, but we also work with many other universities, Case Western Reserve University, the University of Alabama, New Jersey Institute of Technology, MIT Haystack. We need to now add Dartmouth College to our little logo here because we're now working with Dartmouth College as well. We work with the TAPR group, and we've received significant research funding from the U.S. National Science Foundation. We are an official NASA citizen science project, and we've received quite a bit of NASA funding, and also ARDC. So how do you get involved? Well, now we have almost 1,500 members, and you can get involved just by going to hamsci.org, and there's a big blue button right there in the middle, and you can join our Google group and mailing list, and we have specialized telecons as well that happens each week. Now, it's with the HamSci community, it's sometimes a little daunting to figure out how to get integrated into everything because you might get in and you're like, I don't know where things are. I'm not sure what project I should be working on, or everyone seems like they know what they're doing, but how do I fit in? And that's part of the, we're a very organically growing community that way. But if you talk to us, we have, you can talk to myself or Gary McKeaton, AFAA, or where are you? He's right there. Gary is our amateur radio community coordinator. If you talk to one of us or any of the speakers today, we will listen to how you would like to get involved, and we will try to help you figure out the best way to join us. So it's really a lot of fun. We are very closely tied with the TAPR organization, and TAPR has been around since for over 40 years, and they're perhaps best known for the TNC and TNC2 back in the 60s and 70s, and then they've done a lot of SDR, software-defined radio work, and many other things. And TAPR is really the engineering branch of HamSci. So here at HamSci, we focus on trying to advance scientific knowledge, but in order to do that, we need radios, we need instruments, we need widgets, and TAPR really helps, they do that development. Now, by some oversight this year, we accidentally scheduled the TAPR forum and the HamSci forum at the same time, and that was not on purpose at all. So over in Forum Room 4, our TAPR friends are discussing the development of a new software-defined radio receiver for use with something called the KA9Q radio software. They're going to be talking about antenna selections for the different receivers we have. They have a new antenna called the single antenna system, receive antenna. So they'll be talking about those things. And the presenters there this morning are Dave Larson, KV0S, Paul Elliott, WB6CXC, who's really one of the people who's just been driving a lot of the design and production for the instruments that HamSci is using. George Birkett, K9TRV, who's just been excellent in helping to diagnose receiver problems, receive site problems, and John Ackerman, N8UR, who is doing the GPS precision timing. So they're really great. So even if you can't make it to their forum today, please come by and visit both of us. We are located in the booths right next to each other in Building 5. So that's 5007 through 5011. All right, so for our forum today, we've got 4 talks, and the first one is going to be by Bob Reif, W1XP. Now, he's going to talk about a project called the Grape 1 HamSci Receiver Build Project for Education and Science. So a little context here. We now have a project, and we've had for a number of years, a project called the Personal Space Weather Station Project. And the idea behind this is that we develop different instruments that amateurs can install at their houses or other properties, and you can use this to do ground-based sensing of the ionosphere and the magnetosphere. And we've got many different instruments in this project. We have a VLF receiver, we have a ground magnetometer, we now have a really awesome software-defined radio receiver that can listen to the entire HF band, decode all of the Whisper FT8 spots, act as a software-defined radio. It's a really neat project. But the Personal Space Weather Station project really got started with a small receiver called the Grape 1, and that was developed by John Gibbons, N8 OBJ at Case Western Reserve University. And the job of that receiver was to listen to WWV and WWVH and CHU and monitor HF Doppler shifts on their carrier. And you would use a GPS disciplined oscillator to provide precision frequency measurement. And this was a fairly small kit that was fairly low cost to build, fairly easy to understand, and it could give you really neat insights as to what sort of variability is happening in the ionosphere between you and WWV. Now, in many ways, the software-defined radios have given us much more flexibility. We're able to do all of that and way more with our software-defined radio receiver. But with our software-defined radio receiver project, it's really just a Linux computer, a SDR that you buy off of Amazon, the GPSDO. You plug all this stuff in, configure the software. You never get to actually hold a soldering iron. It's very hard to actually look at the individual components and see and say, oh, this component's doing this. I understand how this works. And with HamSci, one of our missions is education, and we really wanted a software, or we wanted a radio receiver that would address someone's need to learn how to solder, to learn how to build, to understand how the whole system worked. The problem with the initial Grape 1 design is it included a few surface mount components that were hard to build. And so now our volunteer Bob Reif is taking that project, redesigning it to just fit on a little board with all discrete through-hole components that can be used in an educational setting to teach someone how to solder, to help them understand some basic receiver architecture, and then also create an instrument that still provides really interesting insights into the ionosphere. Now, Bob is no stranger to hardware design or citizen science or ham radio. So he was telling me that he got his ham radio license in 1955, and he has been doing citizen science with ham radio since the International Geophysical Year in 1957. Now, how many people here know what the International Geophysical Year was? All right, quite a few. So probably a good percentage more than the average person you meet on the street. So the International Geophysical Year happened in 1957 and 1958, and that was a period of immense collaboration between many different countries to study the geospace environment and the Earth as a whole. And that year launched many initiatives going forward and leads us to where we are today. So with that, I would like to welcome Bob Reif up to the stage, W1XP, and he will talk to you about his Grape 1 through-hole receiver. So please give Bob a nice round of applause.
Thank you, thank you, thank you. Welcome and good morning. Yes, it's been early. I am really pleased with the way Nathaniel went through and took about the first 10 minutes of my speech by explaining what ham radio science is and what the SDR and the Personal Space Weather Station are. So I'm really going to jump into the middle of my talk in a way, because you've had such a good introduction by Nathaniel. Now, if I can, the wheel works. What is, one of the things that I wanted to do is, my title was Through Hole Grape. And the whole idea is we wanted to take this nice little receiver that's built with small surface mount parts that most people can't see without a magnifier. Well, I was concerned about building, and I'd been building fancy radios with chip components and things professionally for years. But I wasn't enthused about building a surface mount radio, but I did. In fact, we built 50 or more of them, and we distributed them to hams who didn't want to take the job on of building them. And the thing we kept thinking about this all along and kept saying, you know, if this was a through-hole design, a lot of these people would be building them. So we took the job here back in March to come up with a design of a through-hole radio. So I was thinking, well, my title could be Through-Hole Grape or Back to the Future. But I couldn't find a picture of a DeLorean. So anyway, why a through-hole grape? Well, as I just said, the idea is to get something that people are not afraid to take on the job of building, and particularly young people who we would try and get interested in science, engineering, technology, and mathematics, STEM. And that's exactly what happened to me in the IGY in 1957. And my whole career that followed after that was very exciting, and I went and did things. I worked on the Apollo program. I worked on a radio that flew on the space shuttle. Unfortunately, the only time I was on the shuttle, it was sitting on the floor in the factory. But I still wanted to write my name on the wall. Anyway, we decided to come up with a design that people would not be afraid to build. The other thing we needed is the grape receiver never was in a electrically conductive case, so it was susceptible to interference, local interference. Even the Wi-Fi chip in the computer would interfere with the radio. So we wanted to be sure it was put in a physically isolating package. And we thought it would be nice if we could add more frequencies. So to take that on, we wrote up a few requirements. And requirement number one was it should work as good as the existing radio. We shouldn't be forced to accept something that didn't work as well. So that was one of the prime requirements. The second one was no surface mount parts. We also wanted it to be compatible. We didn't want to have to design the rest of the system, which included the local oscillator source and a Raspberry Pi computer and the software that ran on it. Well, if you add more frequencies and things, there's only going to have to be some modification to the software, but otherwise it's a plug-in compatible. You just disconnect the old one, connect up the connectors to the new one, and it'll work fine. Now, the frequency range of the original one was 2.5 megacycles, 5 megacycles, 10 megacycles and 15 megacycles WWV, and it was also the 3 CSU frequencies. Now the CSU is the WWV of Canada, and it's located in Ottawa, Canada. The end result is we added 2 more frequencies for WWV. We added 20 megacycles and 25 megacycles. So it covers the original WWV frequencies and CHU frequencies plus 2 additional ones. Now, whether we really need that coverage looking forward with the declining solar cycle or not is a question that we still need to decide on. But anyway, what does it look like? Well, this is a schematic diagram. I hope you can at least see it well enough. But the part here defined by all this circuitry is the RF front end of the receiver. This is the RF selectivity that provides the frequency coverage of all the channels that I described. And that's done by plugging in jumper little, like you're programming your disk drive in your old PC. There's essentially, this is the equivalent of a band switch, and this set of jumpers is equivalent to the tuning dial. So you select the band, and then you select which of the frequencies within that band you cover. This component here is a double balance mixer. That's the thing that does the RF to audio conversion. The original surface mount design used an NE602, NE612 integrated circuit. It was designed in 1982, and it's now out of production. So it's a piece of unobtainium. So we needed to replace that, and we spent a lot of time looking for a mixer to replace it, and we actually ended up with a mixer that we're actually building. We'll have to wind 2 transformers here and put some 4 diodes into a ring and make it. But it works very well. So it's a suitable replacement. It's just big compared to this little tiny thing that's now 2 toroids and 4 diodes mounted on a PC board. The rest of the circuit, this is all essentially an audio amplifier. All of the gain of this receiver, and this is a challenge, is at audio frequency. So you with so many dB of gain in one little place, it's very hard to be sure you come up with a design that isn't an audio oscillator. But so it takes a lot of thought when you lay it out. And fortunately, I've been joined in this project by a fellow who's been one of my friends and associates, both in amateur radio and professionally. We worked together for years. To also, by the name of Warner Harrison, he's K4 or K1 KG, K1 King George. And don't anybody tell Warner that laying out a printed circuit board isn't fun. He has done a magnificent job. I'll show you some pictures in a minute of the work he's done, but he is the one who has really driven this project to the state where it is now with his diligent work laying out and helping with the design. both. And it's a team project between Warner and I, and then there's going to be some other people get on the team before it's done for sure. But I just want to recognize that Warner has been a major contributor to this program. And it's the first real ham sci work he's done. And he's pleased and proud of what he's doing, so, and he deserves a lot of recognition. To continue a bit, this is a detail, a little just of the RF selectivity thing. And this is occupying about 40% of the printed circuit board. And the board is hard to build only because there's so many parts on it. There's almost 70 parts. Most of them are resistors and capacitors, but there's 4 toroids to wind that are just inductors. There are 3 toroids to wind, no, 6. There's 5 toroids to wind that are just that are transformers. So it's a lot of kind of detailed work that people. So we're thinking about what can we do to try and reduce some of those parts. And for example, if we would not cover the 2.5 megacycle band and CHU, that saves 1 large inductor to wind, and it saves about 4 capacitors. The capacitors are hardly much bigger than the surface mount parts, but at least they have low leads you can poke through a hole. And likewise, at the other end of the spectrum, there's an equal number of parts. There's 1 more toroid you have to wind and some more capacitors. And that covers the 20 and 25 megacycle frequencies. And with the decaying sunspot cycle, it's very likely we may not have those bands too much longer. So between 2.5 and the 3 megacycle low bands, which are dead at night because they're nighttime bands because they're dead in the daytime because of the D layer absorption. And the 2 high bands are dead at night because of the lack of ionization. So maybe these are not too important. So we need to discuss with the user community whether we should add this complexity to the design or not. So there's some decisions to make, but progress. We've built 2 boards. We've laid out a whole bunch of boards, and we've got about parts and kits put together for 5 kits to get people who, at this point, we call it a prototype, and we want to put kits in the hands of people who will build the board, still give us comments on the construction difficulties and whatever, and get them on the air so we can do a side-by-side comparison between the through-hole design and the existing design. And that's our goal at the moment. But we want to get that done while we work out some of these more logistical problems about how many bands we cover and how we're going to maybe get the production end of this thing going. but we would really like to get this in the hands of students by this fall. So it's an ambitious program, but, well, sometimes you only work best under pressure. Here's what it looks like. Here's the original grape one. This is a small little surface mount board. It certainly could be built by a machine. And like I say, we've built 50 of these. I've probably soldered 30 of them together myself over the last 4 years. And this is the first of the prototypes. We chose an Altoids candy box. First of all, if you like the candy, you could consider the boxes being free. You can actually buy these boxes from Amazon, and in quantities of 40, they're only 82 cents. So we can afford that. Oops, where do we go here? Pump the... Anyway, this was really a challenge. How much can we get in an Altoids box? So we went through this 4 times, laying it out and changing things and adding things and deleting things. And that's about all we can get in. And it's really too complex, and that's why we'd like to simplify it. But we've done some things that we've added an audio isolation transformer, which was not in the original grape, as you can see. But most people end up with an audio isolation transformer external to these. We've got these big toroids rather than surface mount toroids. I'm down to 1 minute. Okay, time to go. This is a graph of the RF response of all the WWV frequencies. And you can see we got pretty good rejection, particularly of the broadcast band on the low end. This is 2.5, 5, 10, 15, 20, and 25. And likewise, this is the CSU response. And this is just to show you some of the progress we've made. Here's the audio response of the original grape, and this is the proposed audio response. And we've actually this is an actual measurement data of the audio response of the grape through hole. And this is some data on the feed through, and these numbers are very good. We're proud of these. This is the amount of LO that leaks out the antenna port, which is a very critical thing in a direct conversion receiver. And there's the receiver as it stands. And there's first light. So that was when I turned on the first board. Power line noise was horrible, but boy, it worked great. I'm about running over, but does anybody have one question?
Speak directly in and speak loud.
If we were to build it at home and use it operationally, how would it work? Would it have to be on all the time? Is it hooked up to a certain antenna? Is it hooked up to your computer all the time?
We should have described the personal space weather station in more detail.
Yeah.
The personal space weather station is a 24/7 kind of thing. Now, that doesn't mean you can't turn it off or anything, but normally the idea is you turn it on, set it up on WWV or one of the channels, and it just runs. And daily, it downloads the results and it goes to the University of Alabama, where it's stored and anybody can access it worldwide.
Okay, this is my question.
Thank you.
Thank you so much, Bob. I really appreciate that, and it's very exciting to see this project come alive. And yes, so as Bob said, with the Personal Space Weather Station project, you do keep it running 24/7, but with this through-hole grape, you would be able to use a very modest antenna. As long as you can receive WWV on like a wire antenna, that will work. So you don't necessarily need to take down your other station or something like that. All right, next we have Gary, AF8A, who's going to talk to you about the Meteor Scatter QSO party. And I think last year, this was a brand new initiative, and we were just launching it, and I was really like, I wonder if this is actually going to work. And now, a year later, we actually have some results we can show you. So, Gary, AF8A.
Good morning. Good morning, everyone. My name is Gary McKeaton. I'm one of the many community volunteers who helps HamSci achieve its goal of doing good science through amateur radio. Today, I'll be talking about meteor scatter. It might sound like an exotic mode to some of you, but I hope to convince you before I'm done today that it's easily accessible to almost anyone with an HF or VHF station. So today we'll start with some meteor basics, and then move into how to operate using meteor trails as signal reflectors. And then we'll talk about the science we might achieve if the ham community joins us by operating and submitting data. And finally, I'll finish with a few words about the past and future runnings of the HamSci Meteor Scatter QSO parties. So let's start with some basic definitions. So even if we're meteor scatter rookies, we don't quite sound like it when we're talking about it. So the term meteoroids, those are the bits of matter thrown off, usually by comets, but sometimes by asteroids circulating in space. Meteoroids are dust, dirt, ice, moving through our solar system, usually in a predictable orbit, following in the wake of their parent object. And I've got a diagram of that in a minute. Meteors, those are the result of when those little bits of meteoroids actually encounter the Earth's atmosphere at high speed, burning up and eroding in the process. They often disappear completely in just milliseconds, but it's meteors that make meteor scatter QSOs possible. Meteorites are what's left of those meteors which survive reentry, what some very lucky people will sometimes occasionally find on the ground. So it can be difficult to visualize how meteors travel through our solar system. This 2D representation, both colorful and well-detailed, is a reasonably good attempt. But I'd like to draw your attention to the highly elongated elliptical path in white there, the kind of cigar-shaped path. That's tracing the path of Halley's Comet. But at the upper, I guess, northwest corner of that, if you will, take a look at the Halley's Comet path where it intersects Earth orbit. That intersection leads to 2 meteor showers every year. When Halley's dirty, dusty remains cross the Earth's atmosphere. Those 2 showers, the Orionids in October and the Eta Aquarids in May, which just happened a few weeks ago. Really, though, for a far better representation of this and many other meteor orbits, visit meteorshowers.org, which has very clear 3D animations of meteors in motion. So, now that I've made you all experts on meteors in 2 slides or less, let's get into the radio-related aspects of this spaceborne matter. The physical process we care most about as hams is the ionization, which occurs as meteors slam into our atmosphere, creating ion and free electron clouds, which are useful for reflecting radio signals over the horizon between a transmitter and a receiver, generally about 300 to 1,500 miles apart. Now, just out of curiosity, as an aside, did anybody here was either in the Cleveland or the Houston areas where we had the big 2 meteors come across and crash into the atmosphere earlier this year? I live in Cleveland. My wife and I were having breakfast, and the sonic boom from the Cleveland event, I got to tell you, was really something. We jumped up, looked out all the windows. We live in a neighborhood where they're building homes and stuff, and it's like we thought something bad had happened here, just a meteor. Anyhow, so let's talk about making some QSOs. So as I said earlier, meteor scatter may sound like an exotic mode, but actually a pretty simple station can make meteor scatter QSOs. 100 watts in an indoor dipole will work, though like a lot of things in ham radio, 500 watts in a small beam, a Moxon, or even a high dipole, of course, would work a lot better. Personally, I use a 6-meter vertical and a 10-meter dipole, both of which mounted my attic to enter the 2025 MSQP events as a receive-only station. So indoor antennas can get you some results. So I go over here, I guess I'd call this a quick start guide to making some meteor scatter QSOs. I'm not going to go into a lot of detail here about software configuration and setup, because if you're like me, you'll forget at least half or maybe more by the time you get out the door. But I would like to point out that and get you in the right direction and make you comfortable with the idea of operating meteor scatter. So this is a meteor scatter QSO that was in process. Note that the software is WSJTX and the mode MSK144 look a whole lot like FT8. There are many similarities. You see the band activity window on the left, the transmit messages window right, the spectrogram above, and so on and so forth. The suggested frequencies are shown here on the slide. 50.260 is predefined in the software. If you click on MSK144, look for 6 meters, it'll set you to that frequency. The 10-meter frequency, 28.145, is something you'll have to add yourself, or maybe Nathaniel to talk to his buddy Joe Taylor and get that added to the frequency list for the next release of WSGT. But the reason 10 meters isn't in there, until a few years ago, you could not operate MSK144 on 10 meters. The baud rate was too high, but the FCC has recently changed their rules, allowing us to do MSK144 on 10. But anyhow, the key thing to remember here is the web address, hamsci.org/MSQP. That'll take you to a page that has far more detailed explanation than all this kind of stuff. So my suggestion for meteor scatter rookies is to start by listening, especially on 6 meters, early in the mornings. Learn to recognize the sounds and the spectrum graphs coming from meteor pings. At the same time, monitor pingjockey.com and watch the banner between meteor scatter stations, and I think you'll catch on pretty quickly. So here in this top graphic on the right, you can see 2 meteor pings there. Those are the 72 millisecond long transmissions from MSK144 reflected back to my station by a meteor, and ended up in 2D codes. I saw a couple of stations calling CQ, so that was valid data. Below that was just a single ping that came back, and that was KB9 TVR in QSO with somebody else. Now, today as we're discussing meteor rights, I owe it to also mention some meteor wrongs. It may seem obvious to state this, but keep in mind that when we send a CQ up into the sky, any of us, we really don't have any control over the propagation mode, which may carry it back down to the other stations. One option is it may be MSK144 off a meteor, that's great, or it may be good old F-layer propagation, it may be sporadic E or even tropo. Shown here, this picket fence type of diagram is something called aircraft scatter, and it is exactly what it sounds like. These MSK144 signals are being reflected off the wings or of a fuselage of probably a commercial aircraft liner at 30,000 feet or so. But the thing is, when you've got all these modes and things going on and you're trying to do science with just the meteor scatter trails, maybe knowing and realizing that we've got all these other options and things might make you appreciate the challenge faced by the scientists and the data analysts who are looking at the submitted data. They are working to figure out how to filter out the meteor scatter QSOs from all the others. And it's not an insurmountable problem. In fact, we've got an undergraduate student at the University of Scranton who just finished her bachelor's in physics, working on some machine learning techniques to pull the meteor scatter data out of all the rest. So, speaking of science, hard to believe, but it's taken me 13 slides to arrive at the real purpose of my talk. To introduce you to and to excite you about the scientific inquiries that HamSci plans to undertake regarding meteor scatter communication using data created and saved by hams like us. But to begin with, what would science be without some equations, okay? Well, don't worry, I'm not going to go over these things in detail or even superficially, but I do want to point out one variable in each equation and that's lambda representing the wavelength. The formula on the left was developed in 1961 by a gentleman by the name of McKinley, and that's what we call the signal strength equation that predicts what the reflected power would be off of a meteor trail. And you can see there's a term in there, lambda cubed, a wavelength cubed. The formula on the right is again from McKinley in 61, but is also what I call the duration or length equation that predicts how long the meteor trail should be there and effective as a reflector. That has a term called lambda squared. What that's telling us is that changing our wavelength from 6 meters to 10 meters is going to have a huge change in both of these signal strengths and the time that's available for reflection according to these equations. In fact, a 66% increase in frequency is what we're talking about, going from 6 to 10 meters. So I'll reiterate my statements about stronger and longer when moving from 6 to 10 meters here in a chart format on the bottom. Let's do like a little thought experiment. Assume that 6 meters is our starting point. If we could record a single QSO on 50.260 and assign that QSO an arbitrary value of signal strength of 1, and then we're able to repeat that very same QSO on 10 meters, 28.145, we would expect the signal to be about 6 times stronger. That's the bottom line of this chart. As for duration, the reflection time should be about 3 times longer when moving from 6 to 10 meters. Those are really significant changes. So I just suggested we'd like to duplicate a single QSO on 2 different bands with everything else being equal: power, antenna, losses, meteor position, ionization levels. Of course, such a duplication is a practical impossibility. But thanks to math and statistics, if we collect data for hundreds, or even better yet, thousands of QSOs, it should be possible to spot strength and duration trends in the data, perhaps even assign values to them, and to see if these numbers actually work out. So where does all this data come from? Well, right now we're looking at 2 sources, one gathered automatically and one kind of semi-manually, but both from WSJT. All right, so before everyone glazes over on the science, we'll pivot back to radio and talk about how to generate data useful to the science community. The first and by far the easiest method is by enabling PSK reporter spotting within WSJT, and I think this is the default setting. But PSK reporter data is valuable because it contains information such as the locations or grid squares of transmitters and receivers, the date and time that QSOs took place, the frequency, and so on and so forth. I think it's worth noting that HamSci and many other researchers have been using PSK reporter data for almost a decade. Over a dozen peer-reviewed scientific papers have been referenced using PSK reporter data. So I'd like to remind everyone regarding the next data source is that all the so-called Joe Taylor digital modes, whether it's MSK or FT4, FT8, and J65 and whatnot, those are all audio-based modes. When you're transmitting, your rig converts audio from your computer into RF, sends it down your coax and out to your antenna. Conversely, when you're receiving, those received signals come in as RF. They are either down-converted or sampled into audio signals that WSJT then decodes. Those audio signals are a goldmine for the researchers. We are fortunate that WSJT allows each user to record all their decodes as individual WAV files. Again, I'm not going to go into all the details here, but please know that we can learn far, far more from the WAV files, the audio recordings, than probably anything else we've seen. So, should you decide to participate, please take the time to read about saving WAV files and then how and where to upload them to HamSci when researchers can have access to them now and far into the future. So what to do with all this data we're collecting, right? Well, earlier I mentioned studying signal strengths and durations relative to wavelength and testing out the McKinley assertions from 1961. There are additional areas of interest, such as echo ceiling height. How far above the Earth's surface are these reflections taking place? Can we develop recommendations for station design, frequency, power levels, geographic footprints for more reliable meteor scatter operation? I think one side benefit of these events, we hope to stimulate the use of 10-meter band for meteor scatter QSOs. Today, as close as we are to the cycle 25 peak, In 4 to 5 years, we may be at the bottom of another cycle. 10-meter QSOs will become rare for many traditional ops, but perhaps not so for the skilled meteor scatter folks. So HamSci kind of dipped its toes in meteor scatter last year by sponsoring 2 QSO parties, one in August and one in December. We are thankful for all the entries, all the operators who got on the air, and those who simply monitored the 6 and 10-meter bands for meteor scatter signals. It was gratifying to see the tilt towards 10-meter operation. The first event, we had about a 47-53 split between 6 and 10 meters. And on the second event, about a 25-75 split, a lot more activity on 10 meters, which is good to see. Because we spent a lot of time and effort pleading our case with meteor scatter ops who, for decades, had only the VHF band 6 meters and above for meteor scatter. So for 2026, we're going to double down and maybe more, doing more events, doing more showers. We see great potential in meteor scatter operating and meteor scatter science. As a result, we're modifying our contest-like format a bit for 2026, along with expanding our events to about a half dozen major showers in the next 7 months. One thing will not change, our emphasis on collecting wave files, which we expect to be the bread and butter of our data sets and future research. So to close, I'd just like to remind everyone and acknowledge that events like the MSQPs don't happen in a vacuum. A great collection of talented, collaborative individuals contributed to the success of the events. And my parting words, of course, join us in 2026. And of course, stop over to our booth in Building 5 this weekend. We'd love to talk meteors with everyone. Thank you all.
All right, thank you. We have a question. Maybe Chip and Gary.
Here you go. Speak directly into it.
Thank you. Excellent presentation. I did want to point out that McKinley's equations there break down as the wavelength increases towards infinity. And this is actually an aspect of the Frisch equation. It's a modified version of the Frisch equation. What I'm trying to say here is that it's valuable to compare it to what he predicts, but I think you're going to find that some of your dwell times, your lengths of time are going to exceed 15 to 20 seconds as you go down below 10 meters, even going down to 12 meters. I'm curious to know if you're considering also using 12 meters as we approach a sunspot minimum. Thank you.
Thank you, Chip. I appreciate that. All right. Thank you, Gary. So yes, everyone, please look at operating some meteor scatter this coming year. Next, a new exciting opportunity. We are going to be part of a NASA mission. And to talk about that is going to be David McGaw, N1HAC, who is a HamSci collaborator and a research engineer at Dartmouth College. Come on up, David.
Good morning. I'm going to be talking about the Cinema/Movie project mission. Cinema is a NASA mission that has been recently approved, and Movie is a citizen science initiative attached to it. Principal investigator is the person I work for personally, Robin Millen at Dartmouth College. She's been involved in a number of NASA missions up to this point. The big one that we had previously was a balloon mission of 20 balloons, 2 different campaigns in Antarctica to study the radiation belts and the X-rays that electrons that are dumping out of the radiation belts generate, and the balloons were picking up those X-rays. But this is now a orbital initiative. The idea is behind the looking at the Earth's geomagnetic tail, which is the source of ionospheric changes, aurora. It is our space weather. So this cinema is going to provide the first system-level cross-scale view to revolutionize our understanding of the magnetospheric dynamics. This convection, this is a simulation of what happens as the solar wind blows past the Earth and how dynamic our magnetic tail is. Drives powerful storms, explosive substorms, and which are the geomagnetic storms that drive aurora. And the overarching goal is to understand the role of the plasma sheet structure and evolution in Earth's multi-scale magnetospheric convection cycle. The plasma sheet is an area behind the Earth where the currents are focused. And then I will quickly say that the dynamics are strongly driven by the magnetic field, direction of magnetic fields of the solar wind and the Earth's magnetic field. If the solar wind field, what we call BZ, is positive, it goes just right past the Earth, and you get the first picture, which is pretty much laminar flow going around the Earth. And this is where, you might have a prediction that there could be aurora, but there isn't. We never know how that magnetic field is going to line up. You can have very strong solar wind and just laminar flow and nothing happens. But then if it's the other way, BZ negative, it drives instabilities in the magnetosphere and basically causes eddies and what's called reconnection in the tail. It throws stuff back at the Earth that gets shunted to the poles, and that's what drives aurora. And so this whole project is supposed to be able to look at all of this at widely different scales. Large scale, an object of the project is to determine the large scale structure and evolution of the plasma sheet for different magnetotail convection regimes. As I say, it can be very different depending upon how things line up. Mesoscale, the middle scales, determine the link between mesoscale dynamics that manifest in the aurora and the structure of the plasma sheet. And then the kinetic scale, small scale, determine connection between particle precipitation attributed to the kinetic wave effects and mesoscale dynamics. And this is came out of the 2024 decadal survey that NASA did, which Robin Millen was actually involved in. It is not well understood how large-scale conditions control microscale processes, how the microscale processes impact the global dynamics, and how the interaction and feedback between the various scales operate. So this is the proposed mission, cinema. It involves polar orbiting satellites, instruments on each satellite for remote sensing, energetic particles, auroral imaging, and magnetometers, and then an evolving constellation. This is one of the more innovative parts of it. There are going to be 9 CubeSats involved that start out in a single orbit, but over time they evolve into 3 separate orbits. And so there are the satellites, the instruments, and the remotes, the magnetometers. And it enables the SMEX with an outsized science impact. A SMEX is a national initiative of small explorer spacecraft, and advances satellite constellations for science. One of the things we'll be doing is we'll be remote sensing both from the satellite and from the ground and building up images of the aurora. By using the aurora, we get an idea of what the mesoscale convection is. It's going to be able to sense boundaries of the magnetic fields, and the energetic particles carry the signatures of key magnetic spheric features. And so we'll be picking those up. And then we'll be remote sensing the actual electrical currents using the magnetometers. Oops. Will you go back? I guess not. So the evolving satellite constellation is an important part of this. You know, where is this going? Sorry. Seem to have lost control of it. It's supposed to be an animation here. Maybe I have to click on it. There we go. So what this is showing is that the magnetic field, it's not a simple dipole field. It stretches out behind the Earth, blown by the wind. And it throws particles back at the Earth along those magnetic field lines. And that's what comes in to the poles, creates aurora, but it does, we can actually pick up the particles themselves before they hit the atmosphere using the polar orbiting satellites. And so with this involving satellite constellation, we can actually image the magnetotail by picking up the particles that it throws back at us. So there are a lot of people already involved in this project, and as we bring in citizen scientists, this will certainly grow, but this is the team that is working on the actual NASA mission itself. Now, MOVIE is what we've coined as the citizen science initiative connected with this. Multi-platform observations from volunteers, ionospheric experiments. That was coined by Christina Collins, who is involved with this project, heavily been involved with HamSci at Case Western University. But we're intending to augment the science of the cinema mission by a distributed series of instruments on the ground. MOVIE enables new discoveries by engaging a diverse community of volunteers. Here we are, and much more. There's people with the HARP project. This is the principal person of the MOVIE initiative is Mike Hardinger of the HARP project. It is not the secret mind control experiment up in Alaska, which I can tell you it isn't because they let me in and I don't have a security clearance. But I have worked with that one. That's HAARP. This is heliophysics heliophysics modification of resonances in plasma, HAARP. And that's one of the parts of this. And then we have the HamSci community involved. EasyMag is another citizen science initiative of distributed ground-based magnetometers in connection with a very innovative NASA mission that is currently in orbit that uses visual sensors to sense the Earth's magnetic field. And then we have aurora chasers with distributed all-sky cameras and whatnot involved in this. So we developed Cinema Movie to integrate these 4 projects with the Cinema mission to address new science questions. The project mentioned are all unified through studies of multi-scale auroral phenomena and ionospheric impacts, including impacts on radio waves and geomagnetic disturbances. Cinema will provide new data that support the science goals of all 4 of these citizen science projects and enable them to address the new science questions. So it's a collaborative. This is our cast, so to speak, so far. There are a lot of us already involved, and we, of course, hope to get many more. There's myself. I'm a research engineer at Dartmouth College. Kelly Cantwell, who's next to my picture here, she just graduated from Dartmouth with a PhD. She's now at University of Calgary and still going to be very much involved with the project. And of course, Mike Hardinger is heads up this side of things. Robin Millen is our overlying PI. Christina Collins, I just mentioned, she's with us at CASE. And of course, Nathaniel is in this with us. So the movie goals, by providing multiple platforms for engagement, movie empowers volunteers to make new discoveries in partnership with the cinema team. And it's to augment cinema science objectives and provide multiple pathways for volunteers with different skills, interests, and availability to contribute meaningfully to the cinema mission and its, of course, to have a positive experience. So the components uses proven approaches of crowdsourced event finding and open source instrumentation that have led to high impact publications in other citizen science projects. So the crowdsourced event finding of cinema, we'd have people involved working with the cinema data and finding interesting events within that. That's actually, we keep talking about having AI go search for these things. People are much better at finding interesting features than AI has been, at least up to this point. We'll see. Observational campaigns also supported by open source instrument kits, hence HamSci and some other initiatives to study the causes and consequences of these multi-scale aurora. One of the things that has been done is geomagnetic disturbance statistical studies. What factors control large amplitude geomagnetic disturbances linked to the mesoscale auroral features. And the motivations are space weather hazards, unresolved connections with magnetotail and aurora. Just basic science so that we can predict what these things are doing. What factors control large amplitude geomagnetic disturbances? And we'd work on graphical user interfaces that people can bring in the data, work with it. And then what factors control large amplitude geomagnetic disturbances linked to these features, and the data collection and expected outcomes. More studies, observational campaigns during the geomagnetic storms, all sky imagers, and observational campaigns with aurora chasers fill gaps between the imagers, open source instrument kits. This is EasyMag, which is already doing magnetometers, our personal space weather station, which can include magnetometers, provide additional coverage and with magnetometers and other instruments. We've got some various things that are in mind of making use of the Personal Space Weather Station hardware for some other things than we have looked at previously. Expected outcomes, the scientific publication of Aurora Chaser images, open source instrument kits, and documentation. And radio wave statistical study and case studies. This gets very much to what we've already been doing with HAMSci. Auroral precipitation leads to changes in the ionosphere that affect radio communications both locally and non-locally. Connections with mesoscale aurora have not been explored in depth, but lack of coordinated investigations, lack of radio wave data sets with sufficient granularity. So we're working on that. This is a picture of one snapshot of the Personal Space Weather Station network during the, I'm not sure which eclipse this was, but the whole eclipse got us getting people involved. But then the question was asked earlier, is this a 24/7? And yes, it is. We expect people, hope people will run these, just turn them on and let them run. And you can run your station next to it and whatnot, and hopefully it doesn't interfere too much. But the idea is to get continuous data coming back, because you never know what events are happening until you look for them. So we're going to fill this out. One of the things I will mention right now is that we've got good coverage happening in the lower 48, but we don't have good coverage up in Canada and Alaska. So we're going to be looking to encourage hams and other citizen scientists to build out the network toward the north. Aurora, of course, can happen down here, but it happens more often up there. And as was pointed out by my other boss, the other person I work for at Dartmouth, Jim LaBelle, we've been doing these radio studies of various sorts in the Arctic and Antarctic for a while, and a lot of our receivers are above where the aurora happens. There's very special stuff that happens up there. So we'll see how we can encourage people in all parts of the globe to get involved. And so we're empowering volunteers to define questions. In established communities such as HAMSci, often define their own research questions. Movie provides them with the tools and freedom to innovate with cinema data. And I think we're almost done here. Ground-based remote sensing, we have the Personal Space Weather Station. There are many configurations available. The Grape 1, Grape 2, the newer RX-888 base systems, and we're working on more. VLF receivers, GPS receivers actually create geomagnetic data, ionospheric data. One man's noise is another man's data as it works out. So we can actually do a lot of remote sensing of the ionosphere using GPS receivers. Rheometer, that's a new one. That's where we pick up galactic noise, get a quiet day curve, and then when that changes, it gives an indication of ionospheric absorption due to these particles that are coming in, and possibly all sky imager integration into the Personal Space Weather Station. That's also being looked at for the EasyMag systems. And movie Phase B. Phase B is the design phase of a NASA mission. Our efforts will include feasibility study for further instrument development, leveraging instrument development and creation that already has been funded and underway. This is a pretty dense list, but this is all the different things that we can look forward to studying using our radios. F-layer propagation, that's the highest layer that most of our stuff bounces off of. We get Doppler shifts off of the ionospheric changes, which come from solar flares and other things. Time of flight data, get heights and such. Amplitudes get changed. And then D-layer absorption, there are various ways that we pick that up. That's what causes the lower bands to disappear during the day. But there's some regular stuff that happens, but then there's stuff that happens due to solar flares and this precipitation from our geomagnetic tail. So stay tuned for the main feature. We have the plot, a great cast, an audience from the prequels. Movie will enable new discoveries by engaging a diverse community of volunteers. And that is the presentation, and I hope people will find it interesting.
Thank you. Any questions for David? We are very excited to be part of Movie. And it's, as David said, we are in the phase B right now, which is the design phase. So we are actually working out a lot of the details of exactly what we're going to be doing later in the project. So we'll report back on that next Hamvention. And now I'd like to welcome Dr. Kuldeep Pandey up to the podium. Dr. Pandey is a postdoc at New Jersey Institute of Technology, and he is working almost full-time on analyzing the solar eclipse amateur radio data. Come on up, Kuldeep. And this is, so he will talk about solar eclipse through ham radio, what the bands revealed. And so these are new science results compared to what we've presented in the past. Go ahead, Kuldeep.
Control L. Oh, no. Control L.
I promise we practiced this before. I know exactly what the problem is. Windows Shift P. There it is. Duplicate.
Yeah, we can see this screen.
Now we go here. Now we hit Control. Now we're good.
Yeah. Hi, everyone. Thank you for coming. And as Nathaniel said, we will be discussing results which we have from the solar eclipse QSO party. And this is one set of results which I am presenting. You saw there are different activities like meteor scatters QSO parties, or solar storm, magnetic storm, or other things. So this is results from the eclipse QSO parties which we had in 2024, and some of the results which we had from 2017. And at the backbone of all these studies are hams, or you, who participate, who like to contact others, your buddies, or anywhere around the world. And in doing so, you generate lots of radio contacts around the globe. And most of these stations are, as you know, located in the contiguous US or European sectors. So it gives us a good advantage of high gridded transmitter receiver locations over contiguous US and over transatlantic communications to analyze scientifically the data of the ham radio and bring out science results. So as you can see, during the eclipses 2017, 23, and 2024, there were lots of radio spots which were being reported, about 4 million logs in 2017, and we have come to about 160 million logs around the globe. And contiguous US contributes to most of it, say 56 million logs. And these are radio contacts from one person to another via voice, or this can be through radio, automated radio networks, or reverse beacon networks, or PSK reporter, these kind of things. And they also, all these data is available at MIT hashtag, and they are archived daily. So we can go for the archival data as long as back to 2009, and we can have the continuous studies. Now, this is an example of 2017 and 24 eclipse tracks. Here you have on 2017 from the west coast to the eastern coast, north to the south, and in the 2024 it goes from southwest to northeast, and then it goes up to Atlantic Ocean. And both these eclipses happened around the same time of UT, say 17 to 19 in 2017 and 18 to 20 in 2024. Now, the right-hand side figure gives you a glimpse of how these radio contacts varied in terms of the range, in terms of the population, say number of contacts being made at each UT time, and the y-axis is the range, how far the radio contact from a transmitter reached to a receiver. And on the left-hand side is our results for 17. From top to bottom are different frequencies. Some people like to have contacts at 21 megahertz, some at 14, 7, or 3.5, and there are other bands also. I just included them for example. On the right-hand side, the same information is given, but for 2024 eclipse. And this white dashed line or gray dashed line is the eclipse totality. So as moon comes in, shadows the sun, there is an obscuration level. So this part is the ingress of the eclipse, and this part is the outgress, and the minimum is the totality, the maximum sun being occulted. And you can see here, which I highlight, there are significant activities or clear-cut signatures of changes in the HF communication at different bands. And to better visualize this, instead of having the plots in the UT, we can do one thing. We can align all the radio spots or contacts with respect to the totality. So how far before the totality it was happening and how after. And this gives a better visualization or a way to better see the data output in terms of the solar eclipse. So now in the x-axis is the epoch hour, 1.5 hour before the totality, around totality, and 1.5 hours the totality. Once again, the top to bottom are frequencies, so multiple frequencies in 2017 and 2024. One thing which is very clear, at 3.5 or 7 megahertz, low HF band or higher wavelength, we see a clear-cut enhancement in the range of communications as the eclipse comes in. And it is kind of a local shadow, a temporary night. That's why you have more range coverage, which you also experience during the day and night difference. And at 14 megahertz, there is a different kind of behavior, say around 3000 kilometer contacts, great circle of distance. There was a bite out in 2017, but this did not happen in 2024. Instead, there is an increase in the range of contacts in 2024. As far as 21 megahertz or the top row is concerned, there were very few contacts being made in 2017 in this band. This was the possibility. But in 24, we have lots of contacts, and it shows a gradual increase in the range of contacts or range of communication. Now, if we try to understand this feature, why it is happening, broadly, we already know. Firstly, this was the D region absorption. As the sun light got occulted, D region recombines very fast, fastest recombination. So it responds almost symmetric to the solar eclipse. That's why lower frequencies respond almost symmetrically. But the rays which bounce back from the F region, which has higher lifetime, it will take some time to decay and some time to recover. So that's why you will see a delayed response at 21 megahertz. Then what happened at 14 megahertz? So 14 megahertz somewhere lies in between. And in the transition zone, when you have a weaker or less denser ionosphere, if you deplete that ionosphere, the rays will pass through the space or to the space. They will not bounce back because the ionosphere is weaker. But in 2024, when the ionosphere is much more denser, why? So in 2024, when the ionosphere is much more denser, the bending or the refractive index will be higher. So bending will be much more, and even 14 megahertz will bend back to the Earth. So that's why 14 megahertz showed kind of a different behavior, and 21 also. And the core region is, as many of us mentioned, solar cycling. So 2017 was in the solar minimum kind of year, and 2024 was solar maximum. So here you will have much more ionization, a denser ionosphere, so higher frequencies will also bend back. So this gives an example that ham radio data can be used to study a long-term changes, say an eclipse, but happening in solar minimum and solar maximum. So some consistencies in the lower frequencies, some differences in the higher frequencies or higher bands because of these differences primarily. So it is really good to see that on a longer term, we have a real test case that, okay, from 70 to 24, we can analyze the eclipse data and we can consistently understand the behavior in terms of the physics. Now, as we do, this all part was, what I gave you was through observations. We can model the radio propagation, which we do by something called MATLAB tool FARLAB. And what it does is, if you launch a fan of rays, say these white lines, from a transmitter, for all the possibilities of elevations, and find out which ray will hit the place which we are trying to contact. So if I fix the transmitter receiver locations, there are a number of possibilities these 2 points can get connected. They can be connected through a one-hop mode, which we call from the Earth to ionosphere comes back, or it can bounce from the Earth and once again go there and connect. So this is 2-hop, 1-hop, 2-hop, and 3-hop modes. In doing so, because the elevation angle is changing, the apogee height or the maximum height the radio wave reached for that particular contact can be different. So here it is very low, here it is very high. So these heights, as I said, the lowermost one, D region, will respond almost instantly to the eclipse. Highermost one, F region, with the higher lifetime, will have delayed response. So it can have both multiple hop contacts or from a different height. Now, in modeling domain, we need to give the background ionosphere to trace it, which comes from the state-of-the-art SAMI-3 model. So SAMI-3 or SAMI-3 model driven by a WACAMX model. So SAMI-3 is the ionospheric physics-based model, but the inherent background thermosphere it drives on is an empirical model, so a data-driven model, so the background. But when I say WACAMX SAMI-3, it is all physics-based. Both background thermosphere and the ionosphere are physics-based. I highlighted this because it will have an implications when you will see just now. So as I said, the possibility that the person you were trying to make a contact with, it could be through one hop, it could be through multiple hops, it could be coming back from the E region, F region, or D region, depending upon different heights. In the modeling domain, we have the ability to, because we can ray trace through all these possibilities, so we decouple between these results depending upon through which hop that possibility was made between TX and RX, and through what apogee height the radio wave came back. And now, as I said, there are two models, SAMI-3 and WACAMX SAMI-3. So let's drive the ionospheric ray traces through both of them and see what happens. And as I said, these are state-of-the-art models, or the ones which are very best at present. So you will see the two models give kind of nearly the same outputs at 7 megahertz. But there are tiny differences if you see the circled red ones. Now, these differences become more obvious at 21 megahertz. Here, you have almost no contact being made around 4,000 kilometers in the SAMI-3 model output, but in the WACAMX, you have continuously well-connected TX-RX coordinates, or say transmitter receiver things. Now, this was WACAMX SAMI-3. And what was happening, say, at 21 megahertz, it was continuously connected. So the one which was driven by the model which is more physics-based gives a better representation of the background ionosphere, and that's why it successfully captures the ham radio data or ham radio contacts. So ham radio contacts, first, in the first result, they gave us a broad picture of solar cycle differences in the eclipse. But if we do it in really more detail, it also helps us to understand which of the latest models in the ionosphere are better representative of the ionosphere. So here it comes out to be a pure physics-based model. And that is obvious also because the data-driven model will be good enough to the data you provide to it. So if you provide, say, 2024 data, it will give you a 2024 data model output better. But if you provide a previous year data and something new happened in this year, it will have slightly off. It will be slightly off. So that's why I think WACAMX, which is a physics-based driven WACAMX SAMI-3 model, gave a better outcome for the ham radio data. Now, as we know, eclipse did not end in the contiguous US. It went on and reached up to Atlantic Ocean. So we had lots of contacts being made from US to Europe, transatlantic communications. So let's zoom out and see what was happening in those radio contacts. So now here, the figure remains the same, but the y-axis limits are different. Earlier, we used to have 0 to 5,000 kilometer within contiguous US contacts, but now we have 4,000 kilometer as the minimum range, and then 10,000. So from here to here. Now, in these, this is a normal quiet day, any day which was non-eclipse, and this is an eclipse day, which you see from now here. What you see is there are changes with respect to the eclipse. Once again, that dotted line, but the more significant changes I am trying to highlight with the red color. So here at 21 megahertz, there is a symmetric response. It goes away and then comes back. Darker the color, more the contacts. At 7 megahertz, this band open up much earlier than it used to happen on a normal quiet day. So first is, let's go back and run the ray trace with the models and check whether the models are able to capture it, and then trying to understand physically what was happening. So first is test it with the Symmetry and Vacamax Symmetry, once again 2 models, and see which of these models is representative of the data which we are observing. So here what you see is the disconnect, and here these are the model output. Here you see a continuously connected 7 megahertz, but there is a bite out around this time. And if you look at the data, 7 megahertz kind of popped in around the eclipse, then there was a bite out, and then it once again got connected. So this feature is well represented once again by the Vacamax Symmetry. Good, consistent with earlier one, but what physically was happening that 7 megahertz got connected much earlier than the other days. So A, we had the eclipse. B, if you look at the transatlantic communications, the eclipse was, when the shadow was somewhere here, the sunset terminator was around the England, say, western coast of Europe. So here we had the sunset terminator, and here we had the solar eclipse. So at the end phase, both solar eclipse shadow and the sunset terminator kind of elongated the channel where a weakened ionosphere can be over a much longer region. So that's why for momentarily 7 megahertz got opened much earlier. So physically, now we understand what happened. Now, what I'm trying to summarize through one was 2017 and 24 difference. Ham radio data was really good in capturing the solar cycle difference. 2, when we had a detailed study, it really proved to be a good tool to test real state of the models like Symmetry or Vacamax Symmetry, and prove that the one which is more physics-based gives a better result. 3, it also gives a physical kind of consistency in terms of what was happening when the sunset terminator and the eclipse came together, a much longer elongated plane. So these kind of studies really help us examine what was happening in terms of the radio propagation and in terms of the ionospheric density changes. And as I said, this all is possible because of you who participate as a hobbyist, contact, or radio receiver automated networks, ham radio data, or the HamSci group. And these are funded by NSF and NASA and all of you through taxpayers' money. Thank you.
Thank you so much, Kuldeep. It's really exciting to see all those solar eclipse observations turn into actual science. Are there any questions? We have a minute for questions. I know we have to, yes, we have one question over there. Did we study medium wave changes, AM broadcasters?
What is his name?
Yes, we do have an amateur, Nick Hall Patch, who is with our community, and he's done a whole series of observations of medium wave, and he's posted that data to Zenodo, and so we can get you access to some of that. Yes.
I will add one more thing.
And Dartmouth College is looking into it too.
Now that data gives us a challenge and an opportunity also. So all the results which I gave you, the model ionosphere starts from say 100 kilometer onwards, but medium waves are more affected through the D region. So it is kind of a really good way to first attempt to model it, and then also bring out a new kind of radio information in the D region. So medium wave has been tricky. Nick Hallpatch asked me if we can analyze it. It has been tricky, but there is a wealth of information available in it. So if we operate at multiple frequencies, we get lots of information. That's what I'm trying to say.
Last question.
Well, I was just going to say one limitation you got to be aware of with medium wave for AM broadcast stations is some of the stations have to change their antenna patterns, between day and night. So that could affect your ability. So you'd have to know when they are switching their patterns.
Yeah, absolutely.
Yes, that's a very good point. Thank you. All right, everyone. Thank you so much for coming to the HamSci workshop or HamSci forum. Ed asked me to give a quick 5-year vision, I think, and I'm just going to kind of pitch out really quickly. We are really growing a number of different projects. We've got the Solar Eclipse project, which is kind of wrapping up right now. This Meteor Scatter QSO party, we just got it in got through our first year. We're seeing that program grow. We're learning how to better run Meteor Scatter QSO parties, how to better ask better science questions, and analyze the data better. And our personal space weather station project, we're seeing very rapid growth in the development of the hardware and the software, and we're aiming to deploy multiple receivers this summer. And our research assistant, Emma, KD3CKD, she's going to be helping with that this summer. So that's kind of the near term. For the future, I think we're going to keep developing these projects, trying to get more people involved in maturing our science and our practice. So thank you. Please come talk to us at the booth. We'll be here all Hamvention. I hope you have a wonderful day. Gary McKeaton does. He says, I have it. I've got Dave Witten's tag. Okay, but.
Okay, let's make sure I get the. Okay, good. Hello, testing.
I'll figure it out.
You're pretty sure it'll work? You can pull it out real quick and see. Okay. All right, welcome to the Balloon Sat Forum 2026. And we have some interesting talks for you. And we're going to be doing some high altitude balloon flights from the food court, probably about 20 or 30 minutes after the forum. We're going to do 2 pico balloon flights, and I'll describe what a pico balloon is for those of you who have never heard or seen of that. And we're taking amateur radio to new heights, and we're talking jet stream and stratosphere. So with that, I'm going to tell you a little bit about the difference. There's 2 types of balloons that we use. Actually, there's 3. One is a regular weather balloon. The latex balloons, they typically go up. The top chart on the upper right shows you the flight profile for a latex weather balloon. You can carry 2 6-pound payloads up to 12 pounds. So lots of sensors, experiments, and cameras, and ham radio experiments. So you can carry a lot with that. The other type that we've been doing for the last few years is a pico balloon, and they're super pressure balloons. Instead of going up and the balloon popping and parachute coming out, which is the typical weather balloon flight, the weather balloon flight takes about an hour and a half to get to altitude. The balloon pops and the parachute comes out, takes about 30 minutes to come down. So it's about a 2.5 hour flight. The pico balloons, they go up, they achieve, if you get the lift just right, and it's pretty critical, if you put too little in, they won't stay up overnight. If you put too much in, they'll pop. So you have to get a little fine range, and it's typically within a gram or 2 of a positive lift. Plus your payloads have to be about a half an ounce. So they're typically, usually totally solar powered. And you see the flight profile down on the bottom right that goes up and it levels out, and it can stay that way for days, weeks, months. And there are several that have been up for 2 or 3 years as they go around the world multiple times. Now there's a group, I've done this years ago, and this is a solar balloon. You know, no helium, hydrogen at all. You just put a black plastic balloon out in a hot sunny day, and it'll take off about 3 ounces or so. And these guys in, that's PU2SWX out of Sao Paulo, Brazil. They've been flying them, and you see the chart right below the map. They go up, they float about 65,000 feet all day long, and they come down at sunset. And they've been flying these radiosonde payloads that we're going to have several discussions on in later talks. And you take a radiosonde, and you can convert it to the 70 centimeter ham bands, and that's what they've been using in Brazil. So they've been having a lot of fun with that, and basically all you need is a lot of black drop cloth and tape it together or heat seal it together, and you've got a really cool balloon that doesn't cost you anything in helium or hydrogen. And helium is pretty expensive nowadays. There are several balloon maps that we use dedicated to ham radio balloons. For the regular pico balloons and the latex balloons, it's called amateur.soundhub.org. And you can see there's at least a dozen to usually about 20 balloons floating around the world. Some of these are the up and down flights, and some of these are the ones that go around the world. And you'll note that there's only a couple in the southern hemisphere. The predominant activity is the United States and Europe. And but some of them do cross over on rare events. And Edge of Space Sciences, they have one called EOSS P-4, and it actually went to the southern hemisphere after circling the northern hemisphere about 10 times. It went clear down to Australia and circled down there for a while. Then it came back and crossed the equator and went back again. Now it's over, I think, South Africa, heading towards Australia again. And that was launched in October. So it's been flying. In fact, they launched 2 in October, and they're both still flying. All of the ones you all flew. This is Jim KC0RPS. He's a member of the EOSS group, Edge of Space Sciences, in Colorado, and he's the one that launched, their group launched those 4 balloons now. Now, if you want to track the radiosondes that the Weather Service and other agencies send up, it's tracker.sondhub.org. And they launch typically twice a day, although I am blessed that I have a site called the Atmospheric Research Monitoring Facility, and they launch 4 a day, just about 30 miles west of me, and certain times of the year, they're dropping all around me. Now, the price of helium is getting exorbitant, so a lot of people have been going to these balloon time tanks. They're about 14 cubic foot. You can get them at Walmart. Don't use it. They're 80% helium now. They market it as an environmentally friendly mix, but they're basically selling you 20% air. So I found on Amazon, for the same price, about $50, this Party Factory. Make sure it says made in Germany. But on Amazon, order that, and it's 99.9% pure. I've actually measured it, and they lived up to their advertising. And this is a really lightweight canister. I have 2 of them over there in the corner. And after the forum, we're going to be using one of these canisters to inflate the balloons. You can get about probably 4 to 5 balloons inflated with just one tank. If you try and buy a big 200, 300 cubic foot tank of helium, it'll cost you about $400 nowadays. Now, a lot of people are going to hydrogen, which is under $100 for a big tank. So if you're flying latex balloons, I highly recommend flying hydrogen. And don't worry, it's pretty safe. Just don't rub a cat and then touch the balloon or smoke, and you'll be okay. If you're in a low humidity environment, you'll have to take a little precautions not to generate any static electricity. But for the most part, hydrogen is very safe. It's just when it mixes with oxygen that you have the issue. And the Hindenburg, that won't happen because the Hindenburg was coated with gun cotton, and that's what caused the big flames on the Hindenburg. So last year, 2 years ago, we had a balloon race, 2 pico balloons, And we launched them from the food court, which is what we're going to do this year. And it was fairly light winds. We had 2 students launching them. The fellow on the left, that was W8BI-11. His made it to Africa. And the other one, let's see, yeah, Israel. And we think it might have got shot down by the Israelis because they were having the Gaza war at that time. Dash 12 went around the world 1.99 times and came down in Kansas somewhere. But that was an amazing flight. And I think if I hit the right button, there should be Now that's ideally how they should go. Oh, you're all getting audio okay on that video clip? Now, last year we did the same thing. Jim, KC0RPS, and KD8PCU, Ken Piper, launched in a 15 to 30 mile an hour wind. Now, I also always say that when you're flying these little pico balloons, if your hat blows off your head, don't fly. Well, our hats, we had to bolt them down. It was very windy that day, but we flew them anyway, so you'll see the results of that. W8BI-11 came down in the Atlantic, and Dash 12 ended up on a mountain. It hit a storm in Pennsylvania and landed on a mountain and transmitted every sunny day until October, 5 months. There was a group in Pennsylvania that was going to go out and get it, but they never did. So we've actually had one that was launched from Salt Lake City that came down in Glenwood, Colorado. And here's a challenge for the Edge of Space Sciences guys. It's still transmitting after 3 years. It didn't transmit all winter. When the snow melted off, it started transmitting again when it's sunny in western Colorado. And it's KG7KYW-1, I believe. If you look it up on APRS-FI or that amateurscientihub.org, you'll probably see it pop up from time to time. So here's what it's like to launch way over the wind limit. 5, 4, 3, 2, 1. It's supposed to go up, not horizontal. I didn't know you could run that fast, Jim. We bounced off of several golf carts, a picnic table. I think we hit somebody's hat and bounced off the building, but they continued to fly. And they actually, like I say, one made it to the Atlantic and one got hit by a storm. Because typically the weather is really bad at the Dayton Hamvention for launching these things. And there's usually all kinds of thunderstorms in the area. But today looks actually fairly decent. It's pretty windy, but I think we'll be able to get them off the ground. It's a little too cloudy than I like because it doesn't take much moisture to compensate for 5 grams of positive lift. The youth rally, the ARRL youth rally, we launched W1AW-11 from on Sunday of Hamvention last year. And this fellow's 9 years old. And that balloon went all the way to Japan. We did something kind of unusual. My good friend Greg, KF4ZTI, has been flying balloons for years. And his dream, ultimate dream, was to launch a balloon around the world. He tried multiple times. They all kept coming down before they achieved the goal. Unfortunately, he passed away. So what we did was we took a little baggie of his ashes, about 0.35 grams. We stuck it on one of these pico balloons and launched it as a memorial. and it went around the world twice. So we sent him around the world. Now I'm going to talk a little bit about student programs, because the best way to bring in new amateur radio operators is to inspire them. And one of the great ways of doing that is through using ham radio and high altitude balloons. So University of Alabama, Huntsville, and I'm their mentor to this club. It's called the Space Hardware Club. They do rocketry, robotics, they're building a satellite they're going to send into space in about 2 years. And they have a big balloon sat program. They also have an outreach program where they go out to the local high schools and middle schools and launch balloons and send up experiments for the students. They have 3 big programs going on right now: Havoc, Luma, and Pascal. This is the Havoc, stands for High Altitude Visual Orientation Control. They actually use gas jets with a big CO2 canister, and they've got moment arms. They have the gas jets going either direction, and they can point in any direction during a flight, because if you've noticed, those of you who've done camera payloads, the spinning is crazy. They can rock solid point it in a direction and keep it there the whole way up and down until they run out of CO2. But they got like a pellet gun CO2 canister, and that usually is enough for an entire flight. And you can see that one picture in the bottom right, you can actually see one of the jets in the view, and on the upper left, you can see the moment R and the 2 jets on either side. Now, a simple way of achieving fairly close to this is to just put drag elements on the end of carbon fiber poles, and it's like a tightrope walker effect, and that'll stabilize it quite a bit by doing that too. Edge of Space Sciences, I think yours is about a foot or 2 on either side on your camera payload. I put them out about 3 or 4 feet, and it really stabilizes it, but it adds more weight. But yours works great too. It's important to put little drag elements on the end. I put little styrofoam balls on mine. This is Luma, Long Range Universal Mission Administrator. These students have a future at NASA and the Army, because they love acronyms in those government agencies, and they're very good at it. So this one is a cut-down mechanism and a long-range data platform, and they have 2-way control of this platform, and they can vent the helium to level it off for a long-duration latex balloon flight. And then when they're done, they hit a cut down, and it separates from the nozzle and comes down. And they have one more program, and it's called Pascal. And this is a great acronym. Let's see: Payload for Atmospheric Sampling and Chemical Analysis from Lightning. So they send up an air sampling payload and various other sensors to detect lightning electromagnetic fields. And they bring these air samples back to Earth to study the internal workings of a thunderstorm. And it's exciting for them. If you like storm chasing, they send these balloons right into severe weather. And they did one in the eye wall of a hurricane in New Orleans. And I saw the APRS readout right after they launched it. The video was they took it out of the van, and it went whoosh. It was reading 80 miles an hour on the ground right after they launched it. So they do some really exciting things with this club, but there's well over 100 members from all disciplines, and almost all of them have a ham radio license, and everybody on the balloon sat team has a ham radio license, which they got so they can operate all the equipment. We did this is an example of an outreach STEM project to really get the word out about amateur radio through high altitude balloons. This is the Inglewood Amateur Radio Society, called EARS. And they teamed up with an appropriately named Sky Academy, the 8th grade STEM class in Englewood, Florida. And Mark, K9SCX, he was instrumental in helping. He's a member of the Ears Club. And they loved it. They had a great time. And this is the launch. Now, Florida has a really strange balloon ban law. If you are not a government agency, you cannot launch a balloon without getting fined for littering. It's a $250 fine. So there is one strange exemption, and that is if you are 6 years or younger, you are exempt from the law. So one of the members brought out his 6-year-old I guess they're twins, 6-year-old granddaughters, and they launched the balloon to get around the law. But if you're concerned, if you're from Florida or from a state that is banning balloons, the NOAA High Split organization uses our pico balloon wind data, particularly over areas like Mongolia and those regions where there's very few wind sample data. And they use our data to refine their wind models. And so technically we are a government-sponsored agency. So you can get around the law that way. That particular flight was launched in February. It's still flying today and has been around the world 5 times. This is a cool website that has a nice chart function. It's called whispertv.com. And the flight is N4EAR-1. Now I'll give you 2 examples of some interesting ham radio payloads you can fly. This is a crossband repeater. You can actually cover 400 miles in all directions line of sight when you're at altitude about around 100,000 feet. This is a Radtel 888G. And it's a simple menu command to just set it up. You set your frequencies one for UHF and one for VHF. You hit the menu button for crossband repeat, and you've got a crossband repeater. I would set it for low power. You don't need much power. This can do 10 watts, but it'd probably melt in the stratosphere if you did that. But there's a real simple idea. That radio costs about $80 on Amazon. The other thing you can do is take a $30 radio like this Quanchang here. That's a $30 radio. Set it up on a simplex frequency and use this simplex repeater from Argent Data Systems. And it has all kinds of bells and whistles for CWIDs and little tones it plays. And I typically set them up for 20 seconds receive, and then it transmits for 20 seconds. Once you get used to that pattern, and there's a little beep tone at the end, sounds like a NASA mission. This is a really simple way to send up a voice repeater that can allow people over a 12-state area from 400 miles in all directions. 2 people 800 miles apart can use the balloon as a repeater and talk to each other using just handhelds. For ground stations, this is an example of the NA6D sound card HT interface for Baofangs and Quanchangs and any really radio that uses 2 jacks. It's a really cool little sound card. Plus it operates as a programmer digital for if you want to program channels and things. Really handy. It's very inexpensive. It's about 30 or 40 bucks. And he ships it right out the same day. And it's a sound card interface. You just plug that into your computer, into any program you want to use to decode data. It's great for APRS or any of these new digital modes. The free payloads are falling from the sky all around us. And the next 2 talks, we're going to be talking about how to find these and how to reprogram them to the amateur radio frequencies, typically in the 70 centimeter band. That's Bev, WB4ELK, and she had a ball chasing these. She was really into geocaching, But this is like the ultimate geocache because you really don't know where they're going to land until they've landed. Now, I use this really cool device called the LilyGo. There's an app that you can program into it called the MySondy Go, and it's got a phone app, and the little ESP32 computer has a radio in it, and you just carry that with you, and it links through Bluetooth to your phone, and you can walk right to these radiosondes and pick them up. And that's a picture of the internal workings of the MySondy Go. It's a LilyGo, and they're probably about 20 bucks. Finally, I'm going to talk about the Great Plains Super Launch. We've got a conference in the middle of June in Pella, Iowa. Superlaunch.org to sign up for it. And if you want to go to an all-day conference about high-altitude ballooning, payload design, and balloon techniques, we also have a multi-launch on Saturday, and we launch typically 10 balloons and a lot of Pico balloons, and we chase them all over the Iowa cornfields. So it's a lot of fun. Now, as we are flying over Iran quite a bit and over Israel and Ukraine, there's a lot of worry about them being shot down on these Pico balloons. And it's very expensive. I know the U.S. military has stopped shooting ours down. They have shot them down. It costs $500,000 for each missile they fire at our little Pico balloons. I have a top secret slide. I probably shouldn't share it with you, but they came up with a new cost-effective way of knocking our balloons out of the sky with their fighter jets. With that, any questions? And I'm going to turn it over to Tom Graham, WX8TOM, and he's going to talk about payloads in the sky. Yes? They said what now? Okay. So they are aware of it. Good. So they aren't going to shoot ours down today. Any other questions out there? Yes. I'll get on the micro. Pico balloons at group.io. Groups.io. Is it Pico balloon or Pico balloons? I think it's just Pico balloon at groups.io. And then there's a, what's the GPSL at groups.io? It's GPSL at groups.io. That's for general ballooning. Okay, with that, I probably better go on to the next talk. So Tom Graham, WX8TOM from Lima, Ohio, will be our next speaker. No S, it's Pico balloon at groups.io.
Set it there.
Cross your fingers. We hope this works. Well, no. We're out here. It's already on. It's saying it's there. Tested this morning. It worked. Huh? You want to transfer the thumb drive? You can always do that. USB-C, USB, you can do that. Technical difficulties. I'll have her start passing some stuff around real quick. Because I've seen you talk. Yeah. Go back to display. So you got yours on the Mac too then. There was something came up. That's not me though. I'll let you look. I'm not seeing this.
While we're figuring that out, let's go around the room and who has ever flown a high altitude balloon or is with a group that has? So we'll start down here if anybody wants to introduce where you're from and did you get it work?
Yeah.
Okay. Well, we'll do that later.
Okay, we got that fixed. My name's Tom. I'm from the Northwest Ohio Amateur Radio Club in Lima, Ohio. I've been doing this about 2 or 3 years now. Somebody asked earlier where you start. I started by a lot of reading, and then one of my buddies got me in contact with Bill. And I've had a few successful launches we'll talk about and how to track. And I'll probably cut out a few slides for time this morning, but I think you'll like this. We talk about the different launches. This was a launch I did. If it's going to work, we might have to skip that one. Bill showed some videos of launching in high winds. I've done some at night and in high wind. And we had one that my first successful flight across the Atlantic was with a battery operated Tracheto is what I used. And I happen to have one here now that's solar powered. My wife down here, WX8MOM, will be passing some of these around. But this is one of them I built that finally, this was one of them. This model here was one of the first ones I had that went around the world. And that flight, that one that was operated, everything was done wrong. It was underpowered. It was flown in high wind. I thought I ripped it when it took off. Bill called me about 3 days later and told me it landed in Sweden. So I was like, okay, we didn't even do anything right. We got one to do. This has to be able to be done. And I did a lot of things in one of my other talks where we showed how with the Tracheto in particular, they have you build a solar site out of some fine, very thin solar cells that break very easy. I ended up going with these flexible ones over time. These are much easier. It was a lot of work to put those together and then just have them break right when you're getting ready to launch them. One of the things I think is very important to talk about is the atmosphere when we raise these. Right now on us, there's probably about 14 pounds of air pushing down on us. That's just the weight of their atmosphere. It's also a reasonable temperature down here. When these balloons are flying, they're going to get out of the troposphere. That's where we spend, or most of us spend our entire lives. If you look over there at the one slide, I'm not sure which one's easier to point at, maybe this one. You can see the pico balloons are going to fly just a little bit above that airplane between 10 and 15. The weather balloons, you see where they fly that the Weather Service uses. When we launch these high altitude balloons, they're going to go on beyond, they'd be off that screen if it was to scale. So they're getting way up there. We had one that hit, I think, 20 miles, give or take. So these little devices, they're unprotected, as you can see when we launch them. But they're putting up with that temperature, they're putting up with the pressure, they handle it all just fine. And as Bill was describing there, he has one that they was talking about thawed out in the spring and still was working. I'll keep it quick on this slide since I believe most of the people in this room are hams, I suppose. But we've all seen this when we study for our exams, I'm sure. All you really need to remember here is UHF and VHF want a straight line. And as you heard him say a minute ago, the transmission power, it doesn't need to be that great when they get high. So some of these we're sending out at very low power. So this one's about HF, also from the book when we study. I like to watch the 20-meter taquitos. Bill also has a device that can send HF as well. But the nice thing about HF is for getting better data resolution, at least when you're over the ocean. With APRS and anything you're using, VHF or UHF, when you get out over the ocean, you're not going to hear from the device for a little while. And if you want to know where it is, I mean, you can wait. You have to be patient with some of these. But when you send the HF ones, if they're working correctly, if there's sunlight out, you're going to hear a transmission from them here and there. And one of the things that was most fascinating to me when I got started was in December of I believe it was 2023 or 2024 maybe. We put one on the ground. It was all spread out, a Torquedo, 16-foot dipole on it each direction. And I turned it on, just was making sure everything was working, that I could pick it up locally. And it actually got picked up in Denver, Colorado, from my backyard in Ohio on the ground. We're talking, what, less than 500 milliwatts of power. So when you crank the stuff up to 100 watts, you don't always need it, I guess, is the lesson there. We talked about a couple different times. The biggest thing here is just the types of payloads you can put on picos versus high altitudes. A pico balloon is going to be small, usually less than a couple of quarters in change, in weight. And that's really all we put on them is just the tracker itself. The distance of those can go around the world, though, several times. I have one in the air right now that's beginning its 10th trip, and Bill launched this one for me during a conference I had in Sandusky, and I got one of my friends from Sandusky up here today, I see. That balloon has just kept going, and what's interesting to see, you get your money's worth out of certain balloons, and other ones, they just come down. Tracking here is Whisper and APRS. How many people have heard of Whisper in here before? Okay, we got hams, they should know. When I first was reading them and studying for my books, I'll never use this, but I do. And it's one of those digital modes that I don't know how well it works the way it does. The only real drawback I see it has is that it's a 2-minute transmission. And if you're underpowered, that's going to be a problem for us. The next one is a high altitude. So you can see it's double the height easily of these other ones. And the payloads, I put 1,000 grams. You could put, what do you say, 4 or 6 pounds. There's some FAA rules, I believe, on that of how big they can be per square inch. But most of the time, you're not going to put anything that big on there. I've only launched trackers so far into high altitude. This spring, I'd like to put maybe a Mesh-tastic repeater on one to see what distance we could talk across the country on that, maybe a camera and see some other things like that. And with some of the people that are talking today, they'll help us. And if any of you are wanting to learn about these, just reach out, and I'm sure any of us will be glad to help. Next, I'm going to talk about a few of these devices. You want to start passing those around, or are they going already? I'm going to start with the Cadillac first. So if we put these in form, hope you don't drive a Dodge or a car, because I'm going to talk about these in that form. But the WBLK Sky Tracker, that would be the Cadillac of all of them. It's not cheap, but it'll work, and it works well. And it's one of them. It's up in the air. It's been floating now for, like I said, 4 months, working just fine. I've not had that kind of success with the Torquedo, but I have had success with the Torquedo. There's a little bit of difference in these two. The Torquedo is one, if you want to build something yourself, it's a great device. You order parts online, and they'll send you that circuit board you see that looks, I don't know, like a robot. They'll send you that circuit board with the components on it after you order it, and you can order that from just text files. And then the other piece is just a plain old Raspberry Pi. And you solder the two together, you put a program in it, you put your call signs in it, and you launch it. And it works well, too. It's a power hog. Right now at home, I'm working on seeing if I can reduce the power usage. I'm a programmer as well, and I've not had a lot of success with that. I actually did something I thought should have reduced power, and it made it use more. And then the last one is the U4B. I'm not going to insult this guy. So the Trakita would probably be your Dodge or Chevy, and I'm going to say the U4B. I think it's the Lakar. It does not get a good GPS pickup, and it's not a fault of the device itself. I think it's just the components that are on it may be older. Bills and the Trakita, if you get them anywhere near with a short, small antenna, if you're seeing that passed around, the antenna only has to be about that big, and it's picking up a signal. So there is a new U4B with a good GPS on it now. Okay, so there's a new one. I might give that one a try because I've had a lot of trouble with the old one. And that group is very helpful. When I called them up, they told me all kinds of things I could do to make it work. So they do support the stuff they sell. And, you know, components do change over time. So the high altitude balloons, what you can do with these. So if you can think of something you want to put up there in the air, you could probably do it. I know there's some experiments where I've seen put marshmallows with cameras so you can see the marshmallow expand at the low pressure. I've seen different radios, repeaters. Bill went over some of these. And, you know, I believe there's some live TV that people have done. Andrew might have even been one that has done that before, and I don't know if he'll talk about that today or not. So what is a radio sonde? I have one running right here, down here, and there's also one passing around. It's in the foam case. Michelle, would you like to hold that up? It's on right now. It's flashing. It's sending out signal. So if you had a way to pick up that signal in here, you would be hearing it. And this is what I'll probably turn this back on in a minute, but that's Horus. That's a digital mode. I'm sure you can hear that. It's loud up here. We can decode this even on a phone. You can actually plug this into a computer and have it decode using the Horus app. It's also sending out CW. Not doing great inside the building. That same device is sending out APRS. I won't put that on right now, but I have a radio with APRS tune. So we're sending out 3 different signals on that. One of the great things with these is the high resolution data, but you might ask, what are these used for initially? And as I said, there's 100 or so of these falling out of the sky every day. Anybody know what this is? Okay, I storm chase a lot with my kids. And I learned to read these. They're not that hard to read once you do, but this is a sounding. I don't believe this was before the tornado went through Mayfield, Kentucky, but afterwards. So a radio sonde actually measures parcels of air, and that could be a parcel 20 miles wide or a parcel 150 miles wide. It's just wherever it goes. And you'll see as you go up that right side of that chart on the left, that is the wind speed all the way up into the atmosphere till it pops. It's going to show the speed the wind is. It's going to show the humidity, the dew point, the temperature. All that stuff can be used then to model from there and predict weather. And we use these to storm chase all the time. This one is afterwards. If this would have been before, you would have seen that Cape line, which is the dash line, been much wider on there for that evening. So that's their first use. And the Weather Service doesn't want these back after they're done. I can probably skip that next one. Bill talked on these briefly. I won't go into a lot of detail. I'll see if the site will open for me and show up on screen. I don't know how well you can see that, but right there, that's WX8TOM. It was over China yesterday or the day before. I'm expecting to see it in the U.S. I was really hoping it would be sending us some live data today during the talk. When I was in Florida speaking on these, I was fortunate enough to have it flying very near Florida that day, so that was pretty special to see data coming in while you're talking. It just flew over Disney on this last trip, though, so it got a free trip to Disney. I don't know if I can get that off there easy now. Anybody see the mouse? Come on. Well, already talked about all the balloons in the air, so I'm going to skip over that. This is a prediction, so we can predict where these balloons are going to fly before they ever launch. And you can see that one right there would go into West Virginia if it was launched yesterday. If I click that today, I think with the weather pattern that's flying over us today or up in the sky above us today, I think it would only go about 20 miles from here. I can't really see the screen well to show you that, but the links, these slides are available on GitHub, and if you take a picture of the thing at the end of here, you can do that. But you can see this will tell us where it's going to go. The other nice thing is once we launch these balloons, it'll continue to tell us where it's going to go as it's in the air. Need my mouse back, guys. There we go. So there again, that's a picture of Bill's device. Again, I can recommend that one to everyone. He actually has kits, I believe, that are ready to go. And if you want to launch one of these, all you got to do is come up with the helium, and I believe his kit even comes maybe with the balloon. But I've launched one. He launched one of these for me as well. You might ask how the data gets to the internet. Being a developer, I always care about this part of it. So I call this an IoT device. What it's really doing is we're putting data into the internet from an external device. So we have there the balloon. It's our telemetry device. That could be a sensor of any kind, but we're pushing this data from that into an SDR or a radio, such as this. You can hook one of these right in and decode it. We demodulate just as we learned about radio initially, and then we have a decoder. So WJSTX, if you're using FT8, you can use that. DARA if you're using APRS. And on the APRS, we use a 70 centimeter band when we're doing it on these. And then the other piece is you can also use it with Horus. And Horus has its own app, and there's also a phone app I'm going to show in a moment. I heard Bill mention this radio, and I just had it on a minute ago. What's nice about this radio is it's one of the most hackable radios out there. It's about a $30 radio, I believe, anywhere from $20 to $30. You can flash it with your own software that they have online. All you need is a cable to do it. And I think the cable came with it when I bought it. What this allows is this radio can now do sideband. So you don't have to have an expensive radio to do sideband, and that is what Horus is being transmitted on. You can also plug into this device and shove that right into your computer with a sound card and run it right through the Horus app there, or hold up a phone and use your phone with it. And we're going to show that app. If anybody wants to click on that QR code, tell me if somebody gets it open. Michelle, carry this phone down to him. I'll keep talking for a second while she's walking over there. Right over here, Michelle, the guy in the yellow. Hold your phone up to that. It should actually, did it decode already? Hit start. I'll move on while we're talking about that. But what that's going to do is decode. And I believe, if Andrew, correct me if I'm wrong, doesn't that actually record that? Yeah. So that'll shove that up to the internet too. So if it decodes, and you should have got something that says one of our call signs. I think that one is probably my daughter's call sign. Did it decode? Okay. So it just worked on his. That's an app you can have and use if you're out here working with any of these balloons. I use that when we're getting ready to launch to make sure the balloon's transmitting. I also have a setup in my car that goes ahead and allows us to I have a Starlink and a SDR hooked up to an antenna that pushes everything in. I'll make this slide quick. It's just RTL SDR. I hope everybody knows what these are. I need to save some time here, I think. And one thing, if you use Windows, I recommend Linux or a Mac for ham work. Everything is easier on a Mac or Linux for this. If you're using Windows, you'll want that VB audio cable at the top. That's probably the most important one. The rest of them you can all find online. That will allow you to pull sound from any device and shove it into the device you want it to go into. It's like a patch cable, except it's a virtual cable. And that's mainly for Windows users. I've never needed to use that on any of my other computers. This is our launch. I'm not going to probably play the video to save time because it's a couple minutes, but this was our very first launch. And if you look out there, starting on that far left side of the picture, that's me. And then the next person is WX4 GPS, one of my buddies from Lexington, Kentucky. Unfortunately, he's not here today. He'll be here tomorrow. And he's very into the balloons as well. And then that's my daughter, WX8 NRD. My whole family is hams. And then, so I got lucky. I forced a habit on them so I could spend more money. The next one in line is my daughter, Elizabeth. She's the one launching the balloon today. This was her 4-H project, and she went to state this year at Ohio State with this project, so we got the word out. But we did very well. This balloon went to 107,000 feet. I'll show that picture in a minute. I got to slide out of order here. One of the things we can do with balloons, and this was, I believe, Bill's idea or Finley's Club, but they got a hold of me last late August, I believe it was. In Findlay, Ohio, they're a balloon fest every year for hot air balloons. It's worth seeing if you've never been up there. But we decided we was going to put on one of these radio sondes onto there. You had to do a couple settings different on the application there on the Sonde Hub to make it work, to tell it was a low altitude balloon. But this is a graph that Bill actually put together, and you can see, first thing I would like to point out is the high resolution data on there. Look at all the data points we have. You couldn't do that with Whisper. That whole flight might have been 5 or 6 points with the Whisper returning it. But this is Horus. It's blasting 10 times, maybe a minute. Yeah, every 3 seconds we're getting data from that. So, oops. We're getting a lot of data we can work with. And you can see the height of it, the distance it went. Very neat piece of data there. And I'm not sure how he did this graphic, but I probably need to talk to him because I think this would be nice to do with other work. Google Earth did that. Next is tracking and recovery. And I have to mention, I believe it's Mark and his daughter Myra, Zach and Myra. Zach actually helped me get my first balloon filled up for high altitude balloons. And I just went out there. So to give you an idea of cost, launching some of these balloons can range anywhere from $50 to $100. A high altitude balloon is going to cost more than that. The balloon itself can range anywhere from $50 to $100 or more, depending on what size balloon you're using. But you're putting a little bit of money up there, so you want it to work right, and you want the payload to go up with it. I've learned to tie really good knots. I have launched stuff that the balloon went up and the device hasn't. I think anybody who's done this has. You forget something. It's frustrating because the balloon itself is expensive. The payload, you're going to retrieve all of them, so that's not a big deal. But on there, on that little slide there, that is the track. You can see as we was watching it as it flew, we know when it's going to pop. We know where it's going to start coming down. And I will be honest, it seems like these things might be a magnet for water, or the water's a magnet for them. It seems like they like to go into swampy areas, it looks like. And I'll tell a story from last year at the Great Plains Super Launch. I watched several people who are really smart drive into places they shouldn't and get stuck. But it's fun. It was fun. The chase is more fun than I thought it would be too. Okay, 3 minutes? I'm about done. This is something else I want to work on. I've actually forked a piece of Meshtastic. I would like to work on something with the balloons to get the balloons to work correctly. And one of the things that we have on some of the GPS, I believe, is they level out around 60,000 feet, and they don't really want to work above that. You can force a setting on them, but Meshtastic, if the device shuts off, which can happen on a solar-powered item, I'm trying to figure if we can do something in there to have a setting that would maybe keep that on for us. And I like playing with code when I have spare time. I haven't had a lot of spare time this last couple of months, but when I get time, I'm going to work on some of these items. There's a resource page. I'm going to go ahead and ask you if there's questions with what I had to wait till Andrew's done just to make sure he can get through his this morning. But I have all this stuff out on GitHub. The one thing I will ask you on this page, if everybody takes a picture of that, that'll take you to a link tree. If you go to GitLab, I have all my talks out there on GitLab with the slides at least. You can get a hold of me anytime, and there's a lot of good information out there on how to start. I got a really nice one from the very first time I figured out how to do the Tracheto from scratch. And if you're in engineering at all, you learn that failure is a good thing, and I try to teach that to kids. One other thing I want to say is, like, I'm available if you're from Ohio or one of the surrounding states. You ever want somebody to come and help with one of these, I'll help. I've been up to Code Mash in Finley. I've got, from our talks, I think it was 3 or 4 people have decided to become hams just doing that. And that's the point of all this. And these are adults. So we got some programmers, very tech people that we're trying to pull in. I've got a fellow back here in the back. I think he's interested in balloons. He was already a ham, but it's a good way to show people there's more than just talking on a radio. And with that, I'm going to go ahead and hand it off to Andrew. What's that? Oh, yeah, if you click on that, you'll get the whole slideshow, but I could take it back one if you want a picture of it.
Oh, probably down on the floor then. He's got his own laptop too. Ready? He's going to do the same thing. All right. Thanks, Tom. And the next speaker is Andrew Koenig, KE5GDB, and he's going to talk to you about free payloads falling from the sky and other things.
Yes.
What's the name of your group again?
The Richardson Area Balloonatics.
From Richardson, Texas.
From Richardson, Texas. Okay. Do we have slides? Do we have audio? Can y'all hear me? Awesome. So, free payloads falling from the sky, and this is going to be a look at radiosondes, horse telemetry, and then I also threw in some details on WENET. WENET is a digital image mode that was briefly touched on, but I've got a couple more slides on that. And at the very end of this talk, I do have a QR code to the entire slide deck. It does pain me to watch y'all a bunch of old guys like, oh, you know. So I've got that QR code at the end, so I can only look at that once. But anyway, my name's Andrew Koenig, KE5GDB. I was first licensed in 2005 in Houston, Texas. I currently live in the DFW area. There's a lot of small cities around Dallas and Fort Worth, and our particular city that we live in is Richardson. And so I'm involved with the Richardson Area Balloonatics. I claim to be the ringleader, but we're not really that organized. And we manage to get about 15 things in the air per year, sometimes with payloads, sometimes without payloads. We've had incidents before and, you know, things happen. So a quick overview. What I'll be talking about today, radiosondes, who, what, and where, the process of receiving them, recovering them, and reusing them, techniques for collecting them without getting shot. Depending on where you live in this country, that matters more than other places. Texas is a particular hotbed for possibly getting shot if you're not supposed to be somewhere. Hacking and reprogramming them for productive amateur use, and then some of the Project Horse telemetry protocols. So what is a radiosonde? Tom did a good job of covering this, but we'll quickly run through my slides on this. It's a radio probe. Sonde is a French word that generally means probe. They are small disposable weather instruments, and there's a tray being passed around with a handful of flavors of radiosondes. Those ones I have either recovered in a field, in a tree, or maybe on eBay. The one that's in the bag definitely came from eBay. Got a couple more up here, but yeah, this one shown is a Vaisala RS92. This one's generally not flown anymore, but it's very interesting because it's got this helical GPS antenna on it. I really like that. It's just different. This was before the little chip-style GPS antennas were made popular. The sensors that they typically carry are going to be temperature, humidity, and a GPS. Some of them will carry a pressure sensor, but your wind data is easily derived from your GPS data. Pressure is optional as well. If you've got a good pressure measurement from the ground, there's no need to measure pressure as you ascend in altitude. That can all be derived from the GPS data. Typically, they've got a 400 to 406 megahertz transmitter, and that's useful for us. And all the current generation ones have an STM32 microprocessor. We like that as well. It's very easy to hack into. So I'm sure you've heard us talk a lot about SondeHub. This is just a quick view as to what SondeHub can look like in the evening hours when all of the NWS launch sites are actually running with all their stuff in the air. As Tom mentioned, there's about 100 active launch sites here in the US. Some of them are automated launchers. You say what? Talk a little closer. All right. Is that better? All right. There are some automated launch sites. It's actually really neat. They're like 20-foot, sometimes even larger shipping containers. They've got this dome on the side that opens up and spits out a latex balloon twice a day. The nearest one to me is in Del Rio, on the southern border, but there are 2 or 3 of them around the states. A lot of the sites changed their schedule due to Doge. There were some staffing impacts at the NWS, and because of that, they shifted from their early morning launch at 1200 UTC. From their early morning launch at 1200 UTC to a midday launch. But typically all the launch sites do run in the evening at 0 UTC. U.S. radiosonde types. The NWS launches the Vaisala RS-41 and the GRA DFM-17. Those are the most common ones that you'll collect. Universities love the IMET-4, and on this little lid that's being passed around with the sondes, the one that's got the handwritten note on it came from Texas A&M. The Aggies aren't really good enough to figure out how to print a label or write legibly, so we got that out of them. The IMET-4 is generally the only radiosonde that's regarded as trash before it's launched. A lot of them are considered to be that once they land. We collect them anyway, but the IMET-4 is just not a great unit. It also runs AFSK, and if it were the 70s and that were bleeding edge, that would be great, but these days there are so many better modulation schemes that are much more efficient and much easier to receive down in the noise. And the rare bird, I didn't even bring this one in because it's so rare, the Lockheed LMS-6. Generally, you only see that guy launched around like Cape Canaveral or sometimes on the West Coast near Vandenberg for various launches, rocket launches. Receiving radiosonde data, we saw the little MySonde Go device. I personally don't run the MySonde Go firmware. Well, that's nice. Man, I'll try and push through, but work with me if I get tripped up by our new lighting effects here. I run software called RDZ TT Go Sonde. It's open source. MySonde Go is not open source, so I do have a bias towards this. But most importantly, the first bullet point here, and this is the one I recommend everybody run if you get a chance, Radiosonde Auto RX. Okay, it runs on a Raspberry Pi, and at a bare minimum, you need an RTL SDR. So a single RTL SDR, a Pi 3 or newer will work best. And you can do a lot with it. It receives all of the radiosonde types that are known to be decodable by us. Ooh, find it there? Almost? I'll take it. That's good. That's good. The coolest development here in the past 18 months or so is a piece of software called KA9Q Radio. And Phil Karn, is Phil in the room by chance? Phil, I want to talk to you afterwards. KA9Q Radio. So Phil wrote this wonderful piece of software, and you've been working on it for probably, what, 5 or 6 years now? Maybe longer. But recently, Mark, VK5QI, with some of my assistance, just a little bit. I can't claim any more than like 1 commit, but we managed to get that implemented into Radiosonde Auto RX, and you can run a multi-slice receiver and receive as many radiosondes as are viable in the bandwidth of your SDR. So with like a Hydra SDR, that's got a real-time bandwidth of, I believe, 10 megahertz. So you can receive any number of radiosondes in that bandwidth. And on some of the rooftops in the Metroplex, I can receive probably about 15 radiosondes simultaneously all across the southern US. So this software works very, very well to glue that all together and allow us to receive many things at the same time. One final note here, a piece of software called ChaseMapper. ChaseMapper is very similar to SondeHub, but it runs locally on your devices. So if you're out in the boonies and don't have cell reception, but still want, lush maps, ChaseMapper is the way. Actually collecting them. SondeHub.org will do real-time predictions. This is great. It uses GFS model data from the NOAA models. Uh-oh, we're back. the predictions are generally pretty accurate. It will give you at least, at burst, it'll give you the right county to drive to. A little while after burst, once it can kind of figure out some of the ascent rates or descent rates, it'll get you in the right zip code. And generally, if you've got a packet that's, say a kilometer above ground level, it'll get you within the right, 100-meter radius area that you need to be looking for the landed device. There's two things here, two pictures. One of these is very high up. The top image, you can see that it's quite a ways out. That last packet was probably about 2 kilometers up, and you can see based on the size of that road that there's quite a distance from the predicted or the last packet where the balloon is to. Let's see. Let me see if I can get the laser pointer going here. So yeah, the last packet where the balloon is right there to the predicted landing spot. Now, if you get a last packet that's closer to the ground, like this, that prediction is measured in just a couple of feet. It's great. So the last packet, we really look for the altitude, the final altitude that we received, on descent, and we look at the velocities, horizontal and vertical. And that's what really drives this prediction and just gut instinct on how to collect things. There is something that should be noted, and that's the special gravitational pull of trees and water. Okay, I don't know how this happens, but let's say you've got an area of North Texas, we'll say representative of the size of this room, right? And say there's like a string just running front to back down this room, right? And that's a creek or a river or something like that. You could have this whole space, right? But you know where my balloon's gonna go? It's gonna head straight for that string. That's just the narrowest thing, and it's amazing. It happens every time. One other thing to note with planning all this is something called the burst timer. The Vaisala radiosondes will turn off 8 hours after burst. Most of them that are launched in the US are configured for this. So when you're trying to go grab that last packet, even if you don't have your boots on and can't hike and grab the device, be mindful of that 8-hour timer. And that's from the time the balloon bursts. If that's not configured, you've got about 24 hours to actually go collect it before the battery dies. So the actual steps I follow. Step 1, turn on your chase car on SONTUB. This is so I don't shoot you. This isn't a property owner thing. This is so I don't come after you. Because oftentimes we'll get 2 or 3 people chasing the same thing, and nothing's more frustrating than me arriving, finding out that you've already picked it up, but didn't claim it, and I didn't know you were coming, right? But just to be neighborly to everybody in the community, it's best to turn on chase mode so we can all coordinate and get together. And often it works out really well to have 2 or 3 people trying to hunt the same thing. When you actually make contact with a property owner, introduce yourself, but introduce yourself as an enthusiast, not as a government official. I know we've, as ham radio operators, like our yellow safety vests, we like to look a little more official than we are. That's up to you. Me personally, I prefer plain clothes and just, hi, my name's Andrew. I'm a weather balloon enthusiast. One landed back here. It landed in your property. And I like to show them a map of where it landed, and usually they can coordinate that, and they'll even walk back with me and sometimes even drive me back there to collect it. Some of the ranches that devices land on in North Texas can be hundreds of acres. And so they'll be like, yeah, hop in the mule, hop in the truck, let's go pick it up. And typically a firm handshake and a referral to sondhub.org is all it takes to finish that interaction. So the gist of that, don't trespass. In Texas, we do have this weird law where if someone paints a fence post purple, that is the equivalent of them putting up a no trespassing sign. And with Texas laws, that can be an issue. You could get shot. But these steps are what I follow, and not once have I had anybody actually say, no, please leave me alone. They've always been helpful, or maybe not super helpful, but willing to tolerate us while we try and collect our payloads. The picture, wow, how long have I lost video? Okay, I looked over right, yeah, the Nyquist dilemma there. The picture here is my best marathon day of collecting. That was 8 radiosondes that we collected. And I believe there was a hurricane in the Gulf, so they were launching 4 a day out of the Fort Worth office, and we managed to have a really good run there. The image on the left here This one landed in an industrial parking lot. That's Sean, KI5PXG, and one of his daughters. One of the easiest collections you'll ever come across is something like this. The next one down, or the next one over, this radiosonde landed in someone's front lawn. It was partially strung up in a tree, and we just kind of ran in and grabbed it, you know, and ran out. Because the radiosonde was just about on the sidewalk, we didn't really want to wake anybody up. It was after dark. So we went forth with that. And the last one here, it landed on some power lines, and you can see the transmitter hanging right there, that little white dot. But the string is made out of cotton, so typically non-conductive, and as long as it's not wet, there's typically no issues. Reprogramming radiosondes. The hardware you need an ST-Link V2. If you've worked with an STM32 microprocessor, you've probably got one of these. You need a cable. There's this Molex part number that makes it really easy. It's pre-terminated. All you have to do is terminate the other end that goes into the ST-Link. If you're working with a DFM, you're going to have to solder a header on there, but that's okay. That's easy. We know how to do that, right? There's two pieces of software that are worthwhile. There's RS41NG, and that will run the Horus binary modes, APRS, CW, and it's now got a Fox mode. There's also RS41 Fox, and that one is a little older, and it's just for running Foxes. So this traffic cone right here was at one of our field day sites. I think this was 2024, and I actually stuck the radiosonde inside the traffic cone, and that was a Fox. We had placed 4 of these around the field day site and had about 100 finds over the course of the field day weekend. So that was our special activity for that weekend. So anyway, let's talk about Horus binary V3 real quick. It is a 100 baud 4FSK protocol. It typically runs about a 32-byte payload, but version 3 of this has an expansion mechanism where it can run 48 bytes, 64, might even be going up to 128. But your typical data, you know, your latitude, longitude, et cetera, that's all available. It takes about 3.3 seconds per packet to transmit, and it takes about 1 kilohertz of bandwidth. It is forward error corrected, and I've seen the decoder for this receive down negative 11 dB below the noise floor. Now, that SNR value should be taken with a grain of salt, but I've also decoded packets from this half a degree below the horizon with just a standard CX333 fiberglass antenna, right? So this mode does a very good job of receiving in the noise. It doesn't quite approach the WSJT modes, but it's very good. We allege that it has about a 20 dB advantage over 1200 baud AFSK, which is awesome. That's just awesome. We love it. What does that make it? About our 25 milliwatt transmission would be equivalent to a 2.5 watt transmission with that advantage. The only disadvantage, as shown earlier by Tom, is that you need a sideband radio to receive it. The Quancheng, the $30 Quancheng UVK6 is perfect for this though. Receiving it, sideband radio, there are plenty of options. We did the Horus demo a minute ago where you can hold the radio up to a laptop or a phone and receive the packets. Horus GUI, that's what's shown here. This is great for actually running with software on your PC, and it'll support rotator control. It will drive your satellite station for you. If you want to run with a Pi, there's also Horus DMod library. So real quick, a couple notes on SondeHub Amateur. It was designed specifically for high altitude balloon use. This is much better than APRS.FI. There's less clutter and it's just balloon stuff. It's got a great mapping interface, chase car support, the robust telemetry display, the real-time predictions as mentioned, and it will automatically ingest APRS packets. Real quick, I want to click on this link here. This might just break everything. But it does have a very robust plot interface or Grafana instance. Let's see here. Stop extending and we'll just show the entire screen. Okay, so amateur.sondhub.org does also display all of this with ease. In this case, you can see what stations were receiving our payloads. You can see all sorts of telemetry. This is the altitude. Anyway, this is wonderful. They've done an amazing job putting this together, the Project Horse crew. WENET, the next topic of discussion here. So this WENET doesn't involve the radiosondes. This is a new mode, but the whole purpose of WENET is to collect and transmit images via Pi camera. It resizes them, adds overlays, and then we'll send them down. And there's actually a live WENET camera running down here on the table. And I'll display a link here in a second, but the one payload over here with the blue camera shroud is actually sending live images to the internet of us in this room. It does this via a 96 kilobit per second link. It uses a LoRa radio, but we don't run it in LoRa mode. And it needs about 300 kilohertz of bandwidth. This is what the modulation looks like on the waterfall. Here are some images that we've collected from the WENET payloads in real time. These pictures didn't come from devices we even recovered, but this was in real time, digital, no slow scan, or no analog. It was slow scan, but there was no analog in this chain, and we really love how these turned out. These three images all came from launches we attempted into thunderstorms or near thunderstorms. This was probably the best one we've had. This one was about 120,000 feet, and you can clearly see the curvature of the Earth there. Funny story about this image in particular, this post-burst chaos was excessive. And I don't know if you can see down here at the bottom, but we're missing a couple packets right there at the very end. You can see that little gray bar. That's because another payload came up, swung and hit our antenna and broke the SMA connector. So we got most of the image, but we lost it right there at the end. Building your own transmitter, it's not a lot to it. You just need a Raspberry Pi. You need this Pi hat, and there are a number of options for this. You can get it for $30 from Adafruit. You need your Pi camera, a U-Blox GPS, and my personal method is to build all of this into a faucet cover. And I've got those sitting up here, but I'll 3D print a base and then I'll stick a faucet cover on top of it. And that actually works really well. I'll skip through the receiver part here real quick because we're almost out of time. But you do need some gain. That's the gist. Because you're running a 96 kilobit per second link, you do need a lot of gain. The latest versions of this, I'm running a 1-watt radio, but the older versions were only 50 milliwatts. 5 minutes? Understood. Similar to that Horus decoder that Tom showed you a little while ago, there's an equivalent for WENET. And by plugging an RTL SDR dongle into your phone, you can decode this on just your phone. It's amazing, in a web browser. It's absolute magic, and it was implemented by VK3FUR. Real quick, some additional features for WENET. It does upload GPS data. We get once per second GPS updates. It will send images, live images, to ssdv.habhub.org. I've got a QR code with that here in another slide or two. An image is composed of many, many packets, but ssdv.habhub.org will reassemble those. So if there are 10 stations and each one of them receive 10% of the image, but they're unique 10% chunks, you'll get the whole image on the website. And this is particularly useful if you've got geographic diversity in your receivers and the payload is swinging, right? Because as much as we'd like an ideal antenna that's omnidirectional, or maybe just the lower half of the payload, a hemisphere, right? I can't think of an antenna that's got an ideal hemispherical pattern. We can't achieve that, and we especially can't achieve it with a light payload. So with like a dipole hanging from the bottom, you will have a null, and by diversifying your receivers, this really helps recompose the whole image. Telemetry aggregation. This is one of the coolest features, and this is more advanced mode, but it does work very well. There's a UDP listener on the payload, so other devices can connect to it via Wi-Fi and actually send telemetry over the data link. We have demonstrated this working very well with Bluetooth Low Energy. So if you've got a bunch of students with unique sensors and unique payloads, they can program just a little Pi Pico W to collect the data from their sensor, and they don't have to worry about the ground station. They just have to get it to this payload, right? Then with my big ground station, I can receive the data, and then I can pipe it to wherever it needs to go. Like I said, perfect for student payloads. So some QR codes, two things. If we pull it off today, these will be the 2 links for our launches. The one on the left will be good for all the balloons going up. The one on the right, if we actually pull off the latex launch here in a couple minutes, that will be where we're live streaming the images. So I'll wait for y'all to open up the tabs on your browsers. Put your phone down once you're good to go so I can know. We're back to the old guy squint. Yeah. Are we in good shape back there? Almost there? Pinch and zoom. All right. And then last slide here. If you want to get involved, the best way to get involved, sondhub.org. We've got a Discord channel there. A lot of fun stuff happening on that Discord channel. Great Plains Super Launch. That is about 1 month from now. What is that? The 18th, 19th, and 20th of June. Superlaunch.org. My local group, the Richardson Area Balloonatics, k5rdbk.org/balloons. There's my email address if you want to harass me after the fact. And this is a QR code to these slides. So if you want to review anything afterwards, open this tab up as well. So anyway, thank you for your time. You know how to view it as a full screen page?
Yeah, we should. Here. Oh, let's get rid of this. Okay. And let me just look at the percentage here. I think this will be fine. If we need to, we can get the plus and minus here to jack it up a bit. But you want to see how it works with the screen? I don't know how they. How to get it projecting.
Probably duplicate. I see it on these ones.
Let's look here a second. Sir. Hang around.
So hopefully everybody's here for the Summits on the Air Forum. And I will confess that none of the three of us use a microphone that frequently, I think, right? So, but we won't send it all in Morse code. I think, are we about ready to roll?
Sure.
Okay. Well, thank you all for coming. I'm just going to do a quick introduction. After doing soda forums for a number of years here, it's so exciting to see still a vibrant crowd and a lot of enthusiasm and excitement. And this year, I thought instead of just listening to me, I would get some actual real professionals in here. So we've got Paula, K9IR, and Dean, K2JB. If you're active in soda, you know them very well. These guys are masters, and I can't wait to hear what they have to share with us. And I'm Keith, KR7RK. And so our goal today is to give you an enjoyable presentation. Also, we would really encourage audience participation wherever it's appropriate. So do you guys have anything to add to that?
I'll just say welcome. I'm Dean, K2JB. Glad to have you here. We'll get started and gauge your interest in soda, whether it's just casual, whether you want to chase, whether you've want to activate a summit, or you've activated one or two, or whether you're really worn out like the rest of us up here. So we'll get started with that shortly. Go ahead, Paula.
Got a lot of tall guys on this forum. Thank you all for coming out to this forum. We're hoping that we'll encourage you to get involved with soda. If you're already involved, we hope we'll encourage you to continue your involvement. I am humbled to be up here with these two guys. These two guys have forgotten more about soda than I will ever know, and they've been up to some really mega peaks and done so many activations, so I'm here to learn as well.
Okay, I have a couple of quick announcements to make. One is tomorrow at 1 p.m. I want to encourage all of you and bring a friend or two. We're going to have a soda meetup in between buildings 2 and 3, 1 p.m. tomorrow afternoon. It's a lot of fun, a more social gathering. You get to meet people and compare some of your stories. And also, we'll do a group photo at that meetup. So hopefully everybody will be there 1 p.m. tomorrow afternoon. Second thing is, if somebody or many of you can take a bunch of pictures, we'd love to
have pictures. It's always fun. I mean, of the forum presentation. It's always fun because we don't get to sit back there and see us doing it. And it also, that way I can send it to my wife and she'll know I'm really here behaving. So with that said, I want to just kind of get us started off. How many people, if you'd raise your hand nice and high, how many people here have never ever participated in SOTA in either as an activator or chaser? You're just here to learn. Awesome. That is so, isn't that great? Okay. How many people here have participated in SOTA as a chaser, maybe not even intentionally as a chaser, but you've happened to work somebody, meaning that you're not on the summit, but you're at home in your car? Okay, and then the last thing would be, how many of you have activated, you've actually traveled to a summit and logged some contacts? Perfect. All right. We got a great crowd. Good. Are we ready to roll?
Go ahead.
So, okay. So we've got a short slide presentation. We're going to just take a minute to go through each slide. And with each slide, Paula and Dean and possibly myself will add a little bit of commentary to that. Please, if you have a question, do not hesitate to shout it out or raise your hand or whatever. We don't need to wait until the end. We want to make sure that the topics get covered as we go. So with that said, so we start with, what is SOTA and who can participate? Who wants to go?
Well, SOTA is an award scheme for radio amateurs to encourage portable operations in mountainous areas. It doesn't necessarily have to be a mountainous area. It can be any summit that fits the requirements for it, and we'll talk about that. So they can be rather shorter than, Pikes Peak, and there are certainly a number of those. So, but it basically encourages hams like us and yourself just to get outside and do what you might have to do should you be called to do something to set up emergency communications. And the way we do that is with a point system. And so, you got to make a game out of it to get all of us, off of the couch and get us outside, make it fun. So that's how they do that. They do it with a point scheme. And they assign those points to different summits based on the elevation in the given area, with no summit worldwide being more than 10 points. Pikes Peak is 14,000 feet. It's a 10-point summit. Tennessee has some 10-point summits that are barely 5,000 feet. So it's all normalized for the regional area. And so that point system is what we accumulate, and what chasers also accumulate. They accumulate those points off also for contacting you.
I would just add that, as Dean mentioned, there's a variety of different heights for summits. I live in the Midwest, so I do have to do a fair amount of travel to get to some summits, but believe it or not, there are summits. I'm in the 9 area. I'm actually the association manager for the 9 area, and there are summits in Wisconsin. There are summits in the Prairie State, and there are summits in Indiana. Not a lot, not like North Georgia, not like Tennessee, not like Colorado, but there are summits there. So there's really only 5 states that don't have summits, and that means that most all of us should be at some point able to get to a place that has some summits that we can operate from.
I'll just add, well, first let me ask, is anybody here from Florida? I don't see anybody. The reason I ask that is Florida is a state that does not have a single summit that qualifies for SOTA. But most places where you live, there is something within driving distance. And for me personally, I love to go be active outside. I love the outdoors. There's nothing more precious to me than being out in fresh air and just enjoying it. But to add to that, I live in a homeowners association that won't let me put up a tower and or even an antenna. They specifically prohibit ham radio antennas. So how do I find a way to operate? Well, one of those ways is to go out and do portable operations and combine it with my love of hiking. Or as a chaser, I can chase from my car. And if I've chased you, if you're an activator, and if I've chased you, I've almost for sure been sitting in my car when I've done that. So it is a way for amateur radio enthusiasts to enjoy our hobby if you're not allowed to have a station at your house. And it really opens up a whole new realm of opportunity for you. Okay. So who can participate in SOTA? You guys want to?
Well, a lot of people start out simply by being a chaser. There's a way that you can find us when we're on a mountaintop. There's a spotting system. We'll talk about that later. But as a chaser, you can participate by finding us on the air and working us on whatever mode we're on. Paul and I are big CW operators, but I do operate phone on occasion. But you can find us and get those points. So if we're on an 8-point summit, you acquire those 8 points by making a contact for us and logging it into the SOTA database. And so that's part of what you can do. You can also be an activator. You can activate with 2 meters. SOTA allows you to operate any mode, any frequency that's within amateur bands. So I know several people who have been very successful reaching their goals in SOTA simply doing VHF. It's a little more challenging, and that's part of the allure of SOTA, is that it is a challenge to go out and get your antenna put up the way you want it, make it work, and make the contacts. Every activation is a challenge, so, but it's also fun. So you want to talk about the shortwave listeners also and your experience?
So, believe it or not, there's also a way for shortwave listeners to participate in SOTA in the same way that maybe some of you have gotten cards through the QSL Bureau or sent directly by shortwave listeners around the world. So it's very expansive program. How many of you are POTA operators? Okay, so you're probably seeing some similarities, and maybe you're scratching your head and you're thinking, well, SOTA, POTA, what's with all these OTAs? What's the difference? Some of the key differences, I think, are, number one, if you're doing POTA, you need to have, as I recall, 10 contacts before your activation qualifies for your points in the POTA system. 4 unique contacts required for SOTA. But for SOTA, we can't have any part of our system connected to our vehicles. We might be able to drive up to a summit, but after that, we disengage from the vehicle. The rule of thumb is I can drive the car away and the station is still up. If any part of the station collapses when the car is driven off, you're not compliant with SOTA rules. Most of the summits, or many of the summits that we access, do require a certain amount of hiking. It might be as little as a quarter mile. It might be as much as several miles. So we're carrying everything in a pack typically. We keep things lightweight. Battery-powered radios. We can't connect to a generator. We can't bring a generator in a car to a drive-up summit and plug in. So those are some of the more salient differences between the two programs, each of which provides its own set of challenges. Dean mentioned about points. And the one thing I'd like to emphasize is that while we're talking about points and totals, and yes, we do look at our points and totals, and we look at each other's points and totals too, but it's not a contest. It's not really a competition per se. It's not a club. There's no dues that you pay to SOTA. It's a program that you participate in. You register so that you have an account where your points for chasing and activating and SWLing can be uploaded, but it's really more the personal challenge, seeing how well you are doing and seeing how much more you want to set as goals for your SOTA activity. So it's really something that you can define for yourself. Dean mentioned doing VHF, UHF. K0NR has published a book on that, and he's in Colorado, I believe. So he's got plenty of summits to go to, but he has focused on VHF and UHF and is a real inspiration for those of you that would like to focus on that as well.
Okay, and I'm going to add, if you don't already know this, there's an amazing website that explains SOTA, and SOTA was originated out of the United Kingdom, and that's where it's headquartered. It's not something where you join and pay dues. You just you join in the sense of creating an account on their website, but it's all free. Everything about SOTA is basically free because you're going to spend plenty of money on the gas and the equipment and hiking gear and shoes, and I could go on and on. But the program itself is not it's not a paid membership. If you just Google search for Summits on the Air, you'll find the website quite easily. If you're participating in SOTA either as an activator or as a chaser, you might wonder how you're going to find other people that are participating. And there's all kinds of spotting applications available. If you have an iPhone or an Android and you search the store for Summits on the Air, you're going to find apps that will help you post your own spots as well as see other people's spots. There is a tendency to congregate around certain frequencies, but there's no requirement. As long as you're on a valid amateur radio frequency, you can go anywhere you want. You can do Morse code, you can do FT8, you can do single sideband, you can do FM. Whatever mode you want is fine. You can do satellites. So it's really, as Paul and Dean have kind of said it, it's an achievement-oriented program, and you get to decide what's important to you, whether that means you want to activate as many summits as you can, or get as many points as you can, or hike as many miles as you can. But with that said, there are rules in the program that we have to follow. One of those rules is to qualify as an activation, you have to have 4 contacts. 4 contacts sounds pretty easy in most cases. It probably is, but there are times when you're going to have a challenge. It could be because you've chosen to only use one band. And one of our most frequent activators emailed me and asked me to clarify, and so I'm going to do this out of respect for his question. I want to clarify that you need 4 points to have it be a qualified activation, but you really actually only need one, and I said points, I meant contacts. You really only need one contact for it to be a valid activation, and you can upload that log and it will count. You just won't get your activator points. And if points aren't important to you, then that's okay. And it could be that you found a mountain that no one has ever activated and you really want to activate it, and you go up there and you can just only squeeze out one contact. Well, you're still the first activator of that mountain. So he asked me to clarify that. I wanted to share that. I'm going to let Dean and Paula discuss some of the other activator rules.
And I've had that happen to me. I've been on a summit, only had VHF, wasn't able to spot. I made 2 contacts, never got another one, and I was on a time schedule to move on it was a 3-day hike in, and so that happened to me, so it's not unusual. One of the things that part of the rules is the activation zone. It's an area from the top of the summit down to 25 meter vertical. Think of it as an island that's 25 meters tall. So anywhere in that vertical space, you can set up and operate. You don't necessarily have to go to the physical summit. It's nice to do it and know that where it is, but sometimes it's just not feasible to get there. The brush is too deep. It's just, too sketchy to get there in some instances. So you can set up and operate in the activation zone. And he mentioned the goals. Soda is really, you're driven by the goals to operate soda, but you get to choose those goals. And basically your goals are within yourself. Your next goal is maybe a shack sloth. You want to chase, get 1,000 points chasing. You want 1,000 points activating. You want to do only unique summits, meaning you never go to the same summit twice. We've got a couple in North Georgia, Mark and Jean Swan, AE1MS and AE1JS. They're a 2 times mountain goat, and they're 100% unique, and they have no plans to do another summit. They want to do everything unique as long as they can. And they think they're going to age out before they'll get to have to go back and do another summit. So really, it's you set your own goals, and then when you reach one, then maybe your next goal is something different within soda. So keep that in mind.
I'll get to this new slide in a minute, less than a minute. One other thing I want to call out, you've heard each of us mention that the 3 of us tend to emphasize CW. Why do we do that? It's not out of a sense of elitism. We don't scoff at people who use other modes. Can anybody, let's get some audience participation. Can anybody suggest why it is that we would tend to use CW more than any other mode? Yes, sir. Signal to noise ratio. That's essentially it. Yes, sir. Little bit. Possibly. Possibly. I mean, there are people that will take QRP rigs and they will operate almost exclusively sideband. So, and there's microphones. I mean, I bought a microphone from K6ARK last night at the FDIM vendor night, and that thing is really tiny. It's smaller than most of the paddles I have. But basically, we're using CW because we're operating generally low power to begin with, because we're kind of limited by what we're able to carry over the distance that we're going and to set up and to power. And since we're not using, generators and other huge power sources, we're generally running off of batteries, so we have to be economical. This soda stud over here will hike up with a mega huge battery and a 100-watt amplifier that's powered by that, what is it, a 24-volt battery? I mean, I got tired watching him do that when we jointly activated a summit. He was kind enough to accompany me up to a summit in Arizona for my first Arizona activation. And I'm looking at what he's carrying, and I'm thinking, I am so glad you are doing that and not me. But that's why we tend to use CW. Let me go quickly to this first slide here. We've got a few slides that address what we've all found to be the most common question we get about soda, which is some variation of, what is a summit? I got this big hill in my backyard, and would that be a summit? There's a concept called prominence, which if you've done any mountaineering work or read about that, you're more familiar with it, but it's actually a technical, well-defined term. And that term is used in soda. What it boils down to in a simple view is soda does not simply look at the height, the elevation of a summit, of a mountain. We look at the elevation or summit relative to the surroundings. And I don't even mean necessarily the immediate surroundings. It could be surroundings that are quite distant, but we're looking also for how the concept of prominence. Does that summit rise up above? And here it's usually 150 meters, okay? 150 meters of prominence is what's needed. There are some associations, 9 Land happens to be one of them, where 100 meters of prominence is sufficient. And I'm sure the soda management team did that in part to make more of the program available to more areas. So in the Midwest, we just have to demonstrate 100 meters of prominence. But think of it in terms of, it's not just the overall height, it's also how dominant is that summit in the surrounding area. I had a question that came from a 9-lander who said there's a place called Lapham Peak in Wisconsin. It's along the Ice Age Trail. It's a very popular hiking location. It's really beautiful, and it's all of about 12 or 15 feet short in prominence. Real close, but I had to tell them, no, unless you come up with some error in the topographic maps, it's never going to be or we change the rules, it's never going to be a summit. It's just short.
Okay, so I want to add just one quick thing about the CW, and it's part of a bigger thing, but when you go to a summit, it's important to be respectful of the environment. You're not, well, in some cases, maybe you are the only user. You may be the only person that's been on that summit for years. And I've done some like that, and that's a fun experience. But other times you're on a summit where it's a popular place to go. And that's especially more common in the East where maybe the population is heavier and it might be a drive up. And so it's kind of important not to make a scene. And you might think it's very cool, but you're going to find maybe a park ranger is going to tell you, you got to get out of here. Or another person who is just enjoying their picnic is annoyed by all the noise and the antenna in the way and so on. So personally, I find Morse code is an easier way to be unobtrusive on a summit. Because if there are other people around you, you can just put the headphones in and nobody even hears you. Whereas if you're using sideband, you're inherently at least speaking into a microphone. And that, again, that's not it doesn't mean there's anything wrong with sideband. And I was joking a little bit. I do a lot of sideband. I just, that's something about Morse code that I prefer. And I do think it's important to be a good user. And one of the rules, you may have a mountain that qualifies the way Paula just described, but you're not supposed to be on that mountain, period. And in Arizona, we have thousands of summits, and about 2/3 of the summits, believe it or not, are off limits. And the majority of that is because they're on Native American land. And the tribes do not allow people to go recreate on those summits, period. They're considered sacred sites. And so it's a little frustrating because you can see a beautiful mountain and you say, I want to go climb it, but you can't. And if you break the rules, you're exposing amateur radio to a lot of bad will that we just don't want to be part of. So one of the rules is you have to legally be allowed to be on the summit. And that's different from what you see for some of the people that the peak bagger community can, people that aren't amateur radio, but just like to climb summits. Sometimes they're proud of the fact that they went to a summit that nobody else is allowed to. In amateur radio, we do not do that. We have to follow the rules. Okay, anything else on that?
Yeah. The rules say that the summit has to be generally accessible. If it's a public park and everyone can go there, you're fine. If it's private property, you should seek permission. If it's posted no trespassing, you're done. We do not trespass, period. If it's posted no trespassing, go find another summit until you might find the owner of that property and get permission to go. And sometimes the answer is yes, sometimes the answer is no. So that's what I like about SOTA is the ethics of it is that we respect those rules, we work within the requirements for SOTA, and we police each other. If something's questionable about it, I get questioned, I question other people, and it's apparent if somebody is trespassing on a summit they're trying to activate. They just don't last long in SOTA because everybody knows whether you're abiding by the rules or not. And that's what I like about it. Getting back to the sideband versus CW, you're limited by the battery that you can carry and the power that you can use. And most of the time we're transmitting peanut-sized signals of 5 to 10 watts. But in CW, that 10 watts is focused in 100 hertz bandwidth. Whereas with sideband, that 10 watts is spread across 3 kilohertz. And I can hear people or see people that are spotted on sideband, and they'll work both modes. I won't hear them on sideband, but when they go to CW, all of a sudden they're 5.7 on me. And it's because that power is concentrated in it and it's a better signal to noise ratio.
So next slide. So I think we kind of covered that, right? Yeah. And I'll let you.
All right, so we talked before about prominence, and I like to use a diagram like this one that I had found online back when I prepared a SOTA presentation a number of years ago to help people understand what does and does not qualify. So you can get an idea of what the overall prominence is. Usually the tricky thing is figuring out what that shared contour line is in order to calculate the measuring point for the prominence. What I would suggest, if this is not, no pun intended, resonating with you right now, what I would recommend is pull out your phone, take a picture of this slide and maybe one or two of the others that are upcoming. And Wikipedia has an excellent entry on the concept of prominence with yet another diagram or two in there. And just spend a little bit of time walking through and thinking through that, because I know for me it wasn't the most intuitive concept at first, and I had to spend some time thinking about it. And I think that you'll benefit from that as well. So, and this is partly to illustrate why I think SOTA uses prominence in addition to overall height. It's not always the highest point that has the prominence. So in Illinois, our high point is called Charles Mound. It's over in the northwest corner of the state towards Galena, Illinois. It's the highest natural point in the state. Guess where all the summits are in the state? Way down south. Actually, probably a continuation of the Ozark mountain chain in Missouri and Arkansas. If you look at a map, you'll see it's almost a complete horizontal move over. And in and near Shawnee National Forest in southern Illinois is where all our summits are, all 9 of them. But even more interesting, I think, is that, all the summits are located there, and they are all, I think Charles Mound is actually, because it's the highest point, it's higher than all those summits, but it is not itself a summit. And when you look at it, you can see why. There's no prominence there. So if nothing else, hopefully that helps you understand better why prominence is included in the SOTA rules.
Okay, and likewise, sometimes you'll be in a place and you can't really sense the prominence, but it can be a qualified. If you go to the Grand Canyon in Arizona, there's a summit there, and the activation zone is about a mile wide. So when you're on the summit, you really don't know that you're on a summit because it's just humongous. Okay, so does it have to be a really high summit to qualify then? Does prominence equate to so many thousands of feet that you can't breathe? I'll let you guys.
Well, no, I mean, the summits range from 1-point summits that have a relatively minor elevation, but they do qualify because of prominence, all the way up to the Pikes Peak, the 14ers in Colorado, the 14ers out in the Sierras. But you don't have to be someone that's going to hike 3 days in to do a summit. If you can get there and get to the summit within a short, hike, maybe it's only 10 or 15 minutes to get some of them. So you don't have to do that. And if you've been doing POTA, you're already halfway there. You've already got the setup. Maybe you're carrying more weight than you would if you were doing SOTA, but you've got the basics down pat. So you can do that. Yeah, Mark. Right. That's a good point. A lot of the summits are in national parks or they're state parks. They qualify as POTA locations also. And so you can claim that too. I did one yesterday. After doing a SOTA summit at Campbell Hill, I came back to Kaiser Lake State Park, did a quick POTA activation there. So real easy to do. So keep that in mind. Now, a lot of my SOTA colleagues go, you do POTA too? No, I do. So don't be afraid if you're doing POTA to do SOTA also, and vice versa. But just keep in mind, the rules are different, a little different for SOTA. They're a little more challenging than for POTA. But if you're doing POTA, you're halfway there.
So we've talked about points, and it would be natural for you to conclude, and there is some truth to this, that certainly the higher summits are higher points, but that doesn't mean that they're the most difficult to get to. Pikes Peak you can drive up. Mount Evans you can drive up. Pardon? Yeah, but I mean, there's a bunch of summits that you can drive up to that are 14ers. There are some 1 and 2 point summits that you will rue the day that you ever thought about hiking up to them because it's either a bushwhack through rhododendron or something else that is really challenging. So keep that in mind as you go through the SOTA website and you try to identify summits that would fit your style, what you want to accomplish, what your abilities are. Don't automatically conclude that the 1 or 2 pointers are going to be easy peasy and the big high pointers are going to be really, really difficult. It could be in many cases the other way around.
Yeah, I will say that by far some of the most difficult summits I've ever activated were the 1 and 2 pointers. And they're very rewarding and you're proud to get up to them, but sometimes it really beats you up in the journey. Because remember, the points have no relation to the distance you hike or the vertical feet you climb. It's strictly based on the height. And in fact, the point system it varies state to state. In Colorado, you need maybe a 14,000 foot summit to get 10 points. In Arizona, you only need a 7,000 foot to get 10 points. And other states might even be lower. Regarding the SOTA and POTA, there's nothing wrong with submitting your log to multiple programs, the same exact log. And in fact, there's apps that will allow you to generate logs that are compatible for upload. Just remember that SOTA only requires 4, POTA requires 10. WWFF, which is kind of the precursor to POTA, it's a much older program, and really much of POTA was based on WWFF. They require 44 contacts. And so, you can, if you go up to a summit that's inside a park that qualifies as a POTA park as well as the WWFF park, as long as, if you make 44 contacts, you just got a triple credit for one single activation. It all depends on the fun you want to have. If you spot yourself on the POTA spotter, you're going to find suddenly a flood of chasers that you didn't know existed if you're only spotting to SOTA. So it opens up a whole new realm of friends and contacts that you're going to make. Okay. Now, quickly, I'll say the drive-ups, they vary a lot from region to region. In Arizona, we have very few drive-ups in Arizona, and those that are generally a pretty rugged four-wheel drive drive-up. And maybe in North Carolina, there might be more certain ones that are along the highway or something. So with that in mind, I'm going to let you guys discuss this next slide.
Well, I was going to say that because, to allude back to the different point structure, I went to a summit in New Mexico called Lookout Mountain. Short little hike up. It's a 10-point summit with 8,800 feet of elevation for the summit. The next day, I went to another summit, about 8,800 feet elevation, In Colorado at Mesa Verde National Park, it was the 8,800 feet of elevation. It was a 2-point summit. So even though they were about the same elevation, different states are normalized based on the total number of summits that they have that meet the criteria. So you can have different points for almost equal elevations in different associations. And the associations are usually by states. In terms of the mobility issues, there are a number of drive-up summits in just about any area. New Mexico has some. I'm trying to think of the one over Albuquerque, Sandia Crest, a nice 10,000-foot summit that's a drive-up, and beautiful area up there to activate from. They have nice, what I call furniture, picnic tables. Usually the furniture on the summits for me is a rock or a log to sit on or a stump or something, but a picnic table is like the greatest furniture on a summit. But keep in mind that if you are challenged for your mobility, there are drive-ups, and I'll give you another example. The highest summit in Tennessee is in the Great Smoky Mountains National Park, and there's a paved trail up there. A lot of people I see pushing people in wheelchairs up there to get to that summit. Of course, they're just there to visit, the highest point in Tennessee and get the view. But some of the mobility issues you can overcome in one way or another.
So Dean mentioned earlier about some of the individual rules with drive-ups and such. One thing I do want to call out, and it was in an earlier slide, I don't know how many people caught it. We talked about that activation zone typically being 25 vertical meters, translates into 82 feet. Most of us round it to 80 feet as a ballpark. But there are some associations, or at least there's one that I know of, for the state of Michigan, W8M, for the Upper Peninsula and the lower part, the mitten part of the state, where the activation zone is only 40 feet. And a lot of people that go to activate in Michigan don't necessarily know that. So while I'm not involved with managing that area, I do try to call out to anybody that contacts me about activating in the Midwest, because I've done a lot of activations in Michigan, to be sure that you're within 40 vertical feet. So there is information posted on the SOTA website for each of the associations, both in this country and abroad, because it is an international program that actually was started in England. You can look up everything there and make sure that you're in compliance. K9EZ, yes, okay. So glad you're here. You came up with the drive-up list, did you not? Okay. Okay. K9EZ went through the time and effort to put together a list of summits, at least I think, are they all east of the Mississippi at this point? It's completely okay. So he's got an ongoing list that he's putting together of all the drive-up summits in the United States, and he'll post this on the Facebook page for SOTA. So be sure you check that out if you're interested further in exploring drive-ups. Anybody, audience participation, want to guess which of the 5 states do not have summits? Anyone? Can you identify the states that do not have summits? Yes, sir. Okay, very good. Very good, very good. And there you go. And by the way, this gentleman has activated first time and elsewhere. How long have you been with the program? Since the beginning, basically? Wow. Yeah, I mean, he's activated more summits than I could ever hope to do. All right, so we've got one of the states identified. Anybody? Yes, back there in the turquoise sweater. Yes. Yes, very good. Okay, we got Delaware and we got Florida. I'm sorry? Kansas, very good. Very, very appropriate. Yes. Not enough prominence. All right, we got 4 of the 5 identified. Anybody want to take? Yes, sir. Yes. So, there you go. Those are the facts. We have a question. It's Michigan is the only state, and it's got its own association. It's the only association I know of that has that 40-foot. I emphasize that because I don't know if there's any others, so you want to check on that. I am not sure why. Well, I have an idea why it is, although I'm not sure why Michigan did that. And for example, Nine Land with Wisconsin, Illinois, and Indiana did not put that restriction. But a number of those summits in Michigan reminds me of what Dean mentioned, the 1 mile plus activation zone. And they may have thought to make it more challenging, they want you to come up hiking much closer to where the actual high point is. That's my guess. If you can. Yeah, I think it may be the only one, but I don't know.
They're actually historically, and I'm not what I consider a long-term soda operator, although surprisingly, I realized the other day it's been 10 years now that I've done soda, but I still feel like a newbie. It goes back farther than that. And there were some inconsistencies in things. It's based out of Europe, so everything was based on meters. And initially, it was that 25 meters rule. And if you translate that to feet that we use here in the United States on the imperial system, it's not an easy number to remember. And so a lot of the different associations would have different numbers. And there was even one, I'm trying to remember if it was Texas, that had 125 feet as their activation zone limit. And there's been an attempt to kind of standardize some of that. And in fact, in recent years, some of the American associations have gone to a standard for prominence that took us to 500 feet because it's rounded off. And in fact, it really was based on the 150 meters rule, which translates to like 490 feet. And by changing it to 500 feet, it actually added new summits to the database. So in Arizona, we were blessed to get a whole bunch of new summits to activate that, 1 year didn't qualify, and the next year, because they raised the threshold by 8 feet, they qualified. I'll also mention on mobility, I'm not aware of anybody that's ever done this, but maybe somebody has. You could fly a helicopter to the top of a summit. And that might sound kind of ridiculous, but there's a summit that I drive past quite frequently in Arizona that has all kinds of commercial towers, and this thing is a slab of rock. And I always dream as I'm going by, how am I going to hike up that? Someday I'm going to hike up it. I've plotted out routes on my GPS. It's in the desert, so it's extremely hot, and that limits when you can do it and limits it to a period where I was historically quite busy with work. So I never have activated it, but I was talking to a friend of mine. He's like, oh yeah, he works for a commercial company. He's like, I go up there all the time. I just fly the helicopter. If you want to ride, let me know. So I don't know. Anyway, that's something to consider. But mobility, I think Paula's point in that slide is you don't have to be, somebody that's capable of going and being a mountaineer and climbing to super high elevations. And there's probably some summits that are accessible to you, and it can be just as fun no matter what summit you choose. So if it's something that sounds appealing to you, but you're like, gosh, I haven't hiked since I was 16, that's okay. Go try to find the drive up, look at the K9EZ list, and I can tell you that a lot of us would be excited to work you on that. So.
We'll mention, the slide mentions a blind summiter. K1LIZ, God rest her soul, was a 2 times mountain goat, and she was 100% blind. Her husband, Ron, NR3E, moved from Indiana down to East Tennessee because he wanted to do SOTA. And she went along with him to the summits he was on. And the first time I met them, it really didn't occur to me, because I had just come off a half-mile bushwhack, didn't really occur to me that anybody with vision issues would take off through that briar patch. And so a year or so later, I discovered that she was completely blind, and she was so interested in what Ron was doing that she got her amateur license, went all the way to extra, and was absolutely thrilled to be able to go. Ron led her every step up to a summit and every step down. And so that's an example of someone that really, really wanted to do SOTA so bad, even though what we would consider a disabling ability, she found a way to get there. And so she enjoyed it. And so there is a way for you to be able to get to a summit one way or another.
I'm going to make a small plug for an upcoming SOTA event, in fact. Amy, Alpha Golf 7 Golf Papa, who is an active SOTA person, a lot of activation. She resides in Oregon. And in addition to sponsoring a W7 campout, where people interested in SOTA will all meet generally at the same campground, camp over a long weekend and activate either solo or together, get together in the evening, trade notes, trade stories, etc. She was also the catalyst for an event that we call Queens of the Mountain, or QOM, that some of you may have heard about. She was kind enough to ask me to assist her with that, but it's really her idea. And what the event is calculated to do is encourage more women to get out and activate summits. And we have an award that we give every year, and we've held this event for the past 2 years. We'll have our 3rd iteration this year in June. It's an international event. It started international last year. And our big award that we give to one of the participants is, we call it the Liz Award. And it's in honor of K1LIZ, because she is such an inspiration to all of us, how she didn't think, if you went to her QRZ page, you would never have known that she lacked sight. I mean, it wasn't an issue for her. She did whatever she wanted to do, and the sight made no difference at all. And we consider that to be a real inspiration to all of us, not just women, but all people involved with SOTA, that we can overcome whatever we might have that's holding us back as well.
All right, and SOTA continues to grow. There's just every year there's more and more people on the website. You can look at statistics about the number of summits available, how many users there are, how many associations. It's probably you're sitting here because you're aware of how big it's become. Do you have anything you want to add to that one?
Well, I'll just say that SOTA continues to grow. I've been active in it for 13 years, and a lot of the same people that were only a few chasers then, there's so many more chasers now. There's so many more activators, people we didn't know. I do want to recognize Gary and Martha, stand up. W0MNA and W0ERI. They are the top chasers in North America that are here with us. I go ahead and fill out my log, W0MNA and W0ERI. They're going to be there. They're going to be there nearly 99% of the time. Excellent chasers. But the SOTA program is growing in both participants and chasers as well as activators. And we're just, all of us that have been doing this for a while are happy to share our knowledge, share our pointers with you. And give you the benefit of our mistakes. And if you're going to activate, you're going to make mistakes. You're going to wind up on the mountain and go, my battery's still on the charger. Well, it was a nice hike. So you learn from your mistakes, and that's part of the challenge, is to continue to improve your station, your ability to get on the air, make as many contacts as you can. So it's just a really, I think SOTA is the very, very best thing of everything about amateur radio. It's the preparation, the skills, the getting outdoors, making it all happen, get to where you're going, but more importantly, get back. That's what my wife says, go, have a good time, but you better come back. There's been times where I took a wrong turn and it took me a little bit longer than I thought to get back.
Yes, yeah, definitely.
Go ahead.
Been here for a second. So we had a question or a comment about using spotting networks. Each of us has mentioned in the course of our comments this afternoon various tools and features of the SOTA website, and one of them is a spotting network. You can post alerts, and for you POTA folks, this will sound very familiar. You could post alerts. I'm going to be on thus and such summit. I anticipate I'll be there at this time, and I expect to operate on these bands and these modes. So people know to expect you around that time. And then there's spotting. And so you can self-spot, other people can spot for you to let people know that now you are in fact at that summit and you are QRV. There's also a self-spotting that works for digital and CW modes. The reverse beacon network will pick up your transmissions, and there's some SOTA software that's written that can pick that off of the RBN and automatically post a spot for you on the SOTA website as well. So there's some really cool features with that. Yes. Right. There are a number of other ways to self-spot. Do it using FT8. That's a more recent way. I know one of my friends, WA9STI, Scott, he spots very frequently using APRS. So there are a number of other ways to spot, but I think probably the most common one is you check for cell service, and you can either text or use the internet and post directly to the SOTA website. The only other thing I would add about the participation level is I mentioned before about the W7 campout. There are a series of different campouts that are held throughout the year in various parts of the country. The W4 campout was just completed in North Carolina this year. This weekend is a W2 campout. There will be a W4 fall campout. There's a W1 campout coming up in a few months. There's campouts in Kentucky. There's campouts in Tennessee. This is a great place for socializing, getting to know your fellow SOTA participants, learning and sharing information, jointly activating, learning more about a particular area. And again, for some of us that do have to do some travel, makes it all the more worthwhile to go to an area where you can chat with some of your friends, do some activations together. The first campout I ever went to was a W4 spring campout. And this gentleman here, together with another friend, were kind enough to take me under their wings, and I think I activated with you, Dean, the entire weekend. I went out with them, and we had a blast, and I learned so much by doing that. I was absolutely thrilled to have that opportunity. So what I do hope coming out of this is if you aren't in SOTA yet, you'll be part of that growth. You'll start participating, whether it's chasing, activating, or both.
Yes, the campouts are a great way. I mean, one of the goals that of the point system is the summit-to-summit contacts that you have. If you contact someone else who's also activating a summit, that's a different bucket of points, if you will, to accumulate. When we have these campouts, we can get 4 summit-to-summit contacts on VHF and qualify the summit, and they're all summit to summit contacts, and we move on to another summit. So that's a lot of fun. As far as the spotting network, Soda Watch 3, if you just Google Soda Watch 3, it'll come up, and if you can register on that website or the Soda website, either one, and then you could see everyone that's out there. This is so important because, you know, we get out on the summit and we've got peanut-sized signals, and we're trying to get the attention of everybody, that among a crowd of everybody that's running 100 watts to full QRO. And so our signals don't get a lot of attention. This gives us the attention that we need to get the chasers pointed in our direction. So Soda Watch 3, Soda Goat is the app for iPhone. There's another one for Android. Soda Atlas is one. And I think there's Ham Alert is one. You can if you just want to look for one particular call sign, you can set Ham Alert up, and it'll alert you when that one person is activating anywhere. So, but Paula mentioned that she came and went with us. If you haven't done SOTA before, find someone that you know that's doing SOTA and go with them. I've learned so much by doing that. Our association manager, Pat, WW4D, he took us on some pretty gnarly bushwhack summits that I would never, ever even consider doing. But going with him and seeing how he navigated and the tools he used raised my confidence level tremendously on being able to go out in the middle of the woods and just take off to a summit. So find someone that you can go with, even if you don't even have any equipment. Go with them and use their equipment. You'll start your learning experience for SOTA by doing that, and that'll get you on the right path.
Yeah, and that comment you just made about the bushwhack is maybe an important one. I'll get to you in just 1 second. A lot of the summits do not have a trail. In fact, it's very common for summits everywhere that the trails don't actually go to the summit. So you may have to be hiking through some pretty rugged terrain, which it's smart, and I don't follow this rule myself as much as I should, but it's smart to go with other people for safety reasons. But it's also great to go with other people. And SOTA itself is great because you're going to establish friendships if you do a camp out, if you go on a joint hike with somebody. You know, just a couple of days ago, a friend of mine came in from Nevada, and he brought another activator from Northern California, and we got together and went on a hike together and did an activation. And those are friendships that I would have never had if it wasn't for SOTA. And that's one of the reasons the program is so exciting. It's not actually about the radio, it's about the people. So that's one reason I encourage everybody to get involved, is because you're gonna meet some amazing people, and just there's a vast wealth of knowledge and friendships and people that will invite you to come visit them that you're never going to have otherwise. We had a question here.
As long as you have 10 contacts, you can upload that file to POTA. You have to massage it a little bit to put the POTA reference in the proper field that's labeled correctly, and I can show you how to do that. But for SOTA, I mean, as long as you're going to have 10 to upload to POTA to get credit for it, but with SOTA, you only need 4. Same contacts, absolutely.
They double count.
Yeah, and there's a lot of logging software that will allow you to put in both. Like I use FLE log. I do all my logging on the summit manually on paper with a pen. There are a lot of apps that allow you to log, you know, directly, but I do it by paper, and then I go home and I use a program called FLE log, Foxtrot Lima Echo. FLE log is like a text editor, if you're familiar with computer programming. Very, very unintuitive, but it's very basic. So you really only need to learn about 4 things and you're done. And you can put in there a POTA reference and a SOTA reference. You generate an ADIF file and you upload the same exact ADIF file to both, and they know, they'll pick up the reference. So, you had a question, Gary?
You want to explain the point system for the awards? Yes. Well, for activating, the Mountain Goat Award is accumulating 1,000 activator points. So if no summit is worth more than 10 points, it takes 100 10-point activations to reach that goal. Well, there are considerably less number of 10-point summits than there are 8, 6, 4s, 2s, and 1s. So it takes more than 100 activations in most cases. The Shack Sloth Award is 1,000 points also that you get for chasing folks for whatever summit they're on. As soon as all those points add up to 1,000, you can claim that Shack Sloth Award. And then after that, it's multiples of that. And you can order the certificates from SOTA. You can order the middle one that you see here is a little glass award for Mountain Goat, and then you can have endorsements put on that also for each multiple of that you get. But my award is the satisfaction of going to every summit. It pumps my tire to go up and just make activations. You make a contact in Europe and the very next one's in California. Who does that? It's just so much fun and enjoyable just to know that you've been able to successfully make those kind of contacts.
Yeah, I think Dean really nailed it as far as the excitement that you get. You set up this really what's a bare bones station compared to even most of our home QTHs. I remember I'll just share one quick war story. I'm sitting on the side of the road to activate a summit in Arkansas because while the summit itself is on private property, the AZ extended to the public shoulder. And so I could legally activate there. And this is probably about 8, 9 o'clock in the morning. I got up really early to drive out, and I'm out there operating. And I'm like, did I hear what I just think I heard? I had a JA contact me on 30 meters, and here I am in Arkansas with an NFED random wire. And I'm like, oh, yeah. But it got even better about 2 years ago. I got my KH-1. I'm up in northern Wisconsin near my cabin. It's like 2 in the afternoon. I go out to a summit there. I pull it out. Let's see what happens. 15 meters. I work 2, 3 JAs with a whip, just like that, and probably less than 5 watts. That really, if that supercharges you, you got to get into SOTA.
Andrew, KD4ZZK, has some comments also. He's the association manager for Arkansas, and where else?
Yeah, Arkansas.
Arkansas. Okay. And he has set me straight. I mentioned that we watch each other's back. He had to correct me on a summit that I did out in Arkansas 3 years ago, where I went to where people had been activating prior to that prominence rule changing. And so I activated it, beautiful spot. But he said, Dean, the prominence rule has changed, and now the activation zone is all on private property, and you can't get there. So I couldn't claim that.
I forgot about that.
I turned it in for POTA, but I couldn't claim it for SOTA. So we do watch each other's back, and we respect that. Go ahead, Andrew.
I forgot about that. I wanted to say one of the biggest differences between POTA and SOTA is activators for SOTA can actually upload a trip report at that particular site. So when you're doing, other people behind you are doing research to say, hey, how do I get here? What's the best way? Is it on private property? Is it not? Well, activators can actually upload a report saying, hey, this is the way you have to go. You can't go this way. And so it's really user interactive. Whereas POTA, you're kind of stuck with the information that's there. And you can upload GPX tracks. You can upload pictures. You can upload a link to, like, if you've got a blog where you got a lot more pictures, you can upload to it. And that helps other activators behind you that are wanting to look at that. Because I've gone and looked at summits when I'm doing research in other states, you know, and I travel 13, 14 hours, and I see it's been activated like 20, 30 times, but there's hardly any information of how to get there. And so I'm thinking to myself, well, it must be an obvious access route. So I look at the map and I'm looking at Google Earth and there's no trails or anything. So I'm like, well, how are these guys getting there? So I end up having to email them directly, and they'll say, oh, well, I went up this way. And I'm like, well, do you have a GPX track? And then they share it with me. Well, then I'll upload it to that page so the next person can just load that track in their GPS and know the best way to get there. And it's really nice the way you can, almost kind of like Wikipedia, where you can put an article in there or put a little note in there for other people that are wanting to do research to get there.
And I will add that WW4D, Pat, is association manager for the W4C area. He has been the pathfinder for all of the rest of us in the W4C association. He just is very diligent. I think he goes to bed and goes to sleep watching Cal Topo just to figure out how to get to summits and do that. Speaking of drive-up summits, if you Google SOTA drive-up summits, Kent's page for drive-up summits will pop up in Google. So SOTA drive-up summits in Google will get you there. Go ahead, Kent. Again? The Facebook page, yeah, there's several Facebook pages for Summits on the Air, Southern Appalachian SOTA, W4C SOTA. So there's different associations have their different Facebook pages also. And we'll publish, you know, if we've got a camp out going on, or there's some sort of a get-together, I know Alan, AG4VA, the Virginia Association manager, they'll have training sessions where they'll all get together, spend a couple of hours talking about how to get to different summits and different methods and whatnot, and then they just go out and disperse and do summits in the immediate area. So there are Facebook pages out there. If you just look for SOTA in Facebook, you'll find many of them there. And there's a lot of good information on those pages.
Okay, Andrew mentioned GPS tracks, and I just wanted to expand on that just a little bit. Normally I carry a Garmin. In my case, it's a Garmin 67. It's a GPS unit that's designed for hikers, and it records your path. And that's really important for a number of reasons, one of which is when you're doing a bushwhack, sometimes you get to the top and it's not real obvious where you came from when you're going back down, and you certainly want to get back to your car. So it helps you re-navigate back. But when you're done, you save that track, and it can help you in the future, and it can help other SOTA activators. And so there's a couple of websites. The older of the two is called SOTA Maps, and that's if you go and get into the SOTA website like we've been discussing, there's a section called SOTA Maps, and you can upload your GPS track for a specific hike that will help other activators decide how they want. And sometimes that's important too, because it may be that half of the mountain is on private property and you can't hike on that half, but you can hike on this half or something like that. So it's a very useful tool. More modern, they created a website that's called, I call it SOTLess. It's SOTL.AS, SOTL.AS. And SOTLess will scour SOTA maps and make it even a little easier to see that. And you can see the track, you can see comments that the activator put, like terribly difficult hike or easy hike or whatever, details about it. But I would strongly encourage, if you're going to activate, a couple of things you should do. One is research to death about who owns that summit and whether it's accessible to you or not. Even if it's already been activated, you still, because sometimes that changes. So if it's on, Forest Service land, yeah, you're probably free to go. You may find that particular summit's closed down because of fire restrictions or some kind of mining activity that they're doing. And that happens to us in Arizona quite often. So you should research your summit before you go. And then, look for those tracks, see if that matches what you're interested in doing for a hike. And those kind of resources, SOTLIS especially, is extremely, extremely useful.
SOTLIS is an acronym for Soda Atlas. So if you Google Soda Atlas, that'll get you there. And if you have a mapping program such as Gaia or CalTopo, you can download those tracks onto your mapping application, and then you just use your phone to follow that track.
And then the other thing I'll add is using the GPS. The particular model I have, it can be a useful tool for when you get onto some remote areas where cell service still doesn't exist. In Arizona, that's common. I know there's certain parts of the country here that's common. As satellites become more prevalent, that's probably going to not be an issue. But currently, there are places you'll go where you can have your spotting application, but you don't have cell service and you can't self-spot. But with the GPS, not only can you use it for emergency communication, but you actually can send a text message that will get translated into a spot and automatically post where you are. So I strongly encourage using a GPS when you're hiking.
So, and as you may have guessed, probably a final reason to have a GPS with you, and maybe one other piece of gear I'll talk about, is for safety. So I was out on one activation in northern Wisconsin, and I kind of got lost, and it was winter, and I was losing daylight, and I found out my boots were leaking, so my feet were cold. I got out of it, but it was a sobering lesson that got me to use some of the mapping tools that Dean and Keith have talked about. And I did get a GPS so I could track myself. The GPS I have is an earlier version of what Keith mentioned. It happens to include the same SOS function that Garmin has on their InReach, and that can be really important if you need to message out because you got yourself in a problem. I was hiking by myself in the UP, slid, thought I just sprained my ankle, hiked for the rest of the week, got home. A friend said, you should have a doctor check that out. I had a broken ankle. I could have been in a real world of hurt if that was a compound fracture. It caused me to buy something called a personal locator beacon. They cost about $350, $400. I know, not cheap, but what's your life worth? I view it as an insurance policy. That's a dedicated emergency device that you register with NOAA, so it is specific to you. And when you fire it off, they know it's you, it sends coordinates, and they can use search and rescue monitoring 24/7 to come in and rescue you if that's what you need.
Well, that does bring up a point. Soda can be dangerous. I've had a couple of injuries doing that, and almost had to push that little red button on the Garmin, thinking I was hurt worse than I really was. But safety is something that should be part of your plan on every activation that you go to, even the drive-ups.
Okay, we're pretty much out of time, and I think, as you can tell, the three of us could stand here for the rest of the day talking and being excited about it. It's SOTA. There's a reason for the excitement. So if you haven't experienced it yourself, definitely get involved. You guys want to?
Okay, I've got one thing here, just a little thing about SOTA. What is it about this thing called SOTA that we trek to mountains when we really don't oughta, to see if it's there, to see if we can, to see if our rigs will reach across the land? It's the drug of choice among the technical savvy, as addictive as crack if your wires match the wavy. We tell all our friends about this thing called SOTA, but only blank stares do we get in exchange for the telling of adventures that conclude we are strange. But we keep trekking to summits, be them a 10 or a 1, for even as kids, we've never had so much fun. Thank you all for coming.
Thank you. Yeah, right, absolutely. You're doing good. Yeah. Did you ever do any of those taking 5X antennas with the special strap?
Fight show on the desktop.
Good afternoon, everybody. It's almost 2 o'clock. And if you know me, I'm Tim Duffy, K3LR. We start on time. That's what we do. And you better buckle up because you've got 3 hours of some really, really good topics today. This is my 43rd year of hosting the Hamvention Antenna Forum, and I'm proud to be back here in Dayton, Ohio. So we have 4 really good presentations. The slide decks for these presentations will be on the k3lr.com website. Next week, we'll have them loaded up, and you can find presentations for the last 25 years are loaded up on that website as well. Just click on the Antenna Forum button, and if you have an idea about an Antenna Forum topic for next year, just send me an email, k3lr@k3lr.com. Our first presentation is investigating the NFED half-wave antenna and what makes a good RF connector. Please welcome Hal Kennedy, N4GG.
Thanks, Tim, and pleasure to be here. Thanks for inviting me. Look forward to this presentation for quite a while. The NFED half-wave is kind of a phenomenon. I was just asking Tim about sales at DX Engineering. He's selling so many that can hardly keep up with it. There's plenty of competitors, same thing. It's a very, very popular antenna for a variety of reasons. And so I'd like to talk about it today more from an engineering perspective and a physics perspective without getting into equations. In this subject area, which has tended to be dominated for the last decade by folklore. There's a 50,000 strong user group on Facebook for NFED half-waves. About 50% of the information that runs through Facebook on this subject is incorrect. And there are probably 30 YouTubes on how to wind the transformers for these things. Maybe 20 or 30% of those are incorrect. There's a lot of misstatements and confusion about how they really work. So maybe we can apply some science to that today. Why are they so popular? The big item in my mind is the fact that you can hang one up with only one support. And the next big item is that you can get one if you have 130 feet for the wire that will cover 80, 40, 30, 20, 17, 15, 12, and 10 meters. There are kind of virtually no other simple antennas available to us you can do that with. And it's inexpensive. So we're talking about 130 feet of wire and a matching transformer, and you're on the air on virtually every HF band. You can disconnect the wire from the transformer and feed it on 160 against radials and add that band. There are techniques to add loading coils to use a shorter wire on all the bands. So it's a versatile antenna, and because it's a single attachment point antenna, if you wish to use it that way, it's great for parks on the air, it's great for summits on the air, it's great for portable vacation locations, but it's also great for my place. I have one where you're dealing with the homeowners association and you got to sneak an antenna in somehow because they're kind of stealthy. The wire can be very thin. So they're inexpensive and they're fun. You can build this thing yourself. There's plenty for sale, and here's a couple of them. The one on the right-hand side, by the way, is the ARRL kit. So you can scratch build an NFED half-wave, but you can also buy one from myantennas.com. You can buy one from a company called PAR NFEDs, which is sold through DX Engineering and also Fiberplex, and make your own. The cores that are inside these transformers are readily available. in multiple places, including DX engineering. And the rest is wire and a little bit of elbow grease. So you certainly can build your own. You can buy a kit from the ARRL, or you can buy the finished product. They come in all sizes and varieties. There's low power ones, high power ones, single band ones, multi-band ones. Take your pick. And the PAR end feds, for example, at DX Engineering, I forget how many versions there are, but there's probably 10 at least. So you can find one that'll do the job that you want to do and works on the bands you want to work on, which is why they're so darn popular. And they don't cost a ton of money. The best ones are about $100, so or a little bit more. And you can certainly scratch build one for much less money than that. So that's why they're so darn popular. Back to folklore. There's researching for this talk and following the antenna anyway, because I have one. It's my primary antenna right now. I really wanted to understand, and I'm a double E, I wanted to understand from an engineering perspective how the thing works. And I wanted to be able to explain to other people how the darn thing works and dispel some of the folklore because it's wrong. So one of the questions that I see coming up all the time is, given you can hang one with one support, what's the best way to do it? Inverted V, inverted L, horizontal, vertical, sloper. Is there a preferred orientation? So we're going to explore that. These antennas need a counterpoise. Some of the people advertising them for sale say no counterpoise required. Don't believe the advertising. If you have one and it works, you have a counterpoise. You may or may not even be aware that you have a counterpoise, but you do. You need a return current to the feed point to be equal and opposite to the current moving into the antenna for that antenna to work. And we'll look at counterpoises. And then high power. These are not too hard to burn up if you really work at it. Anybody, I do not want a show of hands. Who runs a kilowatt or more on FT8? Do not raise your hand, okay? Do not raise your hand, because the people sitting around you are going to come out of their chairs. This is a very controversial topic. But it's easy to burn one of these up if you run a kilowatt on FT8. I should probably have thought better of this, but I'm going to show you how to do that successfully, just in case you might want to. And there's no reason at all not to run 1.5 kW on CW and sideband to win a contest or break a DX pileup. And so building them for high power, I think, is a legitimate subject to talk about. So let's talk about that too. Two subjects on theory, and then we're going to move to practical stuff. This is the current and the voltage along a half wavelength of wire. You're most familiar, almost all of us are, with feeding this thing in the middle. That's called a half wave dipole. That is the point of maximum current in a half wavelength of wire. And it doesn't matter where you feed it. You can feed it at the end. You can feed it halfway in the middle. You can feed it at the 1/3 point. We call those off-center fed dipoles. The current distribution is always the same. It's that orange line, and it occurs as a peak where the voltage is a minimum. And that's where the radiation happens. If you don't remember anything else today, antennas radiate where the current flows. It's the flow of electrons through a conductor that causes RF. And so in a dipole, the current's the peak at the middle, and the radiation is from the middle of the wire. There's very little current at the ends. There's very little radiation at the ends. That includes feeding it at the end, feeding it in the middle, or feeding it halfway in between. As the current goes down for a given power, this is just Ohm's law now. Here's the hardest science today, Ohm's law, okay? For a given amount of power, if the current goes down on that wire, which you will discover out at the end, the impedance has to go up. It's just Ohm's law, solve the equation. So in the middle of a dipole, we see about 72 ohms of impedance, and that's what we're used to, and we feed those with coax, and they're a good match for coax on the fundamental frequency of a half-wave antenna. As you move away from the center, the impedance goes up. The current's going down, the impedance is going up. When you get all the way out to the end, the current is almost zero. The impedance is up between 2,000 and 4,000 ohms, and it becomes impossible to feed it directly with coax. If you apply a 50 ohm transmission line to a 2,000 ohm load, you get an SWR of about 20 to 1. So we use a matching transformer at the ends. There's a magic place about a third of the way out the wire where the impedance looks like it's about 200 ohms. That's easily fed with a 4 to 1 balun. And off-center fed, you'll notice off-center fed antennas being offered for sale are fed with 4 to 1 baluns, and they operate at 200 ohms. So that's what's going on a half wavelength of wire, whether it's a dipole, off-center fed, or end fed. One more chart. The green line now is what the orange line was a moment ago. That's the fundamental frequency. And if we're feeding it in the middle, again, we're going to see 72 ohms, give or take. On the second harmonic, though, the other line is the current waveform on the second harmonic. On the second harmonic, there are 2 current peaks, not one, and there's a current minimum in the middle of that wire. It's a 1 wavelength wire at this frequency, or the second harmonic, if you will, of the fundamental frequency. Out at the end, the impedance is the same on the fundamental as it is on the second harmonic. Way out to the edge, either edge, right? We have very low current in both cases, very high impedance, but the same matching transformer can match that wire, whether it's on its fundamental or second harmonic. A third of the way out, where we would put the feed for an off-center fed dipole, it's still 200 ohms. And this is why off-center fed dipoles are able to work. As you start drawing the waveforms for third, fourth, fifth, sixth harmonic, you'll notice they all intersect at a point about a third of the way down the wire, and at that point, they all look like 200 ohms. So you can feed a wire on all of its harmonics, one-third of the way, roughly one-third of the way out, with a 200 ohm matching transformer. You can feed the wire on all of its harmonics at the edges with a transformer that gets you up to about 2,000 to 3,000 ohms. And you cannot feed the wire in the middle on the even harmonics. Take a look at the middle of the wire. On the fundamental, we have lots of current, about 70 ohm impedance. On the second harmonic, we have almost no current and a 2,000 or 3,000 ohm impedance. This is why 40 meter dipoles don't work on 20, right? You load up on 40, got a 1 to 1 SWR, load up on 20, have a 20 to 1 SWR. We don't use 40 meter dipoles on 20, we don't use them on 10. Those are even numbered harmonics. And the center of the antenna is moving wildly from 70 ohms to thousands of ohms as we step through the various harmonics. So if you want to feed a wire on every single band, move at least a third of the way out, or move all the way out where the impedance stays relatively constant no matter what harmonic you're on. Yeah, okay, great, swell, bunch of theory, thanks for nothing. If you struggle through those charts, let's talk about what that actually means if you're going to put one of these things up and get on the air and try and have a good signal. Promise to try and make it meaningful for everybody. So back to the first question, what's the best way to put it up? Given that you have a chance, right? You may not have a chance if your park's on the air and your only opportunity is the transformer box on the picnic table and you throw the wire up in a tree. Well, your option is a sloper or no option, one option only. And that's way better than nothing. There are no bad orientations in the list. There are scenarios where one orientation might be better than another. Lou McCoy, been a long time since he's silent key, but he wrote extensively for QST and CQ. And the handbooks always used to say, look, all the RF has to go someplace, right? So if all the RF has to go someplace, anyhow, just put one up. Don't stress out. That's the first tip. Don't stress out about the orientation. In some scenarios, the orientation's better than others by a little bit, but they all work. Don't sweat it too much. In terms of what's best, I can't answer your question till you answer some of my questions, which are, do you want to rag chew with your buddy 2 states away, or work DX, or both? What bands do you like to work on? What do you got for supports? Can you only get the wire up 10 feet off the ground? That gives you one answer. If you have 2 pine trees at home that are 90 feet tall, that gives you a completely different answer. How portable do you want the antenna? How fast do you want to put it up? This really surprised me. I'm not into POTA, at least not yet, but I've talked to a POTA buddy of mine to get ready for this. And I asked him what makes a good POTA antenna. He said, oh, speed of deployment. I would have never thought of speed of deployment. He said, look, I can put 8 parks on the air in one day along the coast of Georgia, but I can't do that if it takes an hour to put the antenna up. But if I can put the antenna up in 10 minutes, I can put 8 parks on the air in one day. To me, the number one overriding characteristic is how fast can I put the thing up? That was a surprise. There are probably more surprises I'm unaware of, right? People have 100 uses, subcategories of uses for antennas. How stealthy do you need it? Got an HOA? The other thing he told me is park rangers do not like to see us throwing wires up in trees. So he said stealth would be number 2 on my list. I want it to go up and down fast, and I want it to be invisible. Other considerations come into the answer to the question. How concerned are you with noise level? Vertical polarization is noisy compared to horizontal. If you're going to run high power at home, you got some safety issues. We'll have a chart on that. What do you got for trees and support poles? That affects the answer. And money may enter into it, but this is a low-cost antenna. All right, let's take a look at the radiation patterns of the antenna in 2 generalized configurations, and then I will actually try and answer the question about what's best. This is the radiation pattern on 40 meters for a 40-meter end fed close to the ground. This would be the parks on the air scenario. And like all 80 and 40-meter antennas close to the ground, virtually all the radiation goes straight up. These are sometimes called NVIS antennas. They're great for local rag chews, not so good for DX, but you can work some DX. And importantly, you're stuck with it. If you're close to the ground, this is what's going to happen, especially on 80 and 40 meters. In the azimuth plane, the radiation is broadside to the wire. So in this laser pointer is not going to work much in this scenario, but in the right-hand chart, the antenna wire would be vertically through the center of the chart, and the radiation would be perpendicular to the wire. This is classic dipole radiation patterns. It's exactly the same. The radiation pattern for half wavelength of wire is the same, whether it's a center-fed dipole or an end-fed half wave. They're identical. So if you know much about what happens when you put a dipole up close to the ground, you know what's going to happen to your end-fed half wave close to the ground. That would be the scenario on 80 and 40 meters. Let's take a look at the scenario all the way up on 10 meters. In the most left-hand diagram, there's the antenna wire with 8 current peaks along the wire. We are now operating on the 8th harmonic, okay? And the first thing I can tell you about that is, and I'm a pretty good antenna modeler, I can't tell you what's going to happen. I mean, I did a model. Here's the results. I can tell you the radiation pattern and elevation will be mostly towards the horizon, unlike the low frequency case. And I can tell you that the radiation now has moved along the wire instead of perpendicular to the wire. But look at all the little blips on these charts, right? I can't tell you how the 8 current lobes interact. I can't tell you how they interact with the ground. I can't tell you how they interact with the branches and the trees and everything around these antennas. My contention is don't spend time modeling on 10 and 15 meters because you can't predict what these are going to do. All the RF will go someplace, put the thing up, get on the air, and don't worry about it if you're real interested in 12 and 10 meters. All right, here's the answer to the question. I tortured you long enough, right, if you really wanted to know. Here's the elevation pattern for 40-meter end fed, and you have to pick a case to talk about. But there's an infinite number of cases. So I tried for a representative case. Here's an end fed half wave on 40-meter end fed on 40 meters. As I mentioned a minute ago, for the case of a horizontal wire, the inverted V wire and the inverted L wire, virtually all the patterns are identical. So don't worry about it. put it up the best way you can, get on the air and have fun. You'll notice there's an outlier, and that's the sloper. And here's one of the pieces of wrong folklore. People say slopers have gain. Slopers do not have gain, okay? Slopers have directionality. Slopers are better in the direction they slope and have a front to back, if you will. But notice overall, if you can see the chart, the gain of the sloper, the green line, off the front and off the back is lower than the horizontal wire. This is why, especially for POTA and also for home installation, I don't recommend necessarily a sloper. If that's all you can do, do it. Get on the air and have some fun. You'll make lots of contacts. If you have a choice, stay away from the sloper and move to something like an inverted L. The inverted L, the vertical part will give you DX coverage. The horizontal part will give you local coverage. It's a great compromise antenna. This is something I discovered. I've never seen this in the literature anyplace. This is kind of new info, unless, catch me afterwards if you've seen this before someplace. I have never seen this. I started modeling these antennas on their second harmonic, and I thought I made a mistake because I'm not used to seeing a pattern, elevation pattern, for a wire near the ground, which doesn't have most of the energy going up. And yet on the second harmonic, in fact, that is what happens. This is operation on 20 meters, comparing operation on 20 on a 20 meter end fed versus operation on 20 on a 40 meter end fed, both at 30 feet, same frequency. You would expect first order approach to it, they look the same, and they don't look at all the same. The end fed operating on its second harmonic is a much better antenna than the end fed on the same frequency at the same height, operating on the fundamental. It took me a long time to figure it out, and the physics get beyond today's conversation. But here's a rudimentary explanation. If you're center feeding an antenna, the signal from either side arrives at the feed point at the same time. If you're end feeding an antenna that has two current lobes, the first current lobe arrives at the feed point all the way at the end at some time that's similar to a dipole, but the current lobe further down the wire has to transverse all the way down the wire and shows up 180 degrees late. That cancels the ground reflection. This is a really cool antenna. You can run these things very close to the ground and not send the RF straight up if you're operating on the second harmonic. So one of my recommendations is if you like 20 meters, and that's a big POTA band, and that's a good band for your house, right? Try and get a 40 meter one up there and then run it on 20, as opposed to a 20 meter one. You'll have much better success with the antenna on 20. So here's some conclusions, and then we'll move to a couple other subjects. For the case where you want a portable antenna, like parks on the air or vacations, a 66-footer, and by the way, the ARRL kit is a 66-footer. You can put a different length of wire on it, but that's how it comes. Those will cover 40, 20, 15, and 10. You do not cover 17, 12, and 30. And 17 is a pretty active POTA band. So you might want to think twice about the ARRL kit or putting up a 66-footer. On the other hand, to go much beyond that, you need a 132-footer, and those are hard to fit into some places. Don't be afraid to dogleg these things. Mine runs out to a tree, and then it crosses over to another tree, and then it goes up another tree. And I have a friend with a 160-meter one that's 260 feet long. It goes all over the place. Up and down trees, back and forth, some slopes, some's horizontal, some's vertical. Thing works great. In fact, that's K80AB. I don't mind mentioning him. He just this month ago got on the bottom rung of the honor roll, 331 confirmed. He did it on an end-fed half-wave. So, you know, don't think it's not a DX antenna. It certainly can be. You're stuck on 80 and 40, the RF's going to go straight up, almost no matter what you do. So don't worry about it. Just put it on the air. You're stuck on 10 meters also. The RF's going to go wherever it's going to go. And there's not a whole lot you can do about it. So just put it up and get on the air. And if you got to pick something and you got a bunch of choices, go for an inverted L, because then you'll have some DX capability and some local rag chew capability, and you'll be all set. They all work. They all work. Okay? It's almost the same story at home. But at home, get it as high as you can. Standard advice, right? Get the thing as high as you can. If you can get it really high, then on 80 and 40, you will not be sending all your RF straight up. You'll be able to shape those patterns depending on what orientation you can achieve. So getting it high certainly matters. The advice from the prior chart applies, though, for the rest of the home situation. Inverted L is a good compromise at home, just like it is if you're operating portable. And if you possibly can and you want to work 20, do it on a 40-meter sized wire. That's the way to go. Here's something we don't talk enough about in ham radio, and I have two terrible stories to tell you. First off, verticals are noisy, so I would not, it's easy to get a 33-foot push-up mast and put a 20-meter end-fed half-wave straight up, right? I don't like that idea. Verticals are noisy. In suburban environments, verticals can be very noisy. I'd rather see you use a sloper or an inverted V than a pure vertical. But the other problem for slopers that start near the ground, like on a picnic table, or verticals, is knowledge and keeping in the front of your brains that these are high voltage antennas at the ends, both ends, the feed point and the far point. With 100 watts on an end-fed half wave, the voltage is about 120 volts peak at the ends, which is not all that much. It'll give you a good RF burn, but you'll survive. At 1,500 watts, SWR 1-to-1, the voltage at the ends of these antennas is 3,100 volts peak, okay? You need really good insulators, and if you look at the commercial ones, they all come with sort of oversized insulators. There's a reason for that. They got to withstand 3,000 volts. Now think about 3,000 volts in a rainstorm or under ice or during a snowstorm. We run these antennas all the time, right, in the weather. So you got high voltage to think about. You have high voltage that can cause horrifically bad RF burns once you get up to 3 kV of RF. And if the feed point of your vertical is near the ground or your sloper, or you're feeding from the end of an inverted V, people will touch it or can touch it, or animals can touch it. They are dangerous, okay? So you may want to fence off the bottom of your end-fed half wave if you're going to run a kilowatt into it. And now here's the really bad item. I know of 2 incidents where people set the woods on fire. No kidding. The case where it was really serious, I am sworn to secrecy to never reveal who that was. It happened near me in Georgia. They had to call the fire department. Fire department had to come out and put the fire out. It was in suburbia. Other homes were at risk. This was caused by an end-fed half wave resting against a tree branch in fall, dry leaves, running a kilowatt. Set the woods on fire. The other case is me, so I can talk about that one. I set the transmission line to a similar antenna on fire, running 1.5 kilowatts in a contest. It was ladder line. Ladder line burns. And I could watch the flame go up the ladder line towards the trees. It is the most frightened I have ever been in my entire life. I'm in the middle of suburbia. I am surrounded by subdivisions. I didn't have to call the fire department. I was able to grab the transmission line and shake it as hard as I could, and I was able to get it to stop burning. But man, you don't want to do that. It's bad for your health. So bad for your homeowner's insurance. If you're going to run high power on these things, don't let it touch trees. Pay attention. There's a lot of voltage involved. Okay, counterpoises in one chart. You cannot feed the end of a wire without having an equal and opposite current going someplace. It needs to look balanced, even though physically what you're going to wind up with is physically unbalanced. So if you see an advertisement that says no counterpoise required, that's not true. The counterpoise can either be a piece of wire or the shield of the coax feeding the matching transformer. If you supply that wire and you don't use a choke, then the antenna will force current down both. It will force current down the shield of the coax and down the counterpoise wire. If you add a choke at the matching transformer to stop current down the shield of the transmission line, then all the current will go down the counterpoise wire. That's not necessarily a good thing. There's really nothing wrong with sending the current that needs to flow in a counterpoise down the shield of the coax. And lots of these things are on the air very successfully, no counterpoise wire, but the shield of the coax is acting as the counterpoise. A rule of thumb is developed, and this is where the folklore looks to be just fine, that if you multiply the wavelength of the lowest band you're on times 0.05, that's a good length for a counterpoise. And if you do the analysis, it turns out that's actually correct. So if it's an 80-meter one, about a 13-foot wire is fine. If it's a 40-meter one, a 6 or 7-foot wire is fine. This is not critical. If you have a 20-meter end fed, then a counterpoise this long is good enough, right? Why is a counterpoise this long good enough, right? Doesn't seem to make sense. Remember, the other end is this gigantic piece of wire, and you're going to counteract the current in that wire with a wire that looks like this. How does that work? Well, the reality is you're feeding the wire at a 2 to 4,000 ohm point. For the counterpoise, all you need is 2,000 to 4,000 ohms, and a piece of wire 3 feet long on 80 meters looks like about 3,000 ohms. So it's a perfectly good counterpoise to supply current to the feed point in an equal and opposite, phase opposite manner to the current going out over the main antenna. And yet here's why you can get away with it. Back to the one thing I said, if you don't remember anything else, remember that it's the flow of current that causes radiation. These little tiny counterpoises have no current flowing in them, right? Because we're working at the end of the wire. So they don't contribute to the radiation pattern. So you can put a 3-foot wire out there and it supplies a 3,000 ohm load that for some small amount of current that matches the current in the end of the big antenna. But the end of the big antenna is not contributing to the radiation pattern, and the little counterpoise is also not contributing to the radiation pattern. So it's there almost like a dummy load, right? It supplies current, but it doesn't affect the radiation pattern. That's how we get away with these things. That's counterpoises in one chart. All right, let's go to high power. If we must. Some people really don't like this subject. The so-called high power ones of these for sale commercially typically rate them at a kilowatt on CW and sideband and about 200 watts on FT8. FT8 has a duty cycle of 42%. This is another major mistake you see all the time. People say it's 100%. It is not 100%, it's 42%. Yeah, when the carrier's on, and that's a peak power of 100% of carrier power. But when we overheat these transformers, we do that over periods of 10 to 15 minutes. And so on FT8, you need to look at what the duty cycle is of the waveform over 10 to 15 minutes. The duty cycle of FT8 is 42%. No more, no less. It's 42.0. You transmit for 12.7 seconds, you listen for about 17. You transmit for 12 seconds, you listen for 17. It's 42%. So how do we, but that turns out that's a lot. That will overheat the transformer in your end-fed half wave if you push much above 200 watts. So what can we do about that? There's two problems. Once you go to high power with these things, there's two problems. This is a photo of the inside of a store-bought, very popular end-fed half-wave. There's a 49-to-1 matching transformer, which is wire wound on a ferrite core, pair of cores. And the cores will overheat on 80 meters. That's one of the two problems. The other problem is there's a small compensation capacitor down at the feed point where the coax comes in. That capacitor is there to compensate leakage inductance in the transformer. And the current through that little tiny capacitor, by the time you get to 10 meters, is up around 4 or 5 amps at high power, and the capacitors can't take it. So if we're going to run this thing with high power, we need to get the heat out of the core on 80 meters, and we need a better capacitor on 10 meters. Let's talk the capacitor first quickly, because this is an easy one. But I'm going to show you something I've never seen before. I think this is a bright idea. I don't know. We'll see. The straightforward way is to add more capacitors. The TDK capacitors that people are using cost 48 cents at Mauser. Similar price at DigiKey. So it's not a money item in terms of what are we going to do about the capacitor. They're really cheap. I buy them 20 at a time. Just parallel them up. Spread the current. As Tim mentioned, these charts are going to be on k3lr.com. So you probably can't read the part number off the bottom of the chart. Just go find the chart on k3lr.com and you'll see the rest of the information. You can use the chart that way. Another alternative, which is better, is doorknob capacitors, but they cost between 20 and 40 bucks on the internet. And some people don't want to make that investment. You can probably find them cheaper at the flea market today. And then here's my idea. Why not put a variable in? Put in an air variable capacitor. Just need 100 picofarads. It'll take all the current, okay? No sweat, so we don't have to worry about that anymore. And it'll allow you to adjust the SWR on 10 meters. The SWR can be pretty far off on 10 meters, and it is very much affected by the antenna. And if you're operating portable, where, you know, from one part to the next, the 10-meter SWR is going to change, wouldn't it be nice to have a little trimmer capacitor so you could zero it back out? So I think a great way for the do-it-yourself version of these things is to scrap the fixed capacitor, grab yourself a variable capacitor out of the boneyard here at Dayton this weekend. 100 picofarads is all you need. Put that in the box. It'll take a kilowatt, and you can tune your antenna up with it. So, and when the next one I build, that's the way I'm going. In fact, that's a picture of my capacitor, my variable capacitor. We are doing, commercially and at home, everything wrong. This is the inside of the commercial box, right? I also refer to this as an oven. We want to get the heat out, right? What things can we possibly do wrong to make sure that we cannot get the heat out? Well, the first thing you do is you put the heat source inside a closed box and you make sure the air does not circulate. That's step one, right? Any path through a metal like copper wire, you make as thin as possible and as long as possible so you can't get the heat out, okay? You take the cores, which is where the heat gets generated, and you don't let them touch the box. The box is not a good heat sink, but better than nothing. And usually there's no contact in these things between the core and the box. So what do you do to fix this? Well, you undo everything I just talked about. Okay. Unfortunately, you can't use a metal box. It'll detune the transformer. But we can attack this problem one piece at a time. Notice in the upper left in this commercially offered product, there's a vent. It's referred to as a vent. It's a pressure relief valve. It's really not a vent. Also, there are two 1/8 inch holes in the bottom of this device. The vent will not allow circulation of air. It's there to relieve pressure. But the two 1/8 inch holes in the bottom of the case relieve the pressure. The vent in this design is completely superfluous. Fortunately, the vent costs about $2. That's what those cost. They come from Amphenol too. And they're useless, right? Unless you try hard to seal the box, the pressure will relieve itself. And these don't provide for any airflow. So let's get rid of it. Down at the bottom is the Amphenol part, which is a pressure relief valve, not a vent. And you will find on Amazon other ones that you can get them like 6 or 7 for $2 on Amazon. These are designed for sprinkler system boxes outdoors. Okay, they are not designed for 1 kilowatt end-fed half-wave transformer boxes. So don't use those. it turns out Bud, the people that make chassis, makes a really nice vent. You look through it, it's pretty much open. And then if you go on Amazon, you can find things 1 inch in diameter, soffit vents made out of plastic, and they're about 20 for $2. Okay, none of this stuff's expensive. Use those. Put the soffit vents in the bottom of the box, put a real vent in the top of the box, and let the air circulate. The thermal capacity of circulating air is about 100 times higher than stagnant air. Any air you can get to move is a big plus. So here's a very good picture of a very ugly experiment. This is the prior end-fed transformer. I have mangled the side of the box to jam a pair of soffit vents in. If I was building from scratch, I'd put them in the bottom. I added one of the Bud vents in the middle of the box because I couldn't get it to the top. If I was building from scratch, I'd put it at the top. I still have a fixed capacitor down at the coax connector. The next time I build from scratch, I'm going to use a variable capacitor. And I took the transformer and I coated the whole back with heatsink compound and then forced it against the box using zip ties to get as good thermal conductivity between the cores and the box as I could. The cores are ferrite, which is 70% iron. They're not real good conductors of heat to begin with. And the boxes are PVC. And PVC is a terrible conductor thermally, but it's typically what we wind up with. So in that case, if you're going to scratch build and really shoot for 1,500 watts, try and get a thin case. NEMA boxes are 2/10 of an inch wall thickness. This commercial product is 1/10 of an inch wall thickness, which is a help. It's less thermal resistance. There are ones that are thinner, and you can thin them out yourself. If you have a drill press, use your drill press as an end mill and thin the case out if you possibly can. Here's some results. Running a 0.5 kilowatt. Remember, this device as sold to me was rated at 200 watts FT8. So, of course, in good ham spirit, I ran 500 watts because, it's what you do, right? Who runs 200 watts when you can run 500 watts? Okie dokes, what happened? Well, an FT8 on 80 meters, which is the worst case, running a 0.5 kilowatt, in 13 minutes it overheated. What happens is the ferrite hits a temperature called a Curie point, C-U-R-I-E, and it stops being ferromagnetic. And then the SWR heads to infinity. And it happens all at once. You can watch your SWR bridge and it's 1-to-1 and suddenly it's 100-to-1, right? You just hit the Curie point. The great thing about ferrite is you let it cool off, it fixes itself. So it's not a permanent problem. Let it cool off, get back on the air again. So I made some improvements. When I added some side vents, I got the overheat problem to 15 minutes. When I added soffit vents, I got up to 16 minutes. When I added the heatsink compound and jammed the cores against the case, I got up to 18 minutes. And that was about as good as I could do with this design, but you can do better, and I'll show you a way to do better. But if you have one of these already, you can do these things. You can add some airflow, you can add some heatsink compound, and you can improve the performance on 80 meters, which is where the problem is, and FT8, or RIDI. RIDI is worse than FT8, by the way. And improve the performance thermally considerably, and that may be good enough. That may be all you really need. Depends on exactly how much power you really plan to run and how much you're in love with 80 meters. For reference, I took the cover off. It's still overheated, and that's plenty of air circulation. That was 22 minutes, which tells me that there's no way to run 1 kilowatt through this thing on 80 meters, no matter what you do for cooling. You can make it much better, but you can't make it steady state. So here's the conclusions on high power, okay? On 40 through 15, you typically do not have a problem. The cores don't overheat. The capacitors don't see amps of current. You're probably good to go. This includes on ones that are only rated for 200 or 300 watts on FT8. You can push way above that. But on 80 and 10, you got a problem. On 10, you fix it by fixing the capacitor. That's straightforward. Just parallel up a couple of capacitors. The heating problem on 80, that's a different story. Even with good heat sinking, the classic transformer, which is 2.4-inch mix 43, 2 cores, will overheat no matter what you do on 80 meters if you go above 500 watts. So don't do that. Do something else, right? There's another mix 52. Take 3 cores to spread the heat some more, and because you're going to need the inductance, as mix 52 has less inductance, so you got to make that up somehow. Mix 52, the Curie point is up at 250 centigrade, so you can run them literally red hot, and that's what you do. You can run 1.5 kilowatts through a 3 stack of these cores, mix 52, and get on 80 meters and run. You want to run 1,500 watts on FT8 for some reason, you can do it. Or if you want to run single sideband in a contest with lots of compression for 48 hours, you can do it. Just use 3 cores, mix 52. The other little wrinkle here, your NEMA box that you're probably going to put this transformer in is made of PVC. It has a melting point of 200 centigrade, and you're going to run this transformer up close to 250. So you're going to melt the box. Well, you can fix that too. There's a polycarbonate box for sale on the internet. They're not much more money. And those melt at 300 centigrade. So you could build yourself a real high temperature 49-to-1 transformer and run lots and lots of power through one of these. Most of us don't think of this as a high power antenna, but most of us don't like the antenna failing in the middle of a contest on 80 meters. So you may want to make at least some minimal conclusions. The next few charts are basically lists. I would encourage you to go to k3lr.com and look at the charts. Here's a list of who supplies all this stuff, where you can buy them. DX Engineering sells all the components. They sell finished product, transformers, components, everything. Everything you need, the wire, you name it. There's little ones from qrpguys.com. That's a good vendor. And many, many, many more. Look at the bottom line. It says avoid Temu, Alibaba, and Amazon. There is ferrite for sale, really cheap, from these locations. And it is really junk. It's full of voids. It's full of cracks. You run high power on those, you will have ferrite dust in your box instead of a core. Do not buy the cheap cores from those sources. And a bunch of it shows up on eBay, of course, too. Stick with the good guys. Go to DX Engineering, or you can get cores from Mauser and DigiKey. They're top quality. They're made by Ferrite or Amadon, which are the top manufacturers. You know what you're getting. They're manufactured to drawings, and they work every time. They're not much more money. We're talking about small dollar values here. To build with the right stuff, don't build with the wrong stuff. You're going to just hurt yourself. I'm not going to read you this chart. Go find it on k3lr.com. However, the first line mentions a YouTube of a talk by K1RF. It's called the End-Fed Half-Wave Antenna. Good title. It's the best talk of 50 talks on the internet. That's the one to watch. If you got 15 minutes, go watch that. It will tell you much more about these antennas than I did, and it's all accurate. The science is good. It's all accurate. The physics holds up. K1RF knows exactly what he's talking about, and he's done lots of experiments. Okay, that's it for NFES. Real quick on PL259s. PL259s are made of 4 parts. The center pin, the insulator, the body, and the nut. Normally we have no trouble with the nut. It should all be silver-plated brass if they're any good. We sometimes have trouble with the body, and one of the things I've discovered is, I haven't seen any lately, but I came home from Dayton about 5 years ago with a bag full of what looked like good PL259s, and the reducer that screws in the back so you can use RG8X wouldn't fit because the threads turned out to be metric. No kidding. And they're probably still out there somewhere, right? And I'll tell you how you find them. The price is $1. If the price is $1, they're probably no good, right? So there are metric parts out there. There are chrome-plated parts out there you can't solder to. So there are problems with the body. There are problems with the insulator. They should be Teflon or phenolic. Sometimes you'll discover polystyrene. It's usually black. You heat the center pin drifts because polystyrene melts. But it's cheaper to make the part that way. And then the big bugaboo, the one that really messes people up, is the center pin. The inside diameter should be 1/8 of an inch, 0.125, plus or minus nothing. And for LMR 400, which a lot of us use a lot of, to go into the connector, it needs to be at least 0.12. And you'd sure like 0.125. If you use 3/8 inch heliacs, most people don't, but if you do, that'll go in a PL259 also, same thing. It will only go through the center pin because its center conductor is 0.125, no kidding. You need a correct center pin. You can make it correct. Grab a drill and a drill bit and drill the thing out from the back. However, I've seen these things so badly made, when you drill the inside diameter to 1/8 of an inch, you got nothing left, right? The wall thickness is gone. There is no center pin anymore. You're looking at the drill bit because the thing was so small and the wall was so thin, you can't even drill them out to get them to the proper size. The outside diameters are usually wrong too, and they're too small, which produces a very bad fit. When you marry it up with this. This is a classic SO239, same problem. You should have silver-plated brass. And notice I highlighted the Amphenol part number, which is stamped right on the side of this part. Old saying for us old-timers, Amphenol or not at all. And when it comes to SO239s, Amphenol's a good bet. They're sold by DX Engineering and lots of other people. You can get your hands on the good ones, for gosh sakes. These are $4. I went connector shopping this morning. I don't need any. I just decided to do some market research. I found good ones for $4. Okay, I found really crummy ones for $2. They were chrome plated. You can't solder to them. And this is what's called a 16V cut. You will notice there are 16 little notches in the annulus of the part. That makes it match up easily with a PL259. The $2 ones, and I'm not talking about flea market either. I'm talking about in building 4, okay? Real vendors selling real parts, right? $2 SO239s. They're not 16V cuts, they're 2 or 4V cuts. They're made out of chrome-plated pot metal. They will fail. They will not grab your PL259 sufficiently to make a good connection. And you will save $2 and cost yourself headaches like you can't believe. So don't buy cheap connectors. One more minute and then we're going to be off the stage. You ever wonder how they turn the corner inside an L or a T? I always wondered. And I took some apart. These are Amphenol. These are good. The male pin is threaded. The female pin is drilled and tapped, and they're screwed together. These are the ones you want. Whenever you use them, take a pair of pliers, grab the male pin, and turn it clockwise. Sometimes they're loose, and that's bad news, right? So tighten them up. Tighten the center pin up when you use the good Amphenols. The bad stuff uses a spring finger at the junction. Those always have resistance. At 1,000 watts, they heat up. When they heat up, the resistance goes up, and then they heat up some more, and you get thermal runaway. I've seen them get red hot. Don't buy junky L's or T's. They're guaranteed trouble. These cost more money. Good Amphenols, good Amphenol L's and T's cost money. Well, you can find them used all over the place, right, for not too much money. How do you find the bad ones? The bad ones have no specs, no drawings. The Amphenol drawing is on the web. You can go to Amphenol, you can go to DX Engineering, that drawing is on DXE's webpage also. I don't suggest anybody walk around with a 1/8 inch drill bit, but if you were to do that, you can test the center pins and see if the drill bit will go up through the center pin. If it is, you probably have a very good connector. If it's an Amphenol, the drill bit will go up the center pin. Take a look, the center pin should be molded in, not swaged in. If they're too shiny, they're chrome plated, you can't solder to them. About 5 years ago, we started seeing counterfeit Amphenol. Where'd they show up? Dayton Hamvention. I have since seen them in Orlando also. The way you tell the counterfeits, they don't look right and they cost too little, but also the ink is water soluble. Take your thumb and wet it, rub it against the connector, and where it says Amphenol, if Amphenol comes off on your thumb, here's the philosophy: cheap parts deserve cheap ink, right? So they use cheap ink on their cheap parts. Those are really bad connectors, but they say Amphenol on them, so be careful. And here's the big discriminator: and anything less than $2.75 can't be a good PL259. So that's what it costs at a zero profit margin to resell these things. So if it's too cheap, it's no good, right? Always test insertion force. When you stick a PL259 into a barrel connector, SO239, anything, it should fit tight. If it doesn't fit tight, it's trouble down the road. Make sure they fit tight. Avoid the mysterious ones. Buy from known sources. Avoid the L's and the T's if you can. T's we usually use in phasing harnesses. You got no alternative. The L's you can usually do without. If you can, do without them. They're usually trouble. Thank you very much for your kind attention. Sorry that was a fire hose, but yep.
And just give me a couple of days to get these slide decks up on k3lr.com, and we'll have those. Our next talk. Okay, yeah. I think that's for the clicker. The next talk is the Yagi turns 100. And please welcome back to the Antenna Forum stage, Greg Wardy, W8WWV.
Where'd my cursor go? Look on those. Yeah, truly the cursor's not visible on this screen. It was. I think I want to go to the very, oh, wait, there it showed up. Hello. Wow. Can anybody fix this? Because boy, do I need to see this. No, truly, I've got the PC screen here, but I guess my slides are up there. What kind of deal is that? Must be a test for me. I know what they are, trust me. But I would like to see them. Well, yeah, in all seriousness, how do I get my screen here to my slides? Oop.
Two separate screens. You need to set it. Are you the IT guy? I'll let you do it.
This is probably the wrong one.
Yeah. And get that full screen if you can.
See if we can get it. Is your, I think I've
It's a
lost it.
PowerPoint slideshow.
Is it the Yagi history?
Yeah.
It's like
That's correct.
It's very weird because it's not. Just
Oop. This could be good.
that work for
And then these things, get me? Thank you very much. Woo. All right, yeah. For my next act, my next trick, okay, let me see here if I can stay on time. Okay, the Yagi turns 100. We're going to go through pretty fast here. 2026 is indeed the 100th anniversary of the introduction of the Yagi Yuta antenna. And of course, it would be a big understatement to say this has not been a colossal part of amateur radio. So let's go back to the beginning and see how we got here. I'm going back real far here. Light waves. Obviously, visible light's been used and studied for as long as humans with eyes have been around. You know, duh. Mirrors and reflectors have been used to shape and direct light forever. A guy by the name of William Hutchinson added a parabolic-shaped mirror reflector to a lighthouse in 1777. And lenses go back at least 2,000 years. Eyeglasses go back to the 13th century. The telescope was invented by a guy by the name of Hans Lippershey in 1608. And interestingly enough, in 1729, a guy by the name of James Bradley measured the speed of light with an error of plus 0.4%, which I'm going to call very good. Okay, the key takeaways here, that light can be directed and focused with reflectors and lenses, and that the speed of light was measured with high accuracy in 1729, and in fact with reduced accuracy back even 1675. So by the 1800s, we already knew a lot about light. The first guy to talk about here is James Clerk Maxwell. I think we've all heard his name. He's primarily known for his 4 equations, which came out about 1861, 1865. He really had about 20 equations that were reduced to 4 by Oliver Heaviside, who shows up in all this stuff for many years. They unified electricity, magnetism, and light as being part of the same phenomenon, electromagnetic waves. And he built on the work of a number of people came before him. Now, his work predicted a velocity for these electromagnetic waves. And the equation he used in the upper right-hand corner here is based upon the permittivity and permeability of free space constants, which include things like farads and henrys. So you don't normally think of this to do with speed, but you do the math, work out the units, and you get a velocity. And it turns out that's very much the same exact as the speed of light that was already figured out, we saw in the past. So Maxwell concluded that light was indeed an electromagnetic wave. His work then also predicts that other electromagnetic waves at non-light frequencies should exist. Well, did they? With what properties? And what could they be good for? Sadly, Maxwell died without knowing at age 49. The next person who normally shows up talking about history is Hertz. And at age 29, in 1887, he took up the challenge to experimentally prove electromagnetic waves existed at other than light frequencies, and they followed Maxwell's equations. He started using sparks to generate very broadband RF, and then, of course, that was refined over the years. But this was his experimental setup. Some of his antennas here we might call have top loading or end loading on them. And he did other experiments that included reflectors. Now, when I see diagrams like this, I just feel he's being heavily influenced by light, because we already know a heck of a lot about light. So he has this big curved reflector behind what's a dipole. I don't know how visible this is here, especially back a seat or two, but there's a small dipole in there with this large reflector. Hertz had a lot of accomplishments. He experimentally verified Maxwell's theory. He measured the speed of non-light electromagnetic waves, the same as light. He invented the dipole. He discovered the importance of resonance. He produced and measured standing waves. He verified the properties of polarization, reflection, refraction, and interference. He found that his waves could go through buildings and fog. And of course, this was sort of the big thing that got people interested, especially if you're talking off the coast of England, where there's endless shipping back then, and fog and hitting the rocks and everything else was a big issue. So the fact that you could transmit through the fog was a big deal. And even if the thought was these go in straight lines like light, right? Still, you could go out 5-10 miles into the ocean, which would be an advantage. His work set off a tsunami of scientific and amateur exploration for what these new waves could be used for. They were first called Hertzian waves. And then around 1910, 1912, the name that got used was radio waves. And he was a good contributor to a bunch of other areas, and he died at the age of 36. Okay, Marconi, we all know about him. He really wasn't interested in science for the sake of science. He was interested in science for the sake of creating wireless telegraphy based upon Hertzian waves. He ultimately shared the 1909 Nobel Prize in Physics for his wireless telegraphy. And he was an entrepreneur and businessman as much as an inventor. And he was willing to buck the consensus that Hertzian waves, like light, only travel in straight lines, limiting the maximum distance. And of course, at this point, the notion that you could have DX propagation and bounce off the atmosphere and the ground clearly doesn't exist, because all we know about is light. Ultimately, he found success with low frequencies, about 350 meters, 850 kilohertz, with tall monopole antennas and grounding both the transmitter and receiver side. He's credited, therefore, with inventing the vertical monopole. And he was the first to span the Atlantic on December 12th of 1901, although most articles about this say that's probably didn't really happen like that, because the path was in daylight all the way from St. John, Newfoundland to Cornwall, England, all in daylight on 850 kilohertz. Give me a break, right? But, eventually it obviously worked. So his work set off a wave of commercial and amateur interest. Okay, a couple of quotes here. Maxwell has one I thought is interesting at the very bottom here, in which he writes to a lawyer, "I have also a paper afloat with an electromagnetic theory of light, which until I am convinced of the contrary, I hold to be great guns," which of course is the understatement of the millennium, right? Guys like Einstein go back to Maxwell as the major force behind them. Hertz here, when asked about verifying Hertzian waves, his line was, "It is of no use whatsoever. This is just an experiment that proves Maestro Maxwell was right. We just have these mysterious electromagnetic waves that we cannot see with the naked eye, but they are there." And he further went on to say, "I do not think that the waves I have discovered will have any practical application." Okay. Marconi was quoted as saying things like, "The coming of the wireless era will make war impossible because it will make war ridiculous." He is also quoted as saying, "Have I done the world good, or have I added a menace?" Tesla, of course, shows up in a lot of this stuff. He's an interesting character in history. I like the line where he says, "Marconi is a good fellow. Let him continue. He's using 17 of my patents." Okay. Now we got up to about 1900, so let's fast forward through the next 25 years. Obviously, a lot was happening then. Marconi's success drove most everybody down to very low frequencies, because that's where you can communicate long distances. The Kennelly-Heaviside layer, described in 1902, is really what we call the E region today, and now you're starting to get into propagation and how these waves can make it literally around the world for something that seems to want to go in a straight line. Spark equipment eventually gave way, thankfully, to true transmitters and receivers with vacuum tubes. ARRL was formed in April 1914, Hy-Vee Persam Maxim, Clarence Tuska. QST first issued December 1915. Crystal-controlled oscillators developed and patented 17. KDKA, the famous Pittsburgh broadcast station, 1920. The beverage antenna, 1921. And you're starting to see some broadside antennas to achieve higher gain, like the Bruce array and the Sturba array. And if those ever had a reflector behind them, it was more in the keeping of the thinking of the reflector, right? Just a big lot of metal, not resonant wires. Now notice 1925 is 60 years since Maxwell. So nothing about the Yagi antenna is obvious. Nobody else stumbled over it. And especially if you're focused on light, there's no good reason to think it would work. Now, one part here we'll throw in, the radioactive 1912. Our good friend, the Titanic, sunk on April 15th, 1912, probably to avoid income tax. It was not the first ship accident where radio helped in search and rescue of people. That was the Republic in 1909. But this showed people that the uncontrolled and unlicensed spectrum was the Wild West, and they needed order, not chaos. And that led to the radioactive 1912, then radioactive 1927, and finally the Communications Act of 1934 that led to the FCC. From the 1912 Act, here was the spectrum. And on the right is 0 hertz DC, and up to 187 kilohertz, that was allocated for high power commercial for long distance. The government grabbed 187 up to about 500 kilohertz for whatever governments do. And then above that there was commercial, standard commercial wavelength, and I highlighted the AM band in red at the bottom there. But ultimately at 1500 kilohertz, the same as 200 meters, everything above that was assigned for amateurs because it was considered useless at the time. So in some sense, I thank Marconi for dragging the world down there. Because, that gave us a chance to grab what's really great spectrum. And I'm almost surprised it was never taken back. And just call me a government skeptic if I say that. Okay, now after this radioactive 1912, it was estimated that 88% of amateurs disappeared because they didn't want to abide by that. Okay, here's the Yagi story we've all heard. The Yagi was invented in 1926 at Tohoku University in Sendai, Japan. It was designed mainly due to the work of Yuda. Yagi was the professor, Yuda was the student. Yagi spoke English and had previously spent time in the West. Yagi's name was on the patent in Japan. Yagi visited the USA in 28 and presented the Yagi design at IRE meetings. In recognition of who probably did most of the work, we should call the design the Yagi Yuda. And of course, we should. That is completely true, although it's rarely done. Goodness knows I ever do it. Okay, everything I just said is true, but there's some interesting details. Let's talk about Yagi and Yuda just for a second here. Hidatsugu Yagi was born in 1886, Osaka, Japan. It really should be pronounced Yagi, and I'm guilty of saying Yagi, 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 but Yagi is the right way to pronounce it. He graduated with a degree, Tokyo Imperial University in 1909. Then for a period of a few years, he did something I think very interesting. He worked with Heinrich Barkhausen in Germany. Barkhausen had the Barkhausen oscillator design. He spent some time working with J.A. Fleming in England, the guy who invented the vacuum tube diode. And then he followed it by work with G.W. Pierce, who had the Pierce oscillator at Harvard in the USA. So not too shabby. Of course, all this was interrupted by World War I. Amateur radios were kicked off the air as they were in World War II. He got a PhD, went to Tohoku, and that's his story. Now, at Tohoku, there was a need for improved communication between the Japanese islands and ships around the island. He received financial support from a private foundation in Sendai, and the focus was going to be on shortwave communication with directional antennas. Now, Yagi advised students Shintaro Yuda and Yuji Nishimura around 24-25. He obviously spoke English. They called their invention the wave projector. He was granted a patent in 26. As I mentioned, he came here in 28. Radio Corporation of America ended up assigned the patent in 32. Yagi went on for a few more things. Here's a picture of him. And the one on the right, I like to call the Letterman years because, boy, is he looking like Dave Letterman. He did die at age 89. That's pretty good run. And Japan Patent Office selected him as one of the 10 Japanese great inventors. Okay, Dr. Shintaro Yuda. He was 10 years younger, born in Toyama Prefecture, Japan. He graduated from Tohoku in 24. He began graduate school under Yagi in 24 again, so it means he was about 28 to 30 years old at the time of the invention. He did visit the USA in 32 for 2 years of study. He was appointed professor in 36. He visited the USA again in 51. And as the story goes, as he was coming into San Francisco, he was already seeing Yagi antennas for TV up on the roofs of houses. And he was sort of taken by that, like, gee, look at that. He died at age 80 a few months later. Here's a strange question. Yagi and these guys died in, 76. Did anybody meet either of them? Like, I was already a ham for 6 years. And, oh, good, then I can make everything up. Yagi was really a space alien, and he came from planet Manga. Okay. And here's a picture of Shintaro Yuda. He had no Letterman phase, as best as I could tell. Okay, if you've been asleep, you can wake up now. Notice received, you probably can't read this up there in that small writing, but received January 9th, 1926. Suppose that a vertical antenna is sending out electromagnetic wave in all directions around it. If a straight metallic rod of finite length be vertically erected within the field of its propagation, then the behavior of this metal rod will be as follows. When the length of this rod is equal to or slightly longer than a half wavelength, the current induced in it will be in phase with or lagging behind the EMF caused by the electric wave, and the rod will act as a wave reflector. If, on the other hand, the length be made somewhat less than a half wavelength, the current induced in it will be leading before the EMF, and the rod will act as a wave director. Now, let me go back, in fact. What else needs to be said, gang, right? I mean, there are 3 stinking paragraphs 100 years ago. There it is. I mean, it's amazing. True then, true now. And of course, based upon light as a reference for electromagnetic waves, who would think that would work? Now, what else was said in that first note or article and what wasn't said? They did write, according to the author's experience, a parabolic reflector is not necessary for producing a beam of radio waves. The simplest comparatively effective reflector may be formed as stated below, and it's, the rods. Now, what was left out? Well, any formal design approach like math, other than trial and error. It's a report of what they found with little y. And of course, much of future Yagi development centers on figuring out why and how the Yagi works. And then any mention of how to efficiently drive the antenna. Nowadays, we're all concerned about impedance matching right out of the starting gates. Back then, that wasn't talked about. But they had the key insight on directors and reflectors. The note also included a couple example designs. The work was at 68.135 megahertz. Now, Dan McGuire, AC6LA, modeled them based upon the information with Auto Easy and EasyNet, and the results closely matched the 1926 paper. Here's another one. And as far as I know, no other antenna at that time had that pattern as focused as that one shows, which is pretty amazing. Now, this one does have, you probably can't read this, there are 25 directors here, right? So this is a long SOB, but still very focused antenna. Here's some black and white pictures of typical antennas in their test range area. Now, I have to wonder, when I see vertical dipoles, again, is this all due to Marconi? Were people thinking, hey, you do things vertically? Of course you do, I'm Marconi. Okay, the revelation. What is the heart, the key of the Yagi design? I personally think it's the realization that the slightly shorter elements create directors and longer elements create reflectors. This is, of course, a very qualitative conclusion, leaving off lots of details. What are the lengths? What's the spacing, the diameter, the number of them? So it's a starting point, but it's a clear direction forward. Now, I wonder if Yagi and Yuda thought the same thing, because that's how they opened their paper, right? With those 3 paragraphs. And of course, once you understand directors and reflectors, then the experiments you could try are pretty much obvious and endless. So who's responsible for that discovery? Not Yagi, certainly not directly, but indirectly. How about Yuda? That's what most people say. Turns out, as best I can tell, it wasn't him. Now I've seen this in a number of pages out there in the internet. This is from an IEEE Cincinnati Section 2011 webpage. Here's what it says. Quote, Yuta initially used a resonant loop antenna and observed the directive radiation it produced. He then tried placing a parasitic loop near the driven loop in an effort to obtain a more directive beam. The idea for this arrangement apparently was suggested by an earlier investigation of loops of various shapes conducted by one of his classmates as a thesis under Yagi's direction. Oop, that's all the time I have, so I'm going. No, just kidding. Okay, now it makes sense that Yuta would have started with a large loop because they're inherently bidirectional, right? You all know that. So if you're trying to come up with a directional antenna and you're starting with the loop, you're already hitting the ground running, so you might as well start there. Again, their dipoles tended to be vertical, which makes them omnidirectional in the horizontal plane. Now, of course, you could ask, does this mean Yuta also invented the quad as we know it today, as soon as he put one loop in front of the other and noticed additional gain? Okay, ultimately, who's the classmate who conducted the original work? Turns out, say hello to Yuji Nishimura. He was a Tohoku graduate in March 24, classmate of Yuta. His advisor was Yagi. Now, his task was not to invent the Yagi antenna. It was to determine the resonant frequency of various shaped loops, triangular, quadrangle, and circular. Okay, he was just trying to measure resonant frequency. So what was his experimental setup? And of course, hint, an MFJ 259B was not available, right? Boy, would that have made this a quick thesis. I turned it on, I wrote the dial. It was 82 plus J0, bye-bye. Here's the picture. So there was an oscillator driving a vertical dipole. About 10 meters away, there was another dipole feeding a crystal detector, and then the device under test, DUT, was placed in front of the receiving dipole. Now let's see, I don't want to read all of this, but the natural wavelengths, okay, now remember the goal here was to measure the resonant frequency of the loop. Okay, and at the end, I think there are principles related to like grid dip oscillators, if you remember those, that might have been in play here. But to get down here to this, the natural wavelengths were measured by examining the rapidly varying values in the detected current of the receiving dipole and their dependence on the size of the coils. Another quick comment. In reading a lot of this old stuff translated from Japanese to English, coil is used for what we think of as like a single turn loop, right? If you say coil to me, hell, I'm winding wires like this, right? But in this writing, one turn, a loop, is called the coil. Okay, this experiment resulted in an interesting phenomenon. The presence of the single turn of a coil, a little shorter than its natural frequency, and of course, by natural frequency, I assume they mean relative to the test system, caused the current in the receiver to increase markedly, to exhibit a wave direction action. In contrast, the presence of a single turn coil a little longer than its natural wavelength caused the current in the receiver to markedly decrease, exhibiting a wave reflective action. So, what I think is funny about this is exactly what you would build if you wanted a 2-element Yagi test range. Right? You'd have a transmitter send a wave down, you've got an antenna in front, and then the detector behind it. I didn't know what he wanted to build, but that's what he made. Okay, both directors and reflectors were discovered. Of course, you got to think, what did it take to get us to this point? We needed tube oscillators with stability and bandwidth sufficiently narrow to resolve small frequency differences. It does turn out Yuta also designed oscillators, so the first one could have been designed by him. Crystal detectors were necessary with enough sensitivity and resolution to detect these positive and negative differences. And of course, these tools were only available in a few years coming up to 24 to 26. But I'll tell you, to me, what really matters is a curious brain and good lab technique. I've modeled this basic setup in EasyNet, and you can see why it looks like a 2-element Yagi. But my God, given what they were using, All I know is there must have been a day when that Nishimura guy walked into like Yuta's office, or his cube if they were modern, and said, hey, look what I found, dude. And I mean, again, it's mind-blowing. All right, what should we name this? Should it be called a Yuji? Maybe a Yuji Yagi? Maybe a Yagi Yuji, you know, all names here. And they also called it a wave projector, a wave duct, wave canal. And then, of course, I'll ask, is this all a big happy accident, right? Because in so many times in history, folks set out to discover one thing and stumble on something else, like America, right? Oh, there it is. From everything I could find in reading about this, the Yagi might have a somewhat similar story, but we all know that luck is when preparedness meets opportunity. So again, I'm not trying to say this was a big accident. I'm just blown away by what this was, because they had the whole thing in under 2 years. Okay, now let's see here. In theory, I should be done in a minute. What do I want to talk about quickly? Yeah, we'll skip to that. This was, I ripped off this picture in the left side from a website from VA3IUL. And if everything I've said doesn't make any sense so far, this kind of is the right way, I think, to think about it. In the optical world, with a mirror and a source and a lens, that really is equivalent to the 3 lines there that do have varying lengths. Now, an interesting question when you think about this is, if like light is 500 nanometers, 500 billionths of a meter, we're going to call that small. If you were able to make a Yagi that small, would it work at light frequencies? And the answer, as best I can tell, is yes. And I think some people are doing that. And if you said, my God, Greg, what gets that small? Ask yourself how they put 30 billion transistors on an integrated circuit these days. Okay, we'll go through this and then I'll stop. But there is a lot more. As Tim said, the slides will be up there. We're about halfway through. I go through a lot of antennas. You know, so many things, the quad, so many different types of antennas, Mach and rectangle, are all effectively Yagis. But just a prophet has no honor in their hometown. It seemed like people in the West embraced the Yagi as good stuff, less so in Japan. Yagi antennas were used very successfully in World War II by the Allies, but less so by Japan. Apparently, they were coming on near the end of the war. There's one Japanese author who writes that the Battle of Midway was an ambush, partly because of the longer range radar of the Allies. There's an interesting story about a British soldier, last name Newman, who in 1942 was manning the radar station in Singapore, which was then invaded by the Japanese, who got Newman, who got the equipment, who got all the documentation. So the Japanese were looking at that and seeing references to Yagi antenna and Yagi array. And so they dragged Newman back in for interrogation, and they said, you know, what's this about? Now, I'm probably going to over-portray this, but the reaction he gave was something like, he's one of you, which, you know, probably caught him off guard. I also think it's true, by the way, Yagi in Japan is translated also to goat. So maybe they thought this was the goat antenna, and no wonder it didn't make any sense. Yeah, there you go. Okay, and finally, and probably sadly from Yagi's Japanese ancestry, the 2 atomic bombs dropped in August of '45 both had Yagi-Yuta antennas to determine when to detonate, which was about 1,500 feet above ground. All right, well, listen, I really want to stay on schedule here. So again, there's a lot more here. Amateur radio, when they appeared, impedance matching, shortening the elements, multiple bands, NBS technical note. This guy here with a Leeson book at mechanical design. I do see Jim Breakall here in the front, WA3 FET. There's some stuff on the optimized wideband antenna. And what that gets you, step IR, Moxon. And of course, all these things are Yagi derivatives, right? I mean, when you look at all that, you think, oh my God, they're inventing new designs. Not really, they're folding wires creatively. Most all of these are a driven element and a reflector. And I do have a ton of, oh, and one last comment, then I will shut up. If you look in this March's QST, which just happened, there's an article from W2JAZ about a quaggy. So we see Yagian elements with a quad-driven element and quad reflector, and then a Moxie, which is a Moxon rectangle with additional directors out in front. So, you know, the stuff is still going on. Well, bottom line, it's amazing how the business about slightly shorter director, slightly longer reflector, it's 100 years old, but we're still using it today. I'll quit. Thank you. Good luck finding the next one. I'm not sure where that'll go.
You can't imagine the amount of research that Greg did on this talk, and certainly the slides.
And what I didn't research, I made up.
Well, you got me hooked. Let's roll on here. We still have two really good papers, and I want to encourage you to stick around. Our next topic is effective antennas without towers. Please welcome John, N1PGA.
If we have the IT assistance, I'd appreciate it. I'm looking for a presentation on that USB. Got it, and just help me make sure I get to. And where do we get the slideshow mode? Thank you very much. Good afternoon, everyone. Thank you. I'm going to give a little bit of a different presentation than the previous two that were really terrific. I'm an operator. I love to contest. I love to build antennas, and I'm going to show you what I've got, and I'm going to show you how I've done it. So I'm from Grafton, Mass, which is up in W1, 35 miles west of Boston, and a little bit north of Providence, Rhode Island. Licensed in '93. I'm an HF guy for all of the different avenues within the hobby you can take. I'm an HF guy. I'm a contester. I'm a DXer. I'm active on 160 up through 10, and primarily a phone guy. I use quads, Yagis, verticals, and wires, and I only use trees for supports, and I've been very fortunate to have some pretty good results. It started for me 28 years ago when we moved into this house. It started with these two bird feeders. Maybe an odd entry to a Dayton presentation, but turns out the squirrels in our neighborhood were very enthusiastic and very active. And pretty soon all the cute bird feeders that my wife and kids had put out were decimated by the squirrels, and that became my problem to fix. So if you look at the backyard from the side view, you notice phototropic trees. They're leaning into the sun. Some of them are pretty stout, and they serve to be a great place for ropes and pulleys for bird feeders. But being a somewhat creative ham, pretty quickly is what else could I put up there? It was pretty unpopular to have antennas hanging over the back of the yard. The domestic police overruled any antennas hanging in the backyard. But I'm going to go through these topics to show you where I'm from, the antennas I use, the performance numbers I'm using to say that, yeah, these are really effective. I'll show you some options of how you connect up and how you get them up and down in the air, and some options and considerations that goes along with doing this. And these other items too, we'll step through. I'll go as quick as I can to hold to the 45-minute allotment. Here we are today in Dayton, and there is N1PGA in Massachusetts, FN42DE, if you happen to speak fluent grid square. A closer look of my hometown. It's a New England hilltop village, and there's thousands of New England hilltop villages. We've got plenty of hills, and this is my hill right here in the middle. I'm about 150 feet above river and wetlands down below. I got great takeoff in all directions. There's nothing in town taller than my antennas. Looking down on my property, that's the lot lines. The antennas, we'll go through all of this, but one of the biggest advantages of what I'm doing is the antennas are underneath the crown. They're underneath the canopy, underneath the umbrella, if you will. And as a result, the antennas are shielded to a large degree from the direct effects of weather. The ice and the wind don't get to the antennas the same as they do if you're on top of a 100-foot tower out in the South 40. So it's a real advantage to me to be working in close proximity to the trees. They're at low heights. 45 feet's my tallest antenna. And ropes and pulleys are the way to get it done. LMR 400 is my feed line. My longest coax goes out about 170 feet. Inside the shack, I'm down to a single radio now, the 7610 fine radio, an old Alpha 99, and I use a desk mic just 100% of the time. I own all the headsets, but for a lot of reasons, and particularly the Heil microphone in conjunction with however my voice gets replicated and the way ICOM does their audio chain, however it gets done, the on-air results are, I will not change a thing. Antennas, we'll go through all of this. Over the past 4 years, I have focused exclusively on 10 meters just to take advantage of the solar peak. And I don't know what I'm going to be doing 11 years from now, so I wanted to catch it this time. And these are the antennas I've been using on 10. I do all of my switching right at the shack, right at my right hand to the side of the radio, based on the great components from Carroll, OK2ZI. So looking at the antennas, there's the lot. And generally, this is how they're distributed out in the backyard. It's a 2/3 of an acre lot. All the antennas are out back. And I'm at 485 feet. I have the luxury of running some beverages out back for such a simple 580-foot run of wire. They're just magic for me. On 10 meters, this is the distribution of the antennas I'm using. And let's take a look at each of them. I've got a tri-bander. It's the only commercial antenna I run. 12-foot boom, works terrific. There it is up in the air, and there it is lowered down on the ground. You can tell by the foliage, it's October. It's getting ready to be CQ Worldwide time. So with ropes and pulleys, I can lower the antennas down. This antenna I can get down to the ground in about 10 seconds. So I want to make sure the shiny parts are shiny. I want to make sure everything is bolted up. I'm going to make sure my weatherproofing, it turns out I'm not so good at weatherproofing. I think I am, but reality is I need to check each year at the weatherproofing. On 20 meters, over in the far right corner of my lot, is what I call the 20-meter location. Now, it doesn't show to you, and I've done the best I can with photos, but it doesn't show to you that it actually exists inside of a clearing. I cleared out about a 35-foot diameter circle, and it's actually a cylinder. It goes up about 65 feet, where I've pruned and trimmed limbs, and I can raise the antenna up to about 60 feet if I have to. The support trees are 50 feet apart. I have a pulley in each of the support trees. The pulleys are up at about 60, and I attach to the front of the boom and one line off the back of the boom. You'll notice the antenna is 2-element quad for 20 meters, this guy. It's only an 8-foot 8-inch antenna, but it's on a 24-foot boom for the mechanical purposes of support, and I'll show you all about that in a minute. I put a little reverse truss under to manage the sag. Here's a 26-year-old picture on the left. I always get a kick out of it when I hear the rumor that, oh, geez, quads, they don't last. They don't hold up. Well, I live on a hilltop in New England, and we get the nor'easters, and I get the ice and the snow load just like you do, but they sure can last. In the picture from last year, you'll notice the pine trees have grown up just a little bit in 26 years, and now I'm hiding a 6-element Yagi behind them. For 15-meter location, similar approach, a clear cylinder, about 50 feet tall. Support trees are 30 feet apart on this. Two pulleys up in the air. 2-element quad, 11-foot boom, only 6-foot required spacing for the elements. And another one of the then and now photos from 2008. Pine trees have grown in this location too, same antenna. On 10 meters, I've got this guy pointed to the Caribbean. 2-element quad. Only about 28 feet. From that exact point where the antenna is, from exactly underneath that antenna, it's all downhill for about 1.25 miles down into that river river valley. And this antenna is a terrific performer for me. I have, for whatever reason, lucked into the exact right height to be a big signal all over the Caribbean and into South America. A near duplicate version of that is my antenna for JA and KL7 and our friends in VE. On 40 meters, I use this 2-element array. There they are, looking at you, and they're in the trees, right? In and amongst the trees. They're in close, and they're 25 years old, yet they're only 1.25 inches at the bottom. These are skinny elements, and they are unguyed, yet they've been there for over 20 years, and I have every reason to believe they're going to be there for an awful long time. This array works really well, 2-element array. I took the time to put down 90 radials underneath each element. 80 meters for me is just a wire quarter wave vertical. It's a wire in the woods, so it's impossible to photograph, right? This is the elevated feed point. I can reach 8 feet, so my elevated feed points are 8 feet. Everything I do at my place is done with my feet flat on the ground. I do not climb, just by preference. I don't use a step ladder. I do everything I do 100% feet flat on the ground. I use 8 raised radials there. 160, a typical deployment. I've got a tall tree. I yield about 65 feet vertical on an inverted L. And I do 2 flavors of this. Out in the woods, I'll do an elevated feed point with 8 radials. And I always wanted to try ground radials. So in the past 2 or 3 seasons, I roll out 40 100-foot radials. And this guy slopes down to about 30 feet. And one evening after dinner, I'm cutting the grass out back, and the sun happened to be setting and highlighting just the support tree. So I took yet another picture. All right, here are my 10-meter antennas. So you can see almost every one of them. How many do you see in the photo? Did I hear a 0? No, come on. There's one right there. There's the first one. It's the 5-element Yagi. He's up at 45 feet, pointing west. If we walk out to the middle of the backyard and look back up, that's what he looks like. And over there is 2-element quad going to JA, also at 45 feet. Now these heights are coincidence. They're my oak tree towers. Next year, I'll be able to tell you they're at 45 feet and 4 inches because they seem to grow a little bit every year. And this one is the antenna for JA, and that's what he looks like if you look straight at him. If we walk out into the back corner, the right corner of my property, and go under the pine trees and look up, there's the 35-foot boom, 6-element Yagi pointed right at Europe. And around the corner, which is the one antenna you can't see, is the 2-element quad over the back corner of the garage. And the tri-bander on the ground, I don't have anywhere else to put him. So he's in reserve. And if anything else happens during the course of a contest, and if I'm pressing really hard for my best possible result, I'll go out and I can raise that tri-bander on one of the bird feeder lines, and I can recover any of those 4 directions and keep going in the contest. So in terms of performance, I think they're terrific because I've built them all and I put them up and I live with them every day. I think they're great. And I'm delighted with what I've got. And I'll change only very little with what I've implemented. But are they effective and what's the performance? I have 4 measurements, and I'll show contest results for 2 of my favorite contests here, ARRL phone and CQ Worldwide phone. When I was a low power contester, 100 watts on all bands, unassisted, I was very fortunate to get top 5 results. And in CQ Worldwide, as a low power, unassisted, all band contester, I got what you would say top 10 results, including a first place finish. I got a plaque on the wall, and I thank the North Coast contesters for sponsoring that plaque. I'm delighted to receive it, and it's in a place of honor. I upped to an amplifier in 2018, and I have fallen out of the top 5 as an all-band contester. I'm in the top 10. And in CQ Worldwide, I'm just now outside of the top 10. So I've got some work to do at high power. It's a little more competitive class. The last 4 years focusing on 10, I've had some very good finishes. My goal has been to win. I enter each one to do my very best with whatever the conditions will yield. And I've come close to first, but not yet. So I'm working on it. Now, I don't know what 10 meters will yield for us next season, but we'll find out. And I've had good finishes on these other contests as well. So from this measurement, I would say to you, yeah, these are pretty effective antennas. Certainly I contest with some enthusiasm. And yes, I'm in W1, but it takes some antennas as part of the equation, and mine are working pretty well. I was fortunate to be able to join the N1W team, activating N1W for the Worldwide Award program, and my team allowed me to kind of monopolize on 10-meter phone, and I wound up being the 3rd highest activator on 10 phone with 6,200 QSOs. It takes some antennas, part of the complement, to do that over a course of a few weeks. CQ Worldwide, I finished number 3 in the US. Here's the pins of all the different contacts I made to kind of give a visual to the result. That at that year was a 5-element Yagi, got all of those guys in the front, and I used 3 2-element quads for the rest. The Caribbean and South America from the little guy over the garage, a 3rd quad up in a separate tree going west out to VK, ZL, Oceania, and then JA, VE7, friends in JA in China off that one. So pretty good results from some humble backyard antennas. Another view of performance, I wanted to compare to some of the best guys I know. K5 Zulu Delta, Randy, at this time was a neighbor, 9 miles down the road. So he and I, although he's a different caliber contester, and he's got certainly a different caliber station, but he and I are going to see the same propagation. And it doesn't help me to compare to the big stations in the hill country of Texas or the guys in the West Coast. I wanted to compare to somebody in close local, and Randy's right down the road. And I wanted a big powerhouse, super heavyweight. And of course, W3LPL on the East Coast was the guy I went to first. This is reverse beacon network data aggregated over in Valencia, Spain by EA5 Whiskey United. And I'm looking at 20 meters, I'm in blue, and without any detailed attempt at analysis, I'm clearly in 3rd place. Not surprising, not unexpected, but a little closer look shows, wait a minute, my 2-element quad hanging in the trees was the loudest signal in Valencia a couple of times. From that, I said, wow, okay, unexpected, how about that? On 40 meters, again, just a quick look at the color, eye-opening. I don't go to 40 often. I don't do well on 40. My numbers on 40 meters in a contest are always lower than everyone else. I've not been aggressive enough, I guess, on 40. This tells me I need to go there more often because my 2-element array in the trees does pretty well. On 80, similarly, interesting to see the blue color go from 0 to hero. And I had a real Godzilla moment there on 80. I don't, I must be just the exact right distance at that moment in time to Valencia, Spain. Now I was encouraged, let's add K3LR, who won this contest by a mile. And they're in there banging it out the full 24-hour period in this chart. And yet there were still a few data points and where N1 PGA, the 2-element quad in the trees, was heard to be the loudest signal in Valencia. Interesting. I offer that as some proof points that the antennas work really well for me. So let's go right to how-tos. How do you get them done? And the first stop is a spatial or dimensional view. If you're going to get out into the trees in your backyard, or if potentially you're going to do this in a park or you're in a summit area, you're in proximity to the trees, how much room do you have to work with? A Yagi on 20 meters, he's looking for 36 feet on the reflector, guaranteed. Probably an 18-foot boom or an 18-foot boom length or longer. And that results in a pizza box that you've got to be able to fit into the space that you might want to put the antenna. Whether it's a moccasin or a log or a trap tri-bander, this is generally the space you need clear enough to operate amongst the trees. And contrast that with a quad, only 18 feet wide, only 9 feet of a boom length. And when you look at the volume of space, how much clearance do I need in and amongst the trees? I think it's the quad should present itself to you as a really valid choice. It may not, it may not be the first antenna that you think about, but in proximity of the trees, I got to tell you, it's a great option. So suspending and connecting to the antennas, I've really got two main methods and two variations. The first is a simple single pulley, one connection point on the boom. And then the other primary option, you do the same thing, but use a second tree and connect to both ends of the boom. And then the alternative is you come down to the boom and connect front and back, a 1-into-2 connection, a Y, a harness, a yoke, if you will. And then similarly, 2 pulleys, but 1 connection, a 2-into-1. Looks to be particularly effective for a hex beam. My terminology, this is the lifting line, does the work of lifting the antenna. The pulley line, obvious, up above. You put a tag line off either end of the boom to hold the azimuth direction to generally what you're looking for. And it also adds a little bit of stability to the suspended antenna. It doesn't matter whether you're suspending a Yagi or a quad or a hex beam. There is a point I want to point out here that I think is particularly important, and it's what do you do with the rest of the pulley line? Now, when I'm putting an antenna up, my eyes are on the antenna. This is the business end of the circuit. So I pay attention to the antenna. I built it. I try not to break it before I get it in the air. And then the next interesting object is the green lifting line, because that's the one I got to be sure I hold it up. Everything is dependent upon the pulley line, on the lifting line. But don't forget about the pulley line. You throw it over the branch, tie it off, and everything else proceeds beyond the pulley line. But you've got to think here that there's some jeopardy. And I'd ask you not to route the pulley line in this direction, not right over the branch down to a hard point tie off on the trunk. There is a reason why, as best as you are able, I'd like to have you route the pulley line down the limb as far as you can to the trunk and then down to the ground. There's potential for abrasion where that pulley line goes over the branch. When the pulley line goes over the branch in tension, you will damage the tree limb, the cambria, the vascular system of the tree. You could potentially break the limb. So routing it as best you're able it looks awkward. It's not too terribly difficult to do, but I'd ask you to strongly consider doing that. The alternative suspension coming down with a 2-point harness, it works well on these lightweight quads. one pulley line, 2 connections. And there are alternatives. If you need extra clearance, you can do a simple redirect on that upper pulley, move that lifting line out of the way. And what I prefer to do now is just simply route it straight down to a weight, straight down to the ground. It's the easiest method of all. Looking at the 2 pulley, 2 tree option, simply the same story, duplicated at the far end of the boom. Now, I learned a lesson along the way. I'd like to think I would have thought this through a million times in advance, but I did not see this one coming. The sky's not the limit. The sky's not the limit. I made the clearing. I cleared out brush. I limbed some trees. I made a clearing that went way up. This is going to be great. I built the antenna. I routed the lines. And I started lifting the antenna up. Now, as you would expect, you begin to pull the lifting line up, and the amount of pulling force that you exert results in lifting force to the antenna. Things are great, just like you'd expect. A little bit of the way up into the air, you notice things get a little bit funky. Things are a little bit different. But that's all right. I'm looking at that antenna. It's the working end of the circuit. This is going to be a good one. But shortly thereafter, things come to a screeching halt. And you can't get the antenna any higher. So what does a backyard engineering ham do? Well, I pull harder on the rope, right? Something's wrong. I'll just pull harder. And you look up and you see the branches begin to bend in. You realize, uh-oh, there's jeopardy right here. Obviously, this is not right. So I lowered it down. I went back and sat on the deck and thought about it, and it became clear that it was all pull-apart tension, to go back to that. At that point, you're pulling, trying to lift, but the lift line is just trying to rip the antenna apart. So there's an upper limit beyond which you simply cannot go. So the side view of that type of antenna is right here. And this is an important point. One of the few very important points this afternoon is that there is a thing called the right angle. It is the place where you have the right amount of tension. It's a place where you have, in conjunction with how high the boom is, how long the boom is, there's a place where the antenna is going to sit. You can raise it easily here, and it's going to sit right there. It's going to sit right in that spot because the 2 lines at that angle are opposing each other. If the antenna tries to swing to the left, the right side is opposing that, and it holds it in place. It's such a simple thing. But when you do it, you'll see it, and almost immediately you'll get the same comfort I have that this is good. This is a solid implementation. This is the way it should be. And it'll ride through the wind, hold all the weather weight that you want. So we'll be looking for the right angle. If your trees are a little further apart and you've got the antenna that you want to put up, well, you now know you can't get it that high. So what does one do? Well, one does this. One extends the boom to reach where you can maintain that right angle, that comfortable opposition or comfortable amount of tension in the system. So an extended boom is what you saw in the 20-meter quad. Looked a little funny to have a quad sitting in the middle of this extended boom, but it's done for this purpose right here. So there is a sweet spot. If the antenna is low to the ground, you've got a lot of wire, there's a lot of play, it can wander. If you get it up higher, it'll get close to that tension spot where it's bad news. Here, there's a sweet spot. So be aware, look for it, find it when you raise your antenna, find that sweet spot, and then maintain it. All right. If you have a shorter antenna, we'll go through this quickly. A shorter antenna, like my little quads, you could do the same thing. This is how I discovered the problem of tension. The antenna I built, I put the eye hooks in too close. The angle is wrong. I didn't know it at the time. Figured it out when I couldn't raise it high. And I wound up putting an extra boom on it, and that's the angle that resulted. And it looks, this is a little bit backyard engineering. It's not pretty in any regard, but boy, it's sure functional. I can raise that antenna up. This is what, so I'm embarrassed to admit it, but it is the way it is. This is what the antenna looks like nearly 20 years later. There was no reason for me to change it. It's a good physical construct. Here's an antenna that looks terrific. That's the plan. I know I need to maintain the angles. That's the height, but uh-oh, there's something in the way. What do? Either you get your chainsaw out, if that's allowed or permissible or wise, or you go offset on the boom. Symmetry is nice. It's not required, though. You want to move away from obstructions, and if you have a quad, they're great antennas. Boy, they put out a big signal, but they're rascals. They're going to try and grab any twig they can. They're going to smile right at you, but at the same time, they're reaching out to grab a branch, and it only takes 2 or 3 little leaf cluster at the end of a twig, and you're going to be frustrated because you're going to have to deal with that. So moving it away from obstructions would make sense, so don't hesitate to do that. And again, a 2-to-1. Now, I highlight for you here that I've moved the pulleys up in this design because there's going to be sag. This antenna, the way you see it, is getting close to that high tension. It's going to pull apart if you try and go any higher. All right, this is some fun. This is some good stuff here. This is the Force 12, and I've got a little short boom extending up above the mass. And I don't know if this is physics or gravity. I don't know if it's lever arm, pivot point. I don't know how you describe it. But this is real magic for me when I first did this. It's about 18 inches above the boom. You see it's offset. Easy to do. The elements are parallel to the ground. The boom is parallel. And similarly, I'm attached above this boom. This is a 22-foot Yagi boom. And yes, it's really ugly backyard engineering, but it establishes a connection point for the rope 10 inches above the boom, which proves to be enough. And let me show you here on the world's worst home video. I can't show you, apparently. I apologize. I don't know why that is. So fundamentally, that establishes a point for the antenna to float. One rope looks wrong when you see it. You can't suspend an antenna with just one rope. But by raising the connection point 18 inches above the boom, gravity holds it in place. Leverage, call it what you will. In that video, I deflected the boom down 12 to 15 inches. I just bounced it down. And again, the advantage, I can lower the antenna down in 15 seconds. I bounced the boom, and by the time I reached and grabbed the little tag line off the end of the boom, the antenna had already begun to stop oscillating and was coming to rest parallel. And with just a little fingertip pressure on the tag line, it negated all the antenna motion. So I wish I could show it to you. It's really cool to see it. It instills confidence that, wait a minute, this is a survivable way to go. The other video is what I call wing waggle. I tried to bend the elements, push the elements down, and there is just so much imbalance with that connection point up above, it goes back into steady state almost all by itself. So it makes it, and you can take it from me, I've been doing this antenna this way for 20 plus years. It's survivable. When you see it ride in the wind, you get that same sense of confidence that this is good. This is going to work well. On the little antennas, I've been so informal as to just tie a simple loop around the bracket, and it holds the antenna in the same fashion as that Yagi. It does not rotate. There is no axial rotation. It does not spin, and a tag line holds it in the direction I intend it to go. I use a 1 down to 2 yoke on this antenna. Above the boom on these other antennas is simply an eye hook run through it. About 2 inches above the boom is all it takes. The antenna does not rotate on its axis. And because it's in comfortable opposition, it doesn't move very much on its own. All right, dealing with the wind, this is the approach the wind has to take to get to my 35-foot boom, 6-element Yagi at 60 feet. All right, you can see it's hidden in and amongst the trees. Now, my man Gary in County Meath, Ireland, The wind coming to his antenna gets a good running start, and here's a hard working step IR. And he knows all about it every time the wind blows, and you compare that to mine being in proximity, in and amongst the trees, it can work very well. And this is not to scale, and I'm not an aeronautic, and I'm not an engineer of any type, but I want the antenna to move in the wind. It's similar, and Charlotte would know more about this than I, similar, I think, to a windsock at an airport. A little bit of wind, you get a little bit of motion. A lot of wind, you get a little bit more rise out of the windsock, similar to the antenna. I want it to move. It's allowed me to build the antennas with a little thinner, a little skinnier schedule of tubing than any commercial antenna you're probably going to find, be it fiberglass tubing for the quads or aluminum for the Aggies. And so being a little bit lighter antenna is a good thing, and it helps them survive. You put a tagline off the end, it controls the direction you want to point it, it stabilizes that motion that much more. Throw it on the other end, perfect if you think you need more stability. If you don't have room to run the taglines out, drop a line, a Y in this fashion, straight down, pull it off to the side 45 degrees. Now you've got one line stabilizing the boom and holding your azimuth direction. Easy. I use a little marine rated bungee cord as a snubber, and it's working pretty well. All right, we're getting close to the end here. I have some short circuit off ramps. I want to show you the notion of fast and easy. As I mentioned, I can raise the antennas quickly, less than a minute to bring down the 35-foot boom. And there's a lot of advantages. If I want to look at it before a contest, it's down at shoulder height in front of me in 60 seconds. The little antennas from 45 feet come down in 15 seconds. If there's heavy weather or something going on I didn't know about, I can get the antennas down and put them on the ground in short order, be it the Yagis or the quad. So fast and easy. For me, it's the great Yagi experiment. And I really enjoyed Greg's terrific presentation. But for me, Yagi started in 2022. This is the first one I built. I put it up and it worked great for this contest. I was excited. I made it a 5-element Yagi for the next contest 4 weeks later. I was motivated. I made it the 6-element. So you can begin to think of, well, I'm actually putting a boom in the air, not an antenna, because the antenna could be a quad today. And in very short order, I can make it a 6-element Yagi. So I'm putting a boom up in the air as much as I'm putting an antenna in the air. I lowered it down because it's an experiment. It was new to me. I left the quad brackets on the boom. And I got to tell you, I'm the kind of guy that I need to measure twice, 3 times before I cut or mark anything. I taped the tape measure to the boom to make sure I got it right. I did the work at shoulder height. I checked it 2 hours before the contest. This is great. And they work great. And yeah, it's 10 meters. It's the peak of the cycle. I've got a good antenna at a good height, but I was able to run 701 people in a row, 5 hours and 20 minutes on 28,353. I've never done anything like that. I couldn't believe it after the contest. I looked at the log reports. And then the 5-element, I finished number 2 in the world, number 2 in the US on 10 meters. And I ran 972 people in a row over 7 hours and 30 minutes. I've never done anything like that. And as a contester, you might wonder if that's wise strategy. Had I known it was 972, I absolutely would have gone for 1,000 just to see a big number of a run on one frequency. So, you know, they are effective antennas. They are easy to build. And the advantage is that you can build at ground level, a shoulder height. When you're building your antenna right here, it is a real advantage. You can do your setups, trial fittings, do the iterations with the analyzer. If you're tuning, you're making fine adjustments. Easy to up and down the antenna. You can vary them as I have. I have multiple presets. If it's a contest, I'm going for battle height. If it's heavy weather, I'm going to put a bit more slack in the system. And then options. Looking out the picture window in the morning, a cup of coffee, you look up and you say, oh, it's a 4.5 element antenna today. Something happened overnight. Let me get after it. And again, you would wear out your climber and your ground crew if you raised the antennas up and down as many times as I have with ropes and pulleys. I think the biggest benefit is it gives me year-round access. My wife sends me out to refill the bird feeders without concern to what the weather is. Hot, cold, day or night, winter, summer, doesn't matter. So same access to the antennas. I see the same stories that you guys see. Oh, geez, the rotator stopped rotating. It'll have to wait until springtime. Well, come on, man. It's December. What are you going to do until then? So I've got great access, year-round access. All right, here's one of the off-ramp buttons. Let's go back to here. Quick, let's look at the top secret files. I like this one. I like this one a lot. This is a current project of the N1PGA R&D group. We know so I've got the cylinder, I've got the antenna, I've got, everything's wonderful. I got the angles. I've raised the pulleys up for this project. And we know a longer boom reaches further to the lifting lines. All right, we know this. You covered that. This is great. This is easy. And so now with a longer boom, I can maintain the right angles at a higher height. Perfect. This is good. But what's the next opportunity? What do you see next? What's right in front of you next? What if the lower antenna didn't go away? What if I did this? I know how to suspend antennas. And this is not particularly heavy antenna in any regard. 10 meters is fading, 15 meters may be my band of choice. I can have one physical location, 2 antennas. But beyond having a duo band location, what if I did this? What if I stack these guys together? I read all the contest summaries, I read all the notes. I don't know of anyone stacking antennas into Europe without a tower. Now, do I have the right height? I don't know. I'll find out. And if I can do 4/4, I can do 5/5. And if I can do 1, you might be surprised that I've identified 3 different locations where I can stack antennas. Now, I got 4 areas of interest: Europe, Caribbean, South America. I need to go west to VKZL. And I need to do the best I can for our friends in Japan. So I don't think that I'm really restricted as much as you might think when you see, oh, antennas in the trees. I've done well with contests, and I would encourage you to think outside of the box. One of my final slides here, all of the slides will be on k3lr.com. But I'm going to need to end here pretty quick. So what if I wanted to maximize a location? And once you see this, you can't unsee it. You cannot unsee this. There's some unused area right there. And, well, it's relatively free and clear. So what does one do? One extends the boom. You put elements on it. And now you've got a monster pointing in one direction. You have to have the right spacing, of course. There's some considerations, but this maintains the right angle. This adds hardly no weight. This is easy to do. And this is the #1 project at N1PGA. That's the end of my 35-foot boom, 6-element Yagi pointed to Europe. Generally, that's where the pulley is, and pulley line and the lift line routing. But there's 6 or 7 feet off the back, and there's 6 or 7 feet off the front. So you might find someone you know on the phone to DX Engineering, order up 2 more 6-foot pieces of tubing, extend the boom, and make a monster. So easy to do, my friends. Tim, how are we on time? Are we close to the end? All right. Thank you very much for having me. I appreciate it, and I wish you the luck of building a good antenna. Yes, please. Sir.
Yeah, well, we can't hear anything up here. I'm sorry. When you go down, maybe you can get one-on-one.
I did hear the question. I am restricted by my wife's tolerance. No, sir, I'm not.
Yep.
Go ahead and shut that down.
Okay, our final presentation here this afternoon, the C-match method of phasing vertical antennas by Lee Barrett, K7NM. Hello, Lee.
So work as far as a pointer?
Should.
Oh, okay.
Stay up on the mic.
Hello, everybody. My name's Lee Barrett, and let's see if we can get back into the presentation here.
Try and get it going. You gotta use the clicker, all right?
Yep.
Don't mess with it.
I didn't.
Okay?
Okay. Number one, thank you for sticking around. Thanks for sticking around for this presentation. I know that I'm in a bad spot because I'm between a bunch of hungry hams and dinner. So we'll see if we can't make some fun out of this. Introduction, I have a master's degree in electrical engineering from Montana State University. I got enamored with phased arrays when I was in graduate school. I had to do a project to get some graduate credit in antennas. So I went out and measured the local broadcast station that had a 5-tower inline array and ran 5 kilowatts. It was interesting to do. I took a small transistor radio and put a detector on the IF and made an S meter out of it. And back in those days, you just had to get county maps and draw a circle around the station. And then I went out to the different intersections and measured the signal strengths, and therefrom sort of plotted the pattern as near as I could get it. The thing that really struck me was during the day, they were totally omnidirectional. During the night, however, they were 5 towers directional, and I was sitting less than a mile from the center tower while they were running 5 kW, and I couldn't hear them. I mean, they were just completely gone, and that impressed the heck out of me. So I thought, well, maybe that's something I could do with my ham station sometime. So, got a question for you. What is the purpose of phasing antennas? I hear directivity. Gain? Okay, well, let me stop you there because it's not for gain.
Phased arrays are for nulls. Phased arrays are from nulls. The gain is a byproduct of taking the energy out of the null and putting it into the auxiliary lobes. And that's something that is a little bit hard for people to understand. But what we have here is an isotropic source over on the left. That is basically a make-believe BB that radiates equally in all directions. Okay, and if you go out a mile and measure the field strength, it's going to be the same in that entire sphere. Okay, so now we take another BB just like that and we put it a quarter wavelength apart and we feed the one to the right 90 degrees phase delayed from the one on the left, and we get a null back toward the left. And the excess energy from the null goes out through the sphere on the right, and that gives you your gain. Okay? And that's why broadcasters use phased arrays, because they have to protect other stations at night. And so they have to very precisely position the nulls. So here's the phased array basics. First, you have to kind of figure out what pattern you want and know that the gain byproduct is a function of the null. Number two, the position of the null is going to be made up by the spacing of the antenna and the phase delay between the antennas. And I'm just talking a two-element array today because it gets really complicated if we go any more than that. Okay, and then the depth of the null is governed by the balance of the power between the two antennas. And so if you want the perfect null or the best null you can get, then your power has to be completely balanced between the two antennas. Okay? So I happen to be a chief engineer of two radio stations in Havre, Montana, where it's colder than your mother-in-law's kiss. During the day, we had a pattern that went to the southwest. And you can see up there that Havre was southwest of the two antennas. So our major lobe was over the city. But at night, we had to switch, and we had to protect a station in Kamloops, British Columbia, and another station in Logan, Utah, at KVNU. Now, if we had perfect power balance, there would have been no signal over our city. And so the way that we got that minor lobe was to unbalance the power by about 5%. And that gave enough signal over a back lobe to be able to cover the city. Okay, so what are the advantages of phased arrays? First of all, no tower climbing. And I never wanted to be a tower climber. So that's one of the reasons I was really interested in the phased array. I don't know why this is messed up in format, but give me a break here. No mechanics to deal with, but you do need an excellent ground system, because what that does is it pulls the vertical radiation pattern down. And that's what you want, is a low angle of radiation in the vertical, especially if you want to work DX. And the other thing is that you get really good rejections in the nulls. It'll rival, in fact, beat a Yagi in some cases. So I'm going to show you how I went about over 25 years using the different laws of physics, broadcast methods, and amateur radio methods to come up with a way of actually building a phased array that doesn't take $100,000 worth of test equipment to align it and works really, really well. It's going to cover a little bit of linear circuit theory, some transmission line theory, and some antenna theory. And I'm not going to go too deep. There is some vector algebra that goes into this, but the good news is that I do have a book that's carried by DX engineering on this particular topic, where there's a CD in there, and I have all the Excel spreadsheets, so all you got to do is plug in the measurements you made, and it calculates everything for you. And so anyway, with that, we'll get started. So this is my east pattern that we're going to talk about today. I live in West Point, Utah, just north of Salt Lake City. And I wanted a pattern, which I went to one of the textbooks and looked up, where I had a null that was going to Seattle and a null that was going to Los Angeles on 20 meters. And I'm sure you can't imagine why I wanted nulls in those directions, but I'll leave it at that. So the major lobe of this thing actually ended up going east. So I was getting into Europe and Africa pretty well. And that's what I wanted. So spacing of the antennas was a quarter wavelength on 20 meters, about 17 feet. And the phase delay that I needed to get those nulls was minus 95.3 degrees. And so when you measure those, you have to do it with the velocity factor of the coax, but we'll get into that in a minute. Okay, this is the way broadcast stations feed their towers. And it's full of inductors. You have a tuned circuit that's tuned to the frequency of the station, and then you have these Jeep coils that tap the main inductor to get the power levels, and those come out at the same phase, and then one of them goes through a phase shifter, which is that T-network. Then you go through your coax and you get out to the towers, and you have L networks out there that have to tune out the mutual coupling between the antennas and match the impedances and split the power. And all of that is you can imagine is very complicated. If you've ever thought that you could just take two resonant ham antennas and stick them a quarter wavelength apart and put a 90-degree phase shift coax on it, you're going to find out that A, doesn't work, B, the SWR is through the roof, and a bunch of other stuff. So anyway, so I'm going to show you how we can go about putting this together with a different approach. And not only that, this is very narrow bandwidth, because an AM station is only 30 kilohertz wide. So your tuned circuits for this phasing system is very narrow banded. So you got a lot of inductors in there. And oh, by the way, my station was licensed for a kilowatt output, but at the common point where your power goes into the phased array, I was licensed to put in 1,250 watts, because the FCC knew we were going to lose 250 watts just through the networks and the coils and everything. And the problem with ham radio is that the FCC is not going to say, oh, well, you can run 1,750 watts. No problem. We know you're going to lose 250 in your antenna tuning. It doesn't happen that way. Okay. So here's one of the approaches that I've seen in one of the amateur publications. It says, okay, this is how you phase antennas. Well, if you do the math, in order for this to work, the voltage going to the antennas at VS has to be equal. And to get a network where the L and C give you the phase shift you want, and then have the voltages equal at both ends of the inductor, is virtually impossible to do. And to adjust your things so that it could do that, just it can't be done. So very hard to tune this. All right, so let's get into how we do it. And this is where we get into the transmission line theory. Okay, so we want power to be equal to both antennas, right? So what we do is build a power divider. And the way we can do that is to take 2 quarter wavelength sections of 72 ohm coax and put it to a T connector. Because when you take 50 ohms and you rotate it back to the T connector, it comes out at 100 ohms, and those are both resistive. So there's no reactance in it if it's exactly a quarter wave. And so that gives you 2 100 ohm
loads in parallel, which gives you 50 ohms to the transmitter. All right, so that's how we build the power divider. It's really quite simple to do. If you have a VNA, all you do is cut it for free space, put a connector on one end, hook it up to your VNA, and then start trimming it, because the opposite end of an open circuit will show up as a short circuit on the VNA end. So you can just trim it until your X goes to 0 and your R is at a minimum. And that's how you get your quarter wave section, and you're done. Okay, the next thing you do is you take your 50 ohm coax and you run it out to your farthest antenna. And that length is arbitrary. You can make it any length you want, but it's 50 ohm cable. And then you cut another piece that's exactly the same length that goes to the other antenna, which is closer. But those two lines have to be equal length exactly. And that gives you the symmetry so that the power divider would be feeding 50 ohm loads at both antennas with the same amount of power and in the same phase. All right, and the next thing that we do is we calculate what 50 ohms worth of phase delay is, and that's 93.5 degrees is what we want. And so what you do is calculate what frequency would give you a quarter wave at 93.5 degrees, and then you do the same thing you did with the 72 ohm coax and put a connector on one end and trim it off at that new frequency so that you get 93 degrees or 93.5 degrees exactly. So then you place that in the line with the antenna in the direction you want your major lobe to go. So in this case, that was the east line for me. And so that's where the phase delay goes. So right now we have a power divider and we have the phase to the antenna that we want to have the major lobe go out. And we also have the same power going to another 50 ohm load on the other side. Well, now all we need is for the antennas to be 50 ohms, and we're home. All right? So this is where life gets complicated. So we got our feeder system all ready to go. Okay? All right, so let's start with the antennas. This is the way my phased array is set up. I have 45 radials. It's looped. You have a loop around the base of each vertical, and then a outdoor loop all the way around the outside with a divider through the center. And you run your radials from the loops around the antennas out to the dividers and to the terminator. And under a study that was done in broadcast antennas, it was found that if you have 15 radials, you get 83% efficiency out of your vertical. And by the way, it makes them really quiet. You know, verticals are always said, oh, they're noisy. Well, they're noisy because if you don't have enough ground under them, they are. But 15 radials minimum. So what happens if you go to 60 radials? Turns out the efficiency goes to 85%. You gain 2%. You go to 120 radials and you get 87%. And so why does the FCC have you put 120 radials around a broadcast tower? Well, the reason is because if you've got a phased array and you have to keep another station protected, then they know that your radials are going to break over time. They're going to corrode and break. And if you lose too many of them, the base impedance of your antennas is going to shift and your pattern is going to go to pieces. And so they want you to have lots and lots of radials in there so that over time you don't have that problem. Now I put that web all the way around on the outside for two reasons. First of all, if any of my radials break, there's an alternate path for the current to still get out into the radials. And secondly, if you take a lightning strike a quarter of a mile away, you're going to have a voltage gradient that goes through your radials. And when it hits those radials with these loops in here, that causes the voltage to change to a circulating current. And the circulating current causes the radial system to go up and down at equal voltage. Whereas if you just have radials out there, you're going to have a voltage difference down your radial. But with the loop currents, the whole thing goes up and down. So if it goes up 1,000 volts above ground, who cares? Because everything that you've connected to it is at the same potential, so you don't have any damage across the potential there. Okay, so how do you put in a good radial system when your grass is already in? Well, here's the answer. You go down to your local rental store and you get an edger that has a saw blade on one side and a wheel on the other side. And you start that little guy up and you go to the base of the antenna and you take it backwards through the grass. And it puts a nice little 1/4-inch slit down into the grass. And then you can put your radial down in there and use a paint stick to push it down into the hole. And after a month or two, it's all grown over. And so it's all ready to go. Okay, here's one of my 40 meters antennas. This one is, I make them out of 3-inch diameter aluminum irrigation pipe. So if you got a farm and ranch store, you can probably get that stuff. So this is 37 feet long, and it turns out that Schedule 40 PVC slides right over that perfectly. So you only need one bolt through it to hold it, and then you have your base insulator, which is the PVC pipe. With this antenna, I had a coupler that I poured into some cement and then had a hole about 20 inches below the cement for the insulator to sit down into, so it stabilized everything. And with the tall one, the 20-meter one, I didn't need it for. 40-meter one, I did. I put some hose clamps around the antenna about 2/3 of the way up, and some links that you can unscrew, and you can put ropes through those and put a guy on them just to hold them in place, because they get pretty unwieldy when they're 37 feet tall in the wind. Okay, so now here's where the bear sleeps, right here. When you're transmitting in one antenna at one phase, it's coupling into the other antenna, and the other antenna is at a different phase, and it's coupling into the first antenna. And so this is called mutual impedance. And if you're closer than a half wave, then it really causes some issues with your base impedance. And so what it does is it modifies the base impedance of the antenna. So this is theoretical. For 90 degrees, my R was supposed to be around 20 ohms. My X, well, minus 15 ohms. So how do we find out what that really is? Well, the first is that you take the antennas and you float them both. When you take a 1/4 wave vertical and you don't connect it up, it floats. It's not there. So you go over to the first antenna, antenna 1, and you measure the base impedance with the other antenna out of the circuit. And then I came up with 44 and plus 64, which means it's inductive. Okay, then I went over to the other antenna and floated the first one. Got 66 ohms and 43 ohms on the reactance, so it's also inductive. So then I calculate what capacitor I need to make the 43 ohms on that second antenna 0. And it turns out to be 261 picofarads. So the next thing I do is I hook up a 270 picofarad capacitor to ground on the second antenna, and that makes the second antenna totally resistive, and the other antenna now is shifted in its base impedance based on the second antenna being in the circuit. And as you can see from this formula here, the R22 is the resistive part of the second antenna, and it's times the difference in impedance between the antenna in and out, and the square root of that gives you the mutual impedance of the two. Okay? Well, now I took a look at what my mutual impedance was, and it was 28.7 ohms and minus 12.7. So it's not too far off the theoretical. All right, so now I can actually calculate the base impedances of my antenna. So with the Z1 for my first antenna, I take the values that I measured when it was all by itself, and then I add in the mutual impedance by the ratio of the currents. Well, since I want to have equal power to each antenna, the currents have to be equal, so I just put half of the current into one and half of the current into the other. But one is at 0 degrees and the other is at minus 95.3, so there's a phase difference. So when you do all the math and crank it all out, the base impedance of the first antenna is 28.7 ohms and 38.38 ohms in reactance. And on the other antenna, it's 75.97 and 72.69. Now, notice, those aren't equal. And this is where we fall off the wagon if we're trying to do a phased array, because now we have a problem. We got to somehow get these base antennas, because they're not 50 ohms either. All right, so how do we fix that? Well, this is where we get into linear circuit theory, okay? Well, first of all, question. If I have a short antenna, what do I do to make it look longer? I put in a coil, right? I put in an inductance. All right, so if I have an antenna that's too long, what do? I put in capacitors, right? Now, which would you rather do? Burn up power in inductors or have no power burned up in capacitors? Dumb question, right? All right, so I cut my verticals so that they were about 97 degrees instead of 90 degrees. So they're long. And they have to be tall enough so that the mutual coupling, the negative 12 that was in my mutual, has to be overcome by the inductance in the base impedance of the antenna. All right? So you make them longer than a quarter wave. So here we have that both of our X values with the mutual are inductive. That's good news, because now what we can do is use what's called the C-match. Now what's cool about this is we don't have to fool with inductors at all, so we're going to bury them. And what we're going to do is we're going to use capacitors to resonate the antennas as parallel tuned circuits. And if you know about phase in a parallel tuned circuit, it's a zero phase shift. So that means there's no contribution of the matching network to your phase. So you don't have to worry about your phase shifting on you. All right? So here's the way we do it. Network A on the left is the antenna. It's an inductance with resistance. All right, so what we do is we calculate what the Q of the antenna is, or the quality of it, which, by the way, also tells you what the bandwidth of it is. Well, with a 3-inch diameter aluminum irrigation pipe, it's pretty broad-banded. And so you take your Q and calculate it by taking the reactance of the series and divide it by the resistance of the series, which we've already measured, and that gives you the Q. All right, then if you take Q squared plus 1 times the series resistance, you come out with the parallel resistance equivalent in network B. And then you take that resistance divided by Q, and that gives you the reactance in parallel. And so you've converted your series circuit of the antenna into a parallel circuit. Okay? Okay. Now, you want the power to be equal to both antennas, and so you can come up with the top equation using the capacitors. And then you also have a voltage divider between R1 and R2, where R2 we want to be 50 ohms, and so you can use the reactances for that too. So these are the design equations to get this antenna tuned up. And so here's how we do it. The total capacitance of the two capacitors together, we want that to resonate the coil so that it tunes at 14.2 for 20 meters. All right? And the ratio of the capacitors, take the R parallel over to the right and divide it down to the 50 ohms that we actually want to match to. And so this network right here, the C match, is the magic that does it. Okay? So now I have two antennas with my C matches on them, and I've got 50 ohms going into them. And so the power's divided, the phase is at the right phase. There's zero contribution from the parallel tuned circuits to the phase, so that's not changed. And the power should be fairly evenly divided. So here's a calculator that I have in my book this is a cardioid antenna that is classic. Everybody kind of knows this pattern. But you see the two powers are at 0.5, and the phasing is at 90 degrees, and the spacing is 90 degrees. And look at the depth of the null. It's 131 or 161 dB. Get that with a Yagi. Okay? Now, what happens if I shift the power by 5%? That null goes from 160 dB down to minus 13. That's how important the power balance is on a phased array. All right, so here's my pattern. And when I got all done, what this tells me is that with my parameters, I should have somewhere around 30 dB null in my nulls, okay? So how do you adjust such an array? Do you have to go buy an operating impedance meter like broadcast stations do for 100K? Do you have to come up with an oscilloscope and sampling loops and equal cables and all of that stuff? No, it's not that hard. It turns out that because of the way we've done this with symmetry and with just the laws of physics, it's simple. So here's how you do it. You go down to the local truck stop and you buy yourself some El Cheapo SWR bridges. And you bring them home and you stick a dummy load on each one individually. And you put about 10 watts of power into the dummy load, and you mark on the forward power meter reading a mark where 10 watts is, because these things aren't calibrated. So you're going to calibrate it to your transmitter for 10 watts. And so you mark both of those, and then you take them out and you stick them right underneath the C match. And you use the same barrel connectors and everything, so it's equal. And then once you've got it all set up like that, you transmit 15 watts out to the array. And then you go over there and you kneel down next to the antenna so you're not coupling to it. And you tweak the capacitors for minimum SWR and equal forward power. And then you go back and forth until you've got the best you can do. Now, the SWR isn't as important as that equal power. So you may have 1.3 on one of them and 1.1 on the other, and so what? But the forward power is what you're really looking for. And the SWR will be low overall, okay? And then what do? Well, you take out the little cheapo SWR bridges and you hook up your coax and you go operate. And this is what the easy neck pattern for my 20-meter verticals look like. And you can see pretty low angle of radiation. Okay, so does it work? Well, I had a gap Challenger in my backyard, which was basically omnidirectional. So I used that as a reference antenna. And so I started making measurements on receive of all different stations all over the place. And I called out most of it because it got too busy, but here's what it looked like. So the dashed line is the Challenger, which is the omnidirectional, and the solid line is my phased array. And you can read some of the reductions in signals around the compass there on the different nulls, and notice that the forward gain, according to EasyNet, was supposed to be around 5 dBi, and I got about 3 dBd, which is about right. And so it did work very, very well and very easy to do. And oh, by the way, it was really fun to do this. I ran this array for 3 years through rain, sleet, snow up above the insulator, and it was solid as a rock. And not only that, because you've done a parallel resonance on the antennas at the middle of the band, the phase difference between the antennas is 0. And so when you QSY down the band, your phase shifts, but they shift together. And what keeps the pattern in place is the difference between the phases. And since there's no relative difference in the phases across the entire band, this pattern holds together across the entire 20-meter band. I even used it once when I was working for the Air Force to talk to a B-52 on 13 megs. No problem at all. Anyway, so it's easy to tune, and really, I'm not going to go through all this because you can read it. So the next project is that the 20-meter band went down, and so there was nothing on it at night. So I thought, well, people say you can't put a set of verticals close spaced and make them work. So I decided, okay, I'm going to try it. So I used this method with 40-meter verticals. They were 37 feet tall and 17 feet apart, 1/8 of a wave. And after I got the network done, I went out and installed it. Took me less than 20 minutes to tune it up. And my first contact was 7A4NX in Algeria on 20 meters at 6 o'clock at night with 100 watts. And I said, it works. So here's what that EasyNet stuff looked like. And here's what my 40-meter phased array looked like. And I used the same pattern as I did for the 20-meter array. So my goal in this was to demonstrate that you can do phased arrays, but you don't have to be a math whiz, and B, you can use a combination of transmission line theory, antenna theory, and linear circuit theory to make the worlds converge on a phased array. and it works really, really well. Okay, now, there's only one drawback. Excuse me. I'm sorry, those are stations that I actually heard and their signal strengths. Sure. Yeah, that's what those are. Okay. Now there is one problem. Okay. I live on a postage stamp in the middle of a neighborhood. Okay. And then there's these things called ground fault interrupters. Okay. And me with 3,700 feet of radial wires under the grass, and yes, my wife did help me put them in. I was on the air one night. I had just bought my first Alpha, and I was on 40 meters on a phased array, and ding dong, and I go to the door, and my neighbor lady's standing there white as a sheet. And she said, something in my kitchen just burned up. And so I went over there, and her GFI in her kitchen had seen my 4 amps of RF in the ground and said, I'm giving my life for my owner and for her appliances. And so it smoked it. So I had to move the GFI out into her garage and out of her kitchen. And anyway, long story short, I had to do some measurements of where the threshold of pain was, and turned out to be 300 watts. So I couldn't run any more than 300 watts on my phased array. But it wasn't all bad news. My wife let me have a 5 by 5 square foot space in her garden, and I ended up getting my first tower, heaven forbid, and a M squared log periodic on top of it. But that's a different story. Okay. A shameless book promotion. This book's available on DX Engineering, and it has a CD inside of it, which is the same one you saw in here for modeling two-phased array antennas. There's also a program in there for modeling 4 squares or rectangular arrays if you want. And this can be used for that, because all you do is take the power divider and you go one more level with quarter wave sections on another T connector off of both ends. And that gives you a 4-port power divider. So anyway, so that's also in the book. And the all of the calculations for the 2-element array, there's a spreadsheet in there where you can make these measurements as you go through the book and plug them into the spreadsheet, and it'll calculate the capacitors and all that stuff. So anyway, hope this is helpful to you. Thank you very much. Any questions? Thank you. Yeah. Not a problem. The 20-meter ones stand there, no problem at all. And I get 90-mile-an-hour winds off the Great Salt Lake. And with the 40-meter ones, I had the rope radials on them, or not radials, but guys, and they were fine. I did have one supercell came off one time, and it snapped one of my ropes and bent the antenna over at the base insulator. And so if you buy good rope, you shouldn't have any problem. Yes, sir.
Nice presentation you make.
Well, thank you.
Simple and nice and smooth.
It is.
Nicely done.
Well, thank you.